chapter 13 is officially where multivariable calculus starts, because this introduces the idea of a function of more than one variable. Now, it's not like you've never seen one before, you know, here and there throughout math courses. You know, you've done stuff like that. Even back in pre-calc, there'll be times when pre-calc students are doing identities, and an identity might feature something like, you know, tangent of x plus y or something like that, and the students have to prove that that's equal to some other expression that's the same thing. Well, you know, that is a multivariable function. It's a function that depends on two different things, x and y, with the implication that they're completely independent of each other. There's no connection between x and y. They are both what we call independent variables. But we never actually used it as a function back then. So they've kind of flashed in and out on occasion, but never to be actually used in function form. And so this is where that sort of becomes a part of the math canon, if you like. So what we're looking at in general here, so you know, single variable. I mean, the names of the variables can be anything you like, but most likely y equals f of x. That's kind of far and away the most frequently used single variable function notation. So in this case, x is my independent variable. And y is my dependent variable. Oh, sorry, dependent variable. Because y depends on x, right? It doesn't have to be that. I mean, you are allowed to write x as the dependent variable and y as the independent variable. There's no reason why you couldn't have x is some function of y. In fact, there are times when we do want that. But one way or another, we have one independent variable. And of course, we may have more than one dependent variable. When we do parametric equations, you know, x is a function of t, y is a function of t, z is a function of t. So when we say single variable expressions, single variable functions, we mean single independent variable. You can have as many dependent variables as you like. Depends on the context to some extent. But in effect, you only have free choice of one thing. You know, with the vector valued functions that we just did, you get to pick t. You pick t equals 5, fine. But that's it. Everything else is determined for you. The vector valued function will tell you what x is, what y is, possibly what z is. You know, and you could go further if you really wanted to. So that's what the terminology is referring to. And so once we start talking about multivariable, pens also seems to be running out of juice as well. What we mean is there's more than one independent variable. Now, our wheelhouse is going to be two independent variables. That's going to be most of the time. But we are going to see plenty of examples with three independent variables as well. And you can have as many as you like. But given how closely these are associated with surfaces and graphs and visuals, you know, four independent variables is starting to get a bit outside of, you know, application. I mean, it exists as a concept, but it's not really helping anyone a whole lot for the most part. So the things that we're going to mainly see here are f of xy or f of xyz. And you know, at the top I wrote y equals f of x, which is fine. But I mean, if you just talk about the function, really all I need to write is f of x. Y equals f of x is terminology very much associated with the graph of a function, which is one aspect, but functions aren't only about graphs. You we do plenty of work on functions that have nothing to do with their graph or any kind of visual representation. Similarly here, I could write z equals some function of x and y, but only if I'm particularly interested in sketching a surface, which we now know z equals f of x and y would represent some two-dimensional surface in space. Possibly a plane, possibly a sphere, possibly a hyperboloid of two sheets, or a cone, or whatever we've talked about. So it's kind of weird in that the book has already dealt with the idea that z equals x squared minus y squared or something like that, but it never did it in a functional form. It just did it in terms of the graphs. Now we're kind of going to the math side of things and say, let's just treat this as a function. And all the things that we'll think about with functions like limits, continuity, integration, differentiation, etc., which is kind of the start of the journey here, if you like, really. Put it in terms of that picture I've been trying to keep over the whole course, in the fact that Calc 3 is basically redoing everything that you've done before. Everything from pre-calc, Calc 1, Calc 2, that was one big arch of single variable calculus. You start the journey in pre-calc, learning about the foundations of it, in particular some of the geometries. But then you go on to do the calculus. We're redoing it. So that first chapter was really the pre-calc for the most part, the chapter 11 that we did. Chapter 12 specifically focused in on vectors. Now, it did use some calculus. Obviously, we did R prime and R double prime and stuff, but it was particularly looking at vectors in space. This right now is kind of the start of Calc 1, but in multivariable. So we're going to do a bit of limits and continuity, and then get into integration, differentiation, and what you could use them for. All right. Like I said, I could here, if I was thinking about this in terms of graphing, I'd probably put W equal, oops, sorry, I'm going to put this in red. You know what, let me just start all this over because that's not what I meant to write at all. Here I probably put Z equals f of x, y, if I was thinking about a graph. Here I'd probably put W equals f of x, y, z, but I would not be thinking about a graph because that would necessarily be a four-dimensional graph, which isn't happening. So yes, you could use three variable functions, but we're never going to care about what the graphs look like. All right. But in these cases, these things would be the independent variables. Simply meaning that I'm free to pick x and then completely separately pick y and possibly z without any consideration of what I've just done. X can be 7, y can be 2, z can be 19. Picking x doesn't have any knock-on effect to what y needs to be and so on. So that's the kind of setup we'll be dealing with for multivariable functions. So like a lot of things, one of the things we need to think about is graphs and the domain and range that go alongside them. All right. So most of section 1 is really just considering two variable functions, thinking about the domain, thinking about the range, and thinking about actually not the graph, but a process that we consider the sort of equivalent of a graph, but is much more drawable. All right. In effect, really, it's a revisitation of the idea of the trace from the first chapter we did, but applied in one particular way. So, for example, let me give you. What should we do? So here's an example of a function. So the domain And the range, well, conceptually the same idea. But this time, domains used to be intervals on a number line, right? The domain was something like -3 to +8 or something along those lines. It was a portion of a number line, a portion of the x-axis in effect. This time, the domain is a description of what needs to be true about x and y for the function to exist. I feel like I'm going to just erase it. I'll just cross it. Well, I'll just cross it out. I'm going to come back to this example in a second, just because I think a different example would best illustrate range. So let's imagine we had this instead. Now, notice that the domain here can't be descriptions of what x can be and what y can be, as though they're two completely separate things. Because it's not the case that I can say, well, it is okay for x to be 7, but it's not okay for x to be 0. Right? That's not a true statement, because it is okay for x to be 7 as long as y isn't 8. Right? If x was 7 and y is 8, that's not okay, because I'm not going to consider the square root of a negative number in, we're considering real values in this particular case. Similarly, x can be 0 as long as y is -5 or something like that. So it's not really a case that you can talk about what values of x are okay as their own completely isolated group of numbers and then y. It's more about how x and y relate to each other, right? What really matters here for the domain is what? Right? I mean, basically, I need x minus y has to be greater than or equal to 0. In other words, x has to be greater than or equal to y. So the way I can talk about my domain is more visually on the plane. If I draw the line y equals x, now in this case, let me just put it in dashed to start off with, because whether points on the line count or not is a separate consideration. But in this case, points on the line will be fine, right? If x equals y, that's acceptable. And then I have to decide which side of the line I want. Do I want above or below that line? I want below, right? I mean, basically pick any point and just ask whether it checks out or not. No, because x can be negative as long as y is even more negative, right? X can be -12 as long as y is -13 or something. But if you want to run a test, this point is 1, 0, which checks out. This point is -1, 1, that does not check out. So any point will give you either a good result, which tells you you've picked a point on the correct side, or a bad result, which tells you you've picked a point on the incorrect side. So I would indicate this domain by basically indicating that it's this side of the line. And of course, it goes on forever, right? There's no sort of bounding to that. And say the line itself is acceptable. So domains now are regions of the plane rather than intervals, right? Any point in that green area represents a point where that function is defined. Any point outside of it, that function is not defined. Okay? That's why I took away the first example, because as you can see in the first example, all points work, right? Well, I'll go back to it in a second, but the square root 1 plus x squared plus y squared, you couldn't find an x and y for which that didn't exist. So in that case, the domain is the entire plane. There's nothing to rule out at all. But in this case, it's only half the plane. Notice that if the function had instead been this, oops, sorry, It's supposed to be a minus. What would the difference be? Right, so this time I'd leave the line dashed. Basically, solid lines and dashed lines are the new version of open dot and closed dot, whether they're included or whether they're not. Solid line means those points are part of it. Dashed line means that's the boundary, but those points aren't part of the domain. So in that case, I draw exactly the same thing, except have a dashed line. Going back to, this is a separate thing, so let me kind of separate that just to illustrate that in that case. Oops. What's the range here? This first function, the square root x minus y. Not all real numbers. If you pick x and y values that are allowed in there, what can you say about the output? Right, 0 and greater, right? Square root of something we always consider to be positive or possibly 0. So the range considerations really are all about the function itself, and so to be honest, that hasn't changed from single variable calculus. The way you'll decide on range is pretty much the same regardless of whether it's just one variable going in or several variables going in. What's allowed out of a function is basically a property of the function itself. And so the range here would be 0. And so the range can still be written as an interval because the range is just a single valued output. It's the domain that needs fairly considerably rethinking. Okay. Now, I think before I do more examples of this, since it's up and we've got ourselves thinking about it, it's probably a good opportunity to introduce the... No, because it's the square root of something.
Range is the height of something, right?
It's all the values that can come out. I mean, it is.
Okay.
So it's the, if I was graphing this, it would be the z height.
Okay.
But at the moment, I'm not graphing it. The domain is simply a way of visually showing what values of x and what values of y are acceptable, but they're not separate from each other. You can't list them one at a time. You know, domains can't be expressed in terms of intervals anymore because they express a connection between x and y. They're now regions of a plane, whereas they used to be regions of a number line. But regions of a number line can be written in interval notation. Regions of a plane really just need to be drawn. Yeah.
For the second example, would the range be 0 to 1?
No, the range would be 0 to infinity as well, except 0 is not included now. Because 1 over a positive number is still a positive number, right?
Like, like if you put like it would be all like if you put 1 over any number, it would still be like less than 1.
But this could be a fraction, right? This could still be at say 1/2 or 1/3. So you can go bigger than 1, but you couldn't get 0 out anymore. So the domain here is the same except you take away the line. The range will be the same except you take away 0. But yeah, it's perfectly okay for that to be a fraction rather than an integer. But let me introduce the other idea from this section, which is, like I say, it's not graphing, but it sort of allows you to imagine what the graph would look like, and it can be a very helpful tool. It's what we call level curves. Like I say, in effect, it's a bit like the idea of the trace that we did back in chapter 11. But what you're considering is curves, which may be straight lines. So I'll say curves, but incorporating the idea of lines as well, on which the function has a constant value. So like, for example, in this case, let's go back to square root x minus y. Let's think about all the places where this function takes the value 1. Well, what's my requirement for that to be true? What condition will make that true? Right, x minus y has to be equal to 1, or put it another way, y equals x minus 1. So when I come to my graph, now bear in mind, we already had y equals x as part of my domain, because along y equals x, that means that the function will be 0, right? So what in effect we're doing here is showing where this function takes on a constant value, c. Now if c is 0, that will be the line y equals x. That was part of our domain. We now know that for c equals 1, we will want the line y equals x minus 1, i.e. slope 1, y-intercept negative 1, so it would be parallel, one space below. What about if we wanted c equal 2? In other words, f of x, y is equal to 2. What would that require? X minus y equals 4, and so y equals x minus 4. So this time, it's a straight line, again slope 1, so again parallel, but this time with a y-intercept of negative 4. Tell me about c equals 3. Right, it'd have a y-intercept of negative 9. Kind of running out of space, but so here's negative 1, negative 4. So I guess I can't draw it in because I've written my thing right to where negative 9 would be. But on yours, you can label that as negative 9. So they're what we call the level curves. Notice that in some ways, they're a more elaborate way of incorporating the domain, right? Because you can see that c equals 0, 1, 2, 3. And by definition, therefore, you know, I don't have to pick integers here. If I wanted c equal 1.5, well, it'd be a straight line somewhere in this interval. Or if I wanted c equals 2.7, it'll be a parallel line somewhere in this interval. So basically, as c goes from 0 to 1, I've got lots and lots of parallel lines kind of covering this whole region, and then 1 to 2, and 2 to 3. But in effect, if I was to label every value of c, you know, 0, 0.1, 0.2, 0.3, 0.4, I'd basically be filling in this to look like the domain that I've just drawn. In effect, it will be the domain. This part, of course, remains empty because no value of c corresponds to regions up here because you can't put these points in. These points aren't part of the domain of the function. So level curves in some ways are more elaborate, more information-dense versions of the domain. Sometimes the domain's all you need. Sometimes you just quickly need to know what's okay and what's not. Level curves are more elaborate, but they also, of course, help you imagine what the graph looks like, because in effect, they are the z coordinates of any point on that line. So what this is really telling me is that graphically, c equals 0, this line is actually part of the surface. C equals 1, this line actually, if you picture a line 1 unit straight out from the board, that's a line on the surface. And then this should be 2 units out the board. So basically, this is a sheet that's kind of curving away from the board, basically like a parabola, because it's kind of going 1, 2, 3. You've got wider and wider stretches. Well, sorry, not like I guess an upside. It's actually going this way, I guess, if you think about it, right? Because I only go this far to go up the first unit, but further to go up the second unit, further still for the third. So actually, it's more of a square root x kind of curve. But if you were to try and picture the surface here, it's sort of curving away from the board like that. So without having to actually draw a three-dimensional picture, level curves help you to kind of just mentally think about what the surface would look like relative to your page, right? Your page is the z equals 0 plane. So this c equals 0 here, this is what we previously called the trace. But sometimes when we did the traces, we also consider, well, okay, what about z equals 1, z equals 2? That's what level curves are, basically. So if you're asked to find or draw level curves, you're basically drawing the lines or the curves on which your function takes a fixed value. And you label that. The level curves must be labeled. They're kind of pointless if they're not labeled, because it doesn't give you a sense of that third dimension, that third distance you need to insert. I'll give you an example of that in a second. All right, but any questions on that? Notice, of course, that level curves are something that are used quite commonly in applications, as the book talks about. For example, a contour map basically is a series of curves which all have the same height, the same altitude. So, you see that on page, move my fingers, like page 875. If you see a contour map where basically you're looking at the landscape compressed down to 2 dimensions. But each one of these might be labeled as like, this is, 1,500 feet, and this is 1,600 feet, and this is 70, whatever. So you're able to interpret, what the landscape looks like, even though you're only looking at a 2-dimensional graph. That's exactly what a contour map does. And the closer the curves, because the curves on a contour map are supposed to represent equal increments of height, so the closer they are together, the steeper the landscape, right? Because you've covered less horizontal distance to go up the same vertical distance. So you could, tell here that, I don't know, the way I've drawn this is a much steeper ascent than this is to the top of that landscape, because the lines are more closely packed together in that direction than they are in the second direction. Or you might look, air pressure maps will show what they call isobars. ISO always means the same constant, or the same value of. So isobars are ridges of constant pressure. So if you see like the diagram, any line on some kind of atmospheric or weather map is showing you all the regions that have the exact same atmospheric pressure. And then the different line will be different pressures, and the closer they are together, the more dramatic the pressure difference, and therefore maybe some more significant weather systems occur in there or whatever. Or isotherms are graphs where all the points on a curve have the same temperature. So they'll show temperature fluctuations across a region and how they are, whatever. So you get lots of contour graphs used in applications to show points of the same altitude, the same pressure, the same temperature, the same whatever it may be. All right. But we're using them in a much more abstract way, just to, well, what we're doing is effectively the closest thing to an actual topographical map of altitude, because we're mostly kind of using it as z, the height, if you like. But so far, we're not really going into applications. We're just treating this as some generic thing. But domain and level curves are very closely related to each other. Range is a separate topic. But like just to indicate that, let me sort of pull a couple of things up. I think my iPad is just about going to make it. But to give you, you know, a couple of examples, let's imagine we had so I'll have f of xy and g of xy. Yes, but I mean, the fact that they're connected is irrelevant here. We're just keeping those completely separate. So let's make this. In fact, I'm going to put this as I'm going to put a pi over 2 factor in here, just to really kind of drive things home. So what would my level curves look like for f? Well, I'll tell you what, let's backtrack a bit and work it from this ground up. What's my domain for f of xy? Right, everything. Right. Now, to some extent, it's almost not worth drawing the graph because it's just, you'd just be shading in the entire xy plane. Sometimes the new version of negative infinity to infinity, we don't really need to go into it, but that symbol basically implies that twice, all real numbers twice. But you'll sometimes see that. You don't have to worry about it. That's not going to be a part of our course. Further down the line in math, you start doing abstract algebra and stuff like that, discrete, then you'll start talking about that notation in more detail. But all real numbers will be fine as well. What's the range? 0 to infinity, including 0. But what about level curves look like?
First one would be y equals square root of 1 minus x squared. So
Wouldn't it be 0? 0 is equal to root of x squared plus y squared.
Right, so if we think about c equals 0, so what's that look like on the graph? That's just the origin, right? That's not actually a curve or a line at all. It's just the origin. So yeah. So when we talk about level curve, it's effectively it's the origin. If you want to really kind of be technical about it, is a circle of radius 0. Is what a point is. So it is a curve. It's just a curve that doesn't really go anywhere. So there's c equals 0. What about c equals 1? So this is what you were, so it'll be a circle, right? Basically, x squared plus y squared has to equal 1. So a circle radius 1 would give me c equals 1. What about c equals 2? Nope. Nearly, but circle radius. Right, it's x squared plus y squared equals 4, but that means a circle radius 2. So there's c equals 2. What about c equals 3? You probably see where this is going now. Circle radius 3. So there are my level curves for this. So sort of think through that. What's the graph look like? It's a cone, right? Because every time you go 1 unit further along horizontally, you go 1 unit further up vertically as well. And we've done that, right? I mean, if you think back in chapter 11, if z is square root x squared plus y squared, that means x squared plus y squared equals z squared, or x squared plus y squared minus z squared is equal to 0. That was the form we looked at back in chapter 11, right? That was how the equation was presented to you back then as an elliptic cone. Now we're changing it up so that we're thinking about it in terms of a function, but there is a lot of overlap between what we're doing here and what we did back in chapter 11. Of course, there is a difference, right? That this is only the top half of the elliptic cone. Z is definitely positive here, whereas this version, as we saw back in chapter 11, was the top and bottom part. So there is a slight difference. The minute you square both sides of something, you can potentially change that up slightly. But there is a slight difference between. But let's think about the second one. Right? What's my domain here? Or my domain? So still, right? Everything, no value of x and y isn't okay here. At the range, like you say, Asher, that's -1 to 1 because that's a property of the sine function. Doesn't really matter what's going into the sine function. That's what's coming out. So this time, what's c equals 0 look like? What is sine 0? Right, well, because the input's going to be 0, so it's the origin again. Right. What would guarantee an output of 1 from this function?
What if you could put like one of the values as either 1 or -1, and the other as 0?
So that would work. But in general, what general prop? I mean, that's one example. Right. I mean, to get an output of 1 from the sine function, I need this to be, well, firstly, let's say pi over 2, right? That's the first possibility. So for this to be pi over 2, this thing would need to be 1, which means a circle radius 1. So circle radius 1 will give an output of 1. But let's think about what the, we're kind of getting a similar thing to evolve. What about my circle radius 2? What's my output if I've got a circle radius 2? 0, right? Because that's now, if the circle is radius 2, this is the square root of 4. So 2, so sine of pi. Sine of pi is 0. What about circle radius 3? We know about sine. I mean, sine's not a one-to-one function. It keeps spitting out the same results over and over. It'd be -1, right? Because it'd be sine of 3 pi over 2 this time. And then the circle, I've run out of room, but the circle radius 4, back to 0 again. But the point I want to draw out is, notice if I wasn't labeling my level curves, I'd have identical diagrams here. But notice label my diagrams, my level curve. What's the graph look like to this? Do you actually visualize in the surface here? it's like a sine wave, but rotated around, right? It's basically like ripples in a pond, right? I mean, this is basically what you get if you drop a rock in a pond, right? You get ripples rippling away from where it goes in, but the cross section will be a sine wave. So same level curves, totally different graph, right? Same traces, but with different heights associated with them. I think the book might have I'm not going to start trying to draw that, but I think in the homework or somewhere, well, it's not the same. I mean, number 50 in the homework has a similar look to it. It's not truly the same, but it's a similar thing. So that kind of underlies the importance of labeling your level curves, but also showing you how, you know, you can kind of see from the pattern of these level curves how they're going to cover the entire plane. No part of the plane that will have a level curve go through it at some point. Therefore, the domain is everything. Also, the level kind of have implication the range as well. You know, you can kind of see here 0, 1, 2, 3, 4. The pattern, there'll never be a -1. There's not going to be a C equals -1 or equals -2. So you kind of see the range implied there. Here you can see 0, 1, 0, -0, 1. You can see how C never leaves -1 to 1 range. So the range is kind of implicit as well. So it's almost the case that level curves supersede the domain and range, but not quite enough that we don't want to consider both side by side, but they are quite closely linked together. Right. If you've done level curves properly, then the domain and range are pretty much there by implication. And that's what this section's dealing with. Right, it's going to ask you to, you know, I skipped over some of the most straightforward stuff, but I'll start by asking you to just evaluate multivariable functions. Plug in x equals and y equals 2, something like that, which is as simple as it sounds. Then 21 to 32, I start asking you about domain and range. And then after that, they start bringing sketching surfaces and sketching a contour map. Contour map, level curves, same thing. Just two different ways of asking the same question. So 51 to 58 are this idea. And this is the thing that's going to help us quite a bit going forward. So definitely try those. But I don't think there'll be anything too confusing in this. Read through the section and you know, I think the book's fairly self-explanatory, and the questions aren't too bad either. So. Okay. I also would like you for homework. I mean, I know you're working on your take as well, but please, I always hope you'll read through the section coming. In particular, here, read through section 2. I don't plan doing a ton of work from section 2 because most of it is terminology, definitions. You can just read. You know, all I'm doing is write out exactly what the book, which is a waste of everyone's time. This is also maybe our chance to at least catch up some of the day behind it that we've managed to get. So, section 1, homework should be fairly straightforward. Read through section 2. All right. If, to be honest, I'm bothered about. I need to. Just my kind-hearted nature, but I really, really need you to do section 2. So I'll put the take-home back to 5. Just so if I don't want you don't have time to read section 2, but I probably expect you to have done it because I'm only going to spend a little bit of time on that on Thursday before going to section 2. So take home I'll accept on Friday evening rather than Thursday evening. Bye guys, see you on Thursday. Thank you. So some of it I kind of mentioned a bit in class the other day without getting as far as the terminology. But as I said, we don't really talk about intervals anymore. Because intervals are very much something that occur on a number line, and that therefore is kind of associated with a single variable. So intervals are something that make perfect sense to talk about in single variable calculus, but they don't really have a whole lot of value in multivariable calculus. Because if we're trying to talk about, for example, the domain, as we talked about last time, or other aspects of things, it tends to be more about location on the plane than position in an interval or not inside an interval. So what we talk about are neighborhoods. We didn't use that phrase last time, but it's basically what we were talking about. Is a neighborhood is a region of the plane that will contain some points and not contain other points. And so that's sort of the new equivalent of an interval, right? Some points are in, some points are out. Points on the boundary may be in or may be out. What we call boundary points to the domain. Boundary points to the neighborhood, rather. So that's a little bit like with intervals. Do you have a bracket or do you have parentheses? You know, is the point, are the end points included or are they not included? Well, a neighborhood now might look something like this. And as we said last time, a dashed line would imply that the boundary points are not included in the neighborhood. A solid line would imply that they are included. Technically, I guess you could have some included, some not, but that starts to look a bit weird there. But it introduces that idea. It introduces the idea of interior points and boundary points. Those are pieces of terminology you should know and are fairly self-explanatory. Notice a delta neighborhood is a disk. Delta neighborhood is one where the boundary points are all some distance delta away from a fixed point. So it's a circular disk with the points inside included and the points outside not included. But the consequence of some of that is seen when we move on to limits, because let's go back to Calc 1. If I talk about the limit as x approaches, let's say, 3 of some function, what did we need for that to exist? Right, the two one-sided limits had to both exist, and they had to be the same thing. Right. If the function itself didn't exist at all on one side, then you could consider it to be a special case one-sided limit. But what we needed was the limit as x approaches 3 from the left, and the limit from x approaches 3 from the right to exist and to be equal. Right? Because that was the two ways you could approach this value, right? No, they didn't. What would I be talking about if I needed that to equal f of 3? What did that tell me?
Well, I think I once learned that f of x equals like f of c, with c being in whatever value input.
But I didn't need that to be true for the limit to exist, to be continuous, right? So limits and continuity were two separate ideas, related but separate ideas. So the limit can exist without the function existing at all. Remember, we had like holes in the graph and things. For a function to be continuous, the limit exists, the function exists, and they're equal to each other. So that, which we are also going to come to, but that's the question of continuity coming up there. Limit by itself only requires that. But now in Calc 3, what we're going to be looking at is something along the lines of the limit as x and y, because remember, we've got two input independent variables. So they might be approaching, let's say 0, 0 is a frequently seen one, of some function of x and y. Well, actually, let's keep this as general as possible. So let's make this just any two numbers, a and b. It's frequently going to be 0, 0, but this could be just a and b in general. All right. Now, my problem here is that, you know, if I'm trying to replicate what went above, where to determine whether a limit exists, I need to think about all the different ways I can get closer, you know, how can x get closer and closer to 3? Well, two ways. It can either get closer and closer to 3 from the left or closer and closer to 3 from the right. But on a number line up here, here's 3. There's only two ways that I'm approaching that value, right? One of them from this side and one of them from this side. The problem is that now in Calc 3, now I'm talking about, let's move on to another screen here. Now I'm talking about x and y getting closer and closer to some point AB. Well, it's not the case anymore that there's only two different ways I can approach that point. I've switched from being able to approach it in two different ways to approaching it in an infinite number of ways, right? Stepping up one dimension is not just kind of doubled or tripled or whatever the different possibilities. Now, well, I could come in like this, or I could come in like this, or I could come in like that, or I could come in. I mean, there's just a never-ending stream of different ways I can approach that point. And that becomes problematic because our setup was kind of checking that all the possibilities existed and were the same, which is fine when there's only two of them. It is not practical once there's an infinite number of them. Now, that's not to say that we don't have some intuition now about limits and how they work that is still going to be valid. You know, for the most part, if a function was a regular function, you know, not piecewise or not some kind of really contrived function, and you were able to just direct substitute your limiting value in, then that was the result, right? The very first thing you ever did with any limit was just actually put x equal to the value and see what happens. And if that gave you an answer, and if the function wasn't piecewise or some quite contrived setup, then that was the answer for your limit. And that's still going to be true here. So despite this complication, for the most part, that's me okay. It does basically mean that in Calc 3, it's an awful lot easier to show that a limit doesn't exist than to show that it does exist, formally. Informally, you'll often just have a good gut feeling about whether a limit exists, and that's fine. But it's very easy to show a limit doesn't exist. You just find two different paths and get two different results. Now, for example, sort of a nice easy example to show here. Let's imagine that I had the limit, I'm in purple, but never mind. The limit as xy approaches the origin, or more accurately now the z-axis, right? What used to be the origin is really now the entire z-axis. X and y approaches 0, 0 of the function x squared minus y squared divided by x squared plus y squared. Now notice any other point at all would be fine. You know, if I was asking you, in fact, let me just instantly change this question. Let's imagine I was asking you to find the limit as xy approached 2, 1. Well, as you might expect, I'll just put x equal to 2, I'll put y equal to 1 and see what happens, and I get 4 minus 1 over 4 plus 1, so my answer is 3/5. Done. It's a regular function. There's nothing weird going on with it. I can sub those values in. In fact, I can sub in absolutely any value and get a meaningful result except 0, 0. Right? That's the only thing where direct substitution isn't going to work, because it's going to give me an indeterminate form. And indeterminate forms are still a thing now, just as they were back in Calc 1. Yeah, Ash. Say what again? No, because as we're about to talk about later today, derivatives don't exist anymore. And so we're going to need something different. Partial derivatives. But partial derivatives are not the same thing as derivatives, and so L'Hopital's rule isn't going to fly, certainly in the original form, because it doesn't have a direct equivalent. So that's off the table, at least in any sort of direct form. It's not to say that you can't eventually come up with some similar idea, but it isn't L'Hopital's rule. That's very much a single variable calculus idea. So in this case, that would be fine. Like I say, pretty much any two values, as long as they're not both 0, is fine. And if this had been x squared minus y squared plus 1 on the numerator, so that direct substitution here gave me 1 divided by 0, a bit like, again, like in Calc 1, that you can safely say limit doesn't exist. It's when you get an indeterminate form that you don't know, and you'll have to do a bit more work. The problem is, though, now that that bit more work can be a much more complicated thing if it is to be the case that the limit exists. This can be a lot harder of a thing to show. But notice in this case, let's just consider two different paths. So I'm going to consider path 1, which is along the y-axis. Right, so let's start with along the x-axis. Makes a bit more sense. I'm going to do both, but let's start with along the x-axis. Now, bear in mind, I'm in 3 dimensions, so I'm already, traveling towards the z-axis here. When I say that x and y are going to 0, 0, that basically means I'm heading towards the z-axis. But I'm specifically heading towards the z-axis along the x-axis now. So along the x-axis, of course, y is already 0. Right? So it's like I'm heading to this point, but path 1, well, where I started, I don't really know, but certainly like the final approach is along the x-axis. By the time I'm actually sort of docking with the origin, if you like, I'm definitely coming in along x. So y is already 0. And so that means that I'm now really thinking about the limit, not as x and y both approach 0, because y already is 0. All that's left is for x now to be getting closer and closer to 0. And this function is now x squared plus nothing over x squared, x squared minus 0 over x squared plus 0. So now L'Hopital's rule is relevant. Or just, any other version of it. What's the answer to that? It's 1, right? I mean, x squared divided by x squared is 1 all the way to 0. And don't forget, a lot of this is still the same case. The limit as x approaches 0 means that x never will actually be 0. It's getting closer and closer. It never actually gets there. So this will be 1 regardless of what value x takes, as long as it never reaches 0.
So are we just assuming that we're doing x, y versus 0, 0, but then
I'm picking one particular approach, right? I mean, this limit as a general idea means I can approach the origin in absolutely any way I like. I'm just picking one here to consider. And I'm then going to pick a second one to consider. Path 2, which as I said before, is now going to be along the, gosh, this pen is really being the worst. Along the y-axis instead. So this time, how I start doesn't really matter, but I'm coming into the origin along the y-axis. So now x will be 0. Right, x doesn't have to get closer and closer to 0. It already is 0 on this path that I'm choosing. And so now it's the limit. Y is still changing. Y is still getting closer and closer to 0. But x already is, so this is 0 minus y squared over 0 plus y squared. And that result will be negative. And so I found 2 different paths giving me 2 different answers. That bit hasn't changed. If it's not the same on every different approach, then the limit doesn't exist. Now, if those 2 things have been the same, that's when I'm kind of in trouble, because that doesn't tell me anything. Being the same on 2 paths doesn't mean that it will be the same on every path. So this method is never going to show that a limit does exist, because there'll always be one more path that you haven't yet looked at. But it can easily show that a limit doesn't exist. And really, that's all I'm going to ask you about, right? I'm not going to ask you to prove that a limit does exist. Knowing that it exists will be an important thing. But as I say, you have just a gut feeling about that. You can just tell whether a limit exists or not. That's not the same thing as proving it, right? Me saying to you, like I did before, what's the limit as xy approaches 2,1 of this function? Now, me asking you to prove that's a very different story. That's quite a complicated proof. Me asking you what it is just sort of you using your knowledge of things. That's fine. So I couldn't ask you to prove that a limit does exist realistically, but I could easily ask you to prove that a limit doesn't exist, and your job will be just to find 2 different paths for which that was the case. Notice, if you're thinking, well, how did I know to pick the x-axis and the y-axis? Well, what if I'd picked y equals x? I don't need to go to another one. Wow, that yellow doesn't show up too well, does it? Never mind. Got a bit ambitious, so let's go orange. If I pick y equals x, well, now there's really no need to write x and y both going to 0, because x and y are the same thing now. So saying x goes to 0 automatically means y is going to 0 as well. But now, of course, the numerator is 0 and the denominator is 2x squared. And so the answer is
0.
0. So there's another path with another result. So that would have done it as well. So it's not like you have to carefully pick out. I mean, generally speaking, x-axis, y-axis, straight line, they're likely to give you different things. It won't always work. If you tried, there are other paths that would also give you an answer of 0. But if you tried y equals 2x here, you get a different result. If you try y equals 3x, you get a different result. They're all going to give you different answers. So, pretty much anything you picked here would work. So it's not like you have to somehow ahead of time know which 2 to choose. That's not really the case. So that's what's going on when it talks about the limits and examples 2, 3, and 4. Then it moves on to continuity, which is what was brought before, and that's the same thing. For continuity, for a function to be continuous at a point, the limit needs to exist, the function needs to exist, and they have to be equal. That's the same set of rules as before. There's nothing new about that. So continuity. That's what I said. I'm not going to ask you to do that. I could ask you to show that a function is not continuous, which you could do by showing that the limit doesn't exist. I wouldn't ask you to prove that it is continuous. Again, really, these things are, if you were doing some kind of geometry, then these would be important. But really, the main thing of this section is that when we come to define partial derivatives and things, that we can write down a limit and have it mean something. We can describe something as being continuous. Without this section, that's not been defined, and so that doesn't exist. But that's all I want to say. That's why I wanted to read through it, because I don't want to spend any more time on section 2, because that's not really what we're kind of getting into in a big way. But section 3 acknowledges what I said earlier, is the fact that now the derivative as we've always used it is meaningless, because the derivative has always been an analysis of how a change in one variable affects a change in another variable, or causes a change in another variable, right? I mean, yes, the derivative is introduced via the tangent line problem and graphs and stuff, but at its heart, when we write dy dx, what we're saying is, as x changes, how does y change? But specifically with the derivative, that's talk about an infinitesimal change, not a large scale change. You know, I mean, it's one thing to say, you know, we have things like average rates of change, which are more interested in large scale things. But, you know, it's one thing to say, you know, if I add a certain amount of money to an investment, how much do I have after 20 years? That's sort of a large big picture thing, but that's not analyzing the incremental day-to-day changes as if I added, you know, that amount spread out over 20 years and analyze the change each day, what am I seeing, right? The derivative is very much a right here and now, what is a very tiny change in x having, or what effect is that having on y? What tiny change is being affected in y? Graphically, that represents the tangent line, right? That's how we introduced it, because if you've got some curve, y equals f of x, you know, we introduced it with the tangent line problem, saying pick a point and find the slope of the tangent line. But really what that's saying is, right in the vicinity of that point, a very small change in x, what is the change in y? And if you remember, back for differentials, the tangent line is an approximation of that, right? Going right back to Calc 1, we had the idea of delta y and dy. Delta y was the actual change. Dy was what we call the differential. Dy approximates delta y. And the smaller that difference is, the more accurate that approximation is. None of this works at 2 or more variables, right? Because what am I differentiating with respect to? If I've got z as a function of x and y, how am I supposed to write a derivative? Do I put dz dx? Why would I ignore y? Why? But dz dy doesn't make any sense. And even more than that, that's not really what a derivative does. A derivative is very much an analysis of, if I change this thing, what change do I see in this thing? So I am not interested in a situation where I change x a bit and y a bit and see what happens, because I won't know which one had what level of effect, right? I can't assume that they contributed equally, right? Let's imagine we find a function that is, let's say weight of traffic at the beach as a function of what time of day it is and what time of year it is, right? Now that weight of traffic is going to fluctuate quite a lot as I change those variables. But if I change both those variables, there's not much point in me knowing, okay, well, here's how much traffic there is at, I don't know, like Sullivan's Island at 10 a.m. at a day in July, and then I now look at 5 p.m. in a day in October. Because the problem is, I don't know which one was the significant factor, or were they both equally significant? Is it the fact that it's now 5 p.m. in the day, not 10 a.m., that's causing the difference? Or is it the fact that one of them's in July and one of them's in October, right? changing two different independent variables and trying to study what effect it has is basically useless, right? Because without knowing which one is having the more significant effect, which one the less significant effect, I'm not really getting anywhere. So yeah, basically what I need to do is try and find a way to only change one and keep the other fixed, right? If I was doing that analysis, what I'd really want to know is, okay, this day in July, what's the traffic at 10 a.m., what's the traffic at 5 p.m.? And then same again in October, what's the traffic at 10 a.m., what's the traffic at 5 a.m.? If I see the same difference in both, then I think it's really the time of day that matters. If it's a radically different thing, then I'm thinking then definitely the time of day matters. I can also, of course, compare 10 a.m. in July to 10 a.m. in October. So there I've only changed the time of year, not the time of day. But that's the kind of thing that's going to give me much more useful data points where if I can keep one of them fixed and change the other, that will help me. But the problem is, of course, I've got two different possibilities. Either I hold X fixed and change Y, or hold Y fixed and change X. Right? Neither one of those can be the derivative. Neither one of those does what a derivative does. What we do is we define both of those to be what we call a partial derivative. Right? So in multivariable calculus, the derivative is gone. Partial derivatives have appeared in the place. And a partial derivative basically takes the same concept of the tangent line problem and the difference quotient, but only treats one of the variables as constant at any time. So what that looks like when we actually do it, so again, calc 1, bear in mind partial df dx, assuming that I'm talking about some function of x. I won't write y as a function of x because I'm not talking about just a graph anymore, just talking about functions as a general idea. Partial df dx, remember, was the limit as delta x goes to 0 of f of x plus delta x minus f of x all divided by delta x. Right? That was my definition of the derivative. Y prime, or f, also called this f prime of x. Back in calc 1. So in calc 3, where now I've got a function of x and y, well, I'm going to have two different things. And I'm just going to take them one at a time. So one of them, I'm basically going to temporarily treat y as a constant. I'm going to hold y fixed, not let it change at all. Let x change and see what happens. So what I will have is the limit as delta x goes to 0. Right? I've allowed x to change by some quantity delta x, and I'm going to make that shrink down to 0. But this time, f is a multivariable function. So I've got f of x plus delta x, but it also depends on y. But then I'm subtracting f of xy. In other words, y is the same in both of those two terms. So I'm holding y fixed, and I'm dividing by delta x. Right? That is called the partial derivative of f with respect to x, and the notation it gets is this. Instead of d, you've got this kind of curly d to denote a partial derivative. The other notation is to write a little subscript, f sub x. That itself will still be a function of x and y. Now, that's the definition. The good news is that you already can know all the rules you need here. Basically, for a partial derivative of a multivariable function, if you want partial derivative with respect to x, then every other variable, might just be y, it might be y and z, whatever, treat those as if they're a constant. Apply all the derivative rules as if they are valued as a constant. Just you apply the rules to x. But then you can do the exact same thing the other way around and treat x as a constant and let y change, which we call partial df dy. and that will be the limit as delta y goes to 0. This time x hasn't changed. It's the same in the first and second case, but y has. Oops. And as you'd expect, we write that as partial df dy. And like I say, if the function was a function of x, y, and z, then you can also do partial df dz as well, but with the same idea. That's what's been introduced in section 3, the idea of partial derivatives. Now you'll notice it's a fairly easy thing to jump from the Calc 1 definition of derivative to the Calc 3 definition of partial derivatives as a concept, right? That doesn't seem particularly crazy of an idea. But we have lost a lot of the implications, right? There is no such thing as the tangent line to a surface, right? I can't I originally invented, I'm not taking credit for this. I did not personally originally invent the derivative, but the derivative was originally invented to find the equation of the tangent line, because a curve has a tangent line at a point. Surfaces don't have tangent lines at points. They have tangent planes, which we will get to further on in this chapter. The idea of trying to find the best flat plane to fit against a surface, but there's no such thing as a tangent line to a surface at a point. So we've lost some of the application or implication of that.
Would they have like tangent vectors, like what we just did?
No, because there'd be different ones in all different directions, right? If I was to, take your bag, for instance, and pick a point on my bag, it kind of depends which direction I go as to what slope I'd be traveling on. What I could do is try and take the span of all those vectors that you're talking about, which is what we would call a tangent plane. So, we'll get there, but we're going to have to constantly redesign how we're using derivatives now, as well as how we define them, because in a lot of cases, the original concept has gone, right? In a similar way that when we get to integration much later in the chapter, actually, I think integration comes in the next chapter, but that used to be area under a curve, right? There's no area under a surface. There's volume under a surface, but there's no area enclosed underneath the surface. So all of those things now are going to have to be rethought about in a new context of 3 dimensions. All right. But in terms of actually coming up with an idea for derivative, this makes a lot of sense and is a fairly easy extension. Notice, like I say, I never wrote it down. The thing that doesn't make sense, the first instinct for this may be the limit as both delta x and delta y go to 0 at the same time, and so you've changed x and y, and you're trying to study how both of these are affected, but you very quickly realize that that idea that you might think makes sense actually isn't going to do anything much good at all, right? Not only that, but even if it did create something workable, it's not much use, because it doesn't tell you, if a change is occurring, did delta x cause more of it? Did delta y cause more of it? Did they both contribute the same? I have no idea. I've changed too many things at once for me to have a sense of what role x is playing, what role y is playing. So this is no good to anybody, right? That might be an idea for a derivative, but it doesn't pan out at all. But the good news is, like I said, the actual math of these partial derivatives is nice and easy. So, for example, let's imagine I had this. If I want to know partial df dx, then I basically apply my differentiation rules, treating y as if it's a constant value. So what do I get if I differentiate 4x cubed y with y being treated as a constant?
I think you get, let's see, 12x squared times y
With the y change.
minus.
Dx. Dx, dy, dx.
No, this isn't implicit differentiation, right? That all happened when y was itself a function of x that I just didn't know back in Calc 1. Here, x and y are totally independent of each other. So it's a very different idea from implicit differentiation. Sorry, go back.
Okay, and then minus 2x y squared, and you just, since y is a constant for 7y4, you just, it's a 0, so yeah.
Just disappears, right?
Yes.
So that would be my partial derivative with respect to x, because, I mean, if you want to, you can, if you want to think of it in terms of the product rule, 4x cubed y, if I differentiate this, it's the derivative of 4x cubed, so 12x squared times y, plus 4x cubed times the derivative of y, y is a constant, so that's nothing. So if you like seeing the product rule, that's fine. Or you can just think of this as being 4y times x cubed. And so what's the result? Well, it's 4y times 3x squared. Either way, you end up with the 12x squared y. So is everyone clear how that result has come up? Right, so if you write down partial df dy as well. I do now. What is it?
4x squared minus 2y x squared plus 28.
Right, so I've just treated x as if it's a constant now and apply my rules. Everyone happy with that? Now, I do want to do more examples, partly just to give you practice, because it's been a while since we've done some intense, like derivative rules, product rule, quotient rule, chain rule, etc. So we need to get back and practice a bit of that. But before doing that, I'll probably do more of that tomorrow. But I think now's as good a time as any to kind of keep going. Notice, as I said, these results themselves are also functions of x and y. So I can differentiate those with respect to x as well, or with respect to y. Right? But notice this is going to start proliferating, right? Because this thing now, let me sort of color code this. This thing now I can differentiate with respect to x if I want, which we just use notation of double x as my suffix, or in the notation it would be d2 of dx squared, just like the second derivative back in Calc 1, but with the partial symbols. What would that be? Minus 2y squared. Because yeah, again, I'm treating y as if it's constant. But I can also differentiate with respect to y, which I will call fxy. That is written, this notation starts to look different than anything we've seen before, but this will be written as partial d2f dx dy. So there's 2 further derivatives for that one, and there will be 2 further derivatives for f1 as well. So in cat 1 was 1 first derivative, 1 second derivative, 1 third derivative, and so on. If you've got 2 variable function, there's 2 first derivatives, 4 second derivatives, 8 third derivatives, and so on. You start to really branch out. But I want you to just finish this. Will help see a point that's very useful. So find x, y, differentiate this with respect to y, and then find both the possibilities for the second one, differentiate them with respect to x and y. See what we notice about your answers. Boy, I was playing a lot of home when I moved this to the first time through. This now after 2 and 3 of what being done. The whole chapter 13, because if you're thinking back to 2, reduce derivative and all rules, rule, chain rule, to 3 applications. So graphing and then max minimum ones, differentials, stuff. This chapter is doing all that. That's where we're at. You're kind of trying to through the second time through sequence up to right now it's 2. Tomorrow we'll get into it. So what do you get for y? 12x squared minus 4xy. Good. And if let me change color just to kind of keep this up. So if I take f sub y, differentiate with respect to x, which we normally just write as f yx, what do I get? Right, I get 12x squared. 4x cubed becomes 12x squared minus 2x squared, and the 28y cubed disappears. Wait a minute, let's try that again. Differentiating that with respect to x, so it should be 4xy. I'm kind of ahead of myself. And say, no, they are the same thing. Before I come back to that, let's just finish up and do fy with respect to y, second derivative. So what's that going to be? Yeah. 4y. Good. So whilst there is technically 4 second partial derivatives, it's not a coincidence that those 2 in the middle are the same thing, right? These are known as mixed partials, right? That's not a concept that exists until you're at the second derivative level, but a mixed partial is exactly what it says. It's one where you're differentiating to at least one variable in one case and a different variable in one of the other cases. You know, obviously I could keep going with this. I could do a third partial derivative. So I could have something like f of yxx. I would still call that a mixed partial derivative. A mixed partial is anything where you have at least, you've differentiated with respect to x at least once and y at least once. But there is a rule that you'll get to in this, which isn't true for absolutely everything. There are exceptions to it. But honestly, I've never, ever come across a function for which this isn't true in any meaningful way. I generally am more of an applied mathematician, so most of my stuff has some relevance. But in my research, in every single course I've ever taught here, I've never come across a function that can be used for anything for which the mixed partial derivatives aren't the same thing. Fyx and fxy, same thing. And similarly over here, if I change the order, if I did f of xyx, it doesn't really matter what order I do it in. If I differentiate with respect to x twice and y once, I'm going to get the same answer regardless of how I do that. Now again, if a function isn't continuous, that might not be true. But honestly, functions that are continuous don't get used for anything. They exist as a concept, but they're not really doing a whole lot. So really, there are actually 3 second partial derivatives. fxx, fxy, or fyx, whichever one you want to call it, but they're identical, and fyy. And similarly, if you went to the third partial derivatives, there's actually only 4. There's fxx, 3 x's, 2 x's and a y, 1 x and 2 y's, 3 y's. There's lots of permutations of those, but there's only 4 different answers you can get. All the rest of them will double up on the answer. So it's not quite as bad as it looks. Like I say, in any meaningful, useful function, mixed partial derivatives are going to be equal. So you don't really have to pay a huge amount of attention as to what order to do it. And you'd usually see it given with all the x's, then all the y's, maybe all the z's if there were z's and so on. All right. So like this is the version that you'd use there. You just tend to list the x's, as many as there are, then the y's and so on. Although again, third derivatives don't do a huge amount. You know, most uses of derivatives go as far as second, and then it's just an idea after that, really. So tomorrow we'll keep doing a few more examples of this before we move on to section 4. But I mean, to be honest, that's all you need to know. I mean, you know all the rules of differentiating. If you know this too, you can probably do the homework. But I say I'll give you some more practice just to remind you about that. I also will just briefly talk about physically what we can actually interpret from this tomorrow as well. So. All right. And yeah, so if you do have any questions on the take home, you can email me tonight, but make sure it is either handed in to me in class tomorrow or emailed to me by 10 p.m. Right, so I'm not recording this. There we go. Another function which will be x squared divided by y squared. So for those, if you find all the first and second derivatives, because they're continuous functions, there'll be 2 first derivatives, fx and fy, and 3 second, fxx, fxy, fyy. See if you can find those. Yeah.
I know you said that there are partial derivatives where the x of x and y does not equal y of x, or we have to worry about that. Okay.
I mean, like I say, I literally, in however long I've been doing this kind of thing, 25 years, I've literally never come across a function for which that's not true.
Gotcha.
You could make one up, but it would be a pointless function.
Just make sure we wouldn't have like
So yeah, no, you won't have to worry about that.
partial integrals of this?
No, but in the same way that partial derivatives aren't the same thing as derivatives, there is something that's equivalent to integrals in multivariable functions that we'll get to in the next chapter.
Okay, so it's possible from.
But we don't call them partial integrals.
Okay, so it's probably go from like the partial xy to the partial x or something.
Right. The big difference is you don't use that kind of curly d at all in the integrals. So that's why we'd never call them partial integrals. But the concept is, and as you probably expect, in the same way that here we treat one variable as constant and use our rules on the other one, that's what we do with integrals as well. So let's think about some of these. So the first derivative, f sub x over here, well, I'm going to need the product rule. I'm treating y as a constant. So it'll be the sine of x plus y squared times 1 plus x. And then for this, I'll need to differentiate using the chain rule. So this will be the derivative of the outer function, so cosine of x plus y squared times the derivative of x plus y squared with respect to x, which is 1. Right? And so my answer is just the sine of x plus y squared plus the cosine of x plus y squared. Sorry, x. I missed out the x there. What's that? X cosine x plus y squared.
Wouldn't the y squared get canceled out though for the cosine? Because y would be a constant.
Well, for the derivative of the inner function, but it's the chain rule, right? So I differentiate the outer function, leaving the input the same. In the same way that if that was cosine of x plus 2, sorry, sine of x plus 2, it'd differentiate to cosine of x plus 2. Okay. F sub y, of course, doesn't need the product rule because the x is a constant coefficient now, but it does still need the chain rule. So that will be x cosine of x plus y squared, but this time the derivative of the inner function is 2y. So I'd write that as 2xy times the cosine of x plus y squared. Right? Happy with that? The second derivatives, fxx, well, if I differentiate the first term, I'd simply get cosine of x plus y squared times 1. And the second term, I'll need the product rule again, so I'll get another cosine of x plus y squared times 1. And this time x will be multiplied by negative sign when I differentiate. So minus x sine of x plus y squared times 1. So obviously this can be simplified to 2 cosine x plus y squared minus x sine x plus y squared. Okay, I'm not going to do all of these because I'm kind of beating it to death. But there's one example. I'll also do fxy just to drive home. Notice here I've got two options really. I can either take my fx here and differentiate with respect to y, or I can take my fy here and differentiate with respect to x, because I know that I'm going to get the same result either way. In fact, that's a way you can check that everything's going right in a test. If you find fxy two ways and they agree with each other, then you've got great confidence that you haven't messed up at any point before that, because if you had, that's when you'd notice it. So if I did fxy, the first one, I would get cosine of x plus y squared times 2y. And for the second one, I'd get minus x sine x plus y squared also times 2y. And obviously I could factor 2y out of that expression as well. But that's what I'd get either way. It might initially look different, but I'd get the same result once I'd, factored stuff and gathered everything together. Okay, so I won't bother with FYY because I'm out of space, and really all we're doing here is reviewing the product, quotient, and chain rules anyway. So is everyone happy with that? Good with that. The second one. Notice, technically that isn't continuous anywhere where y is 0. So the xz plane, this function's not continuous. So technically, that's an issue for the mixed partial derivatives. But as you can see, the mixed partial derivatives themselves won't exist when y is 0 either. So it doesn't really matter. That's why we don't worry about it. The chances are any place where the mixed partial derivatives wouldn't be equal, they don't exist anyway. I could contrive a piecewise function for which that wasn't true, but I'm not going to. So for this one, a bit more straightforward, fx will be 2x divided by y squared, and fy will be negative 2x squared divided by y cubed. Right? That one's much easier, just using the power rule, basically. I don't have any chain rule to use. And so fxx will be 2 over y squared. fxy will be minus 4x over y cubed, either way. And fyy here will be positive 6x squared over y to the power 4. And of course, I could do third derivatives and fourth derivatives, but I mean, if you get to that point, then you know what's going on. So everyone happy with that? Notice again that all of these functions can themselves be evaluated at a point. So for example, let me go back to that second case. Can I get rid of this screen? Is everyone happy with this? So let me go back to the idea that fxy is x squared divided by y squared. And so fx was 2x over y squared, and fy was minus 2x squared over y cubed. So let's think about what about if I'm at the point 2, 1. Well, f itself at the point 2, 1 is 4, right? 2 squared divided by 1 squared. fx at the point 2, 1 will also be 4. And fy at the point 2, 1 will be negative 8. So what do those numbers mean? What are my practical values? Because back in Calc 1, when we actually evaluated a derivative numerically, if I took a derivative, f prime, and plugged in a number, what did it tell me? I mean, there's a few things it told me, but initially, what did I think of that as telling me? I mean, what was I using it to find first when I did the derivative? Slope, right? I mean, the tangent line, but that told me the slope. So back in Calc 1, if down here, back in Calc 1, if, for example, f of x was equal to square root x, and f prime of x was 1 over 2 square root x, then when I said that, f of 4 is equal to 2, and f prime of 4 is 1/4, well, what that told me was that when I graph this function, the point 4, 2 is on the graph. Right? The f of 4 equals 2 tells me a point on the graph. And the second thing tells me that at that point, the tangent line has a slope of 1/4. Right? So I had physical meanings to these two numbers. Right? That was Calc 1. So what about my numbers here? I've got 3 values here. F and fx and fy all evaluated at the point 2, 1. Well, this one is telling me what? Z is equal to 4. In other words, the point 2, 1, 4 is on this surface. Right? It's not a curve anymore. This thing is a surface, and it contains the point 2, 1, 4. So the question becomes, well, what are the physical interpretations of these things? Well, bear in mind what's going on. Now, I don't really know what this surface looks like. This isn't one of those ones that we've looked at in the past. But bear in mind what we're doing. When we write fx of 2, 1, I'm treating y as a constant, right? So I've got some surface, just picture any surface, but I'm superimposing on that surface here the fact that y equals 1, which now is a plane, right? It's not a line anymore. Y equals 1 is a plane. I'm basically slicing through that surface with that plane, right? Because I'm considering both situations. And if I take a surface and slice through it with a plane, I now have a curve in that plane, curve of intersection, right? What this number's telling me now is the tangent line, or the slope rather, of the tangent line of that curve at that point. There is no tangent line to the surface, but the minute I slice through the surface with a plane to get a curve of intersection, now there's a tangent line. So I don't know if I can get a viable diagram, but you know, let's say I've got some kind of surface, and then I slice through it with a plane. That's going to give me some curve of intersection. And so the point, which in this, you know, this surface doesn't look anything like what I've drawn there. This is just a completely random thing. But if I pick some point, say the point 214, if this was the plane of y equals 1, intersected with the surface, now the slope of that tangent line, which is sitting in a plane, so the slope is very much defined as a rise over run idea, that's what the force telling me. On the other hand, if I slice through the same surface at the same point, but now with the plane x equals 2, because this time I'm keeping x constant, so it's the same surface, same point, but instead of slicing through with y equals something, I'm now slicing through perpendicular with x equals something. So that's going to give me a different curve with a different slope, and in this case the slope will be -8. So physically those numbers are still telling you slope, but the reason I can get all different values at one point is because I'm slicing through with different planes at that point. There's much better diagrams in section 3 in the book when you look through it. Ash.
I'm a bit confused about the partial of y. Shouldn't have been -2x squared to y to the -1.
No, because this is x squared y to the -2, so it becomes -2y to the -3. You subtract 1 from here.
Okay.
So powers on denominators get bigger when you differentiate. Powers on numerators get smaller.
Thank you.
So, you know, to be honest, we're not going to use this physical interpretation a whole lot, to be honest. But that's what it is. You know, if you're thinking like, well, what does this 4 and -8 mean? That's what it means. It is the slope to a particular curve that you can create if you consider taking a surface and intersecting it with a plane. Like I say, if you read through section 3, they do much better diagrams than I can do. You know, example 3 is a perfect example. Page 896. They do some work, they draw diagrams, and they show you exactly how their answers are showing themselves, basically. Okay, any questions about it? I mean, there are, you know, little extras in section 3 when you read through it, but essentially the main point of section 3 is to define partial derivatives and then just practice finding.
I think about what fxy would be like in that visualization.
Fxy is the z coordinate of the point. So because this is a surface in 3 dimensions, every point on the surface.
The double derivative thing, the partial derivative.
Oh,
Yeah.
Oh, so that would basically, well, yeah, that becomes really tricky. I mean, fxx becomes just concavity of that same, you know, so when I say this slope, on this tangent line has a slope of 4. Fxx will give you the concavity of that, whether it's concave up, concave down, just like Cat 1. Fyy in that. Fxy, the mixed partials really, there's really not much.
That makes sense because you see like the change in y, but you treated y as a constant, like, so it's not changing, right? Like,
Right. So in this case, because I treated y as a constant, that's what I'm saying. I've got a surface, but I want the curve that is both on that surface, but also in the plane y equals 1, because on y equals 1, y is a constant. And so the intersection of the surface and the plane will actually be a one-dimensional curve.
yeah.
And that's the curve that I'm then finding the slope of at different points. And like I say, if I did work out fxx, well, I'm still holding y constant. So now I'll be finding the concavity of this curve at any point. But yeah, the mixed partials, you'd really struggle to find a physical meaning to the mixed partials using that visualization. Because you're kind of switching up what you're holding constant halfway through, and I don't know I can give you anything meaningful really in terms of the graph. Sorry, what?
Would it be rotation or something?
No, not really. I mean, it's got plenty of value in what we're going to do, but not in terms of visualizing it in terms of a surface, you know. And you know, not everything has to relate to a graph in math. A lot of stuff does, and it can be very handy. But there's plenty of things we're interested in that really don't directly relate to graphs. So. Okay, so section 4, which we can move on to and then finish on Monday, is the multivariable version of differentials. Right, so let me just remind you, because this tends to be a section that causes more problems than most in Calc 1 when you come to differentials. So back in Calc 1, if y is some function of x, then the differential dy is what? F prime of x dx. Right, that was what I call the differential. It's functionally the same fact as writing dy dx equals f prime. It's just expressing it in a different form. All right, but what we use them for, well, I mean, ultimately the main value of differentials, by the time you finish Calc 1, the main values in them are use of substitution in integration, right? If you make a substitution, u equals x squared, then du will be 2x dx, or something like that, right? That wound up being, you know, 90% of what we use differentials for. But when it was first introduced, the point of differentials was it is an approximation of the actual change occurring in your dependent variable, but done in a more streamlined fashion. So in effect, what was happening here, let's say we had some graph and we're interested in some point here, x, xy. Well, the idea was what happens if you change x by some amount, delta x, right? You consider some small increase in x. Well, don't forget we have a tangent line to this graph. Right. I mean, at this point in Calc 1, all we were really interested in was tangent lines. We haven't really progressed much further than that. But this graph has a tangent line at the given point. And so as you change x to delta x, well, y is going to increase by some amount as well. But the actual amount y increases by, I've lost track of what will be a good color anymore. But the actual amount that y increases by would be this amount, the vertical change from the original y coordinate to the new y coordinate on the graph. But according to the tangent line, that's the change, right? If you're looking at the tangent line, that's the change that's happened here. Now, obviously on this diagram, they look quite considerably different, right? One is considerably bigger than the other because I've actually shown a very large delta x. Delta x is supposed to be tiny. You know, the notation itself, delta something in math, always has the connotation of a very small quantity, something that is ideally going to be going towards zero. But I can't really draw that. But basically, the thing in blue is what we call delta y, the actual change. The thing in green is what we call dy, the differential. It's a linear approximation of the change. Now, as I said, in this diagram, delta y and dy do not look similar. But if I'd made my increment very small, if delta x had actually only moved me to here, again, I mean, because I've drawn this to really emphasize things, it still looks quite a bit. But realistically, this close, delta y and dy would actually be very close to each other. One would be a good approximation of the other, but dy is just a multiple of dx, whereas delta y isn't. Okay, so the kind of problem that we did back in Calc 1, and I think it's worth reviewing that just to kind of remind you, because it's the kind of thing that certainly got forgotten easily and sometimes wasn't even fully understood at the time. But these things were supposed to represent approximate but quick to calculate changes or possibly errors. The two main questions in Calc 1 were either you change x by this amount, what's the change in y? Or when you make a measurement, there's an error margin in the measurement you make, what is the associated error margin in the thing you're calculating? Right, those were the two broad ideas. Mathematically, they were identical. It's just whether you regarded delta x as a change that you have caused or an error in your measuring equipment. All right. So, for example, let's take a physics thing. So in physics, power dissipated is voltage squared divided by resistance, right? That's an equation that relates power, voltage, and resistance. So if you had this isn't great. This is more of an because that's a multivariable function. So that's going to be more useful for what we're about to do in our chapter. So I should probably revise that. I need a single variable function. So let's have kinetic energy being 1/2 mv squared. Right, because mass is going to be constant, so this is only a function of a single variable. So what I would say is that, you know, let's imagine an object with a mass of, let's say, 50 kilograms, increases velocity from I don't know, 20 to 30 units. That's meters per second and kilograms if we're sticking with SI units, but units aren't really our wheelhouse here right now. So I know that the original K, kinetic energy, would be 1/2 times 50 times 20 squared. So that's what 1,000. Hang on, that can't be right. What? So 50 times 20 is 1,000, so 10,000, right? Well, 50 times 20 is 1,000, and then times by 20 again is 20,000, then half of it is 10,000. And then the new kinetic energy will be 1/2 times 50 times 30 squared. So 22,500. Now, this is good and bad in that by keeping the thing simple, it allows us to work out the numbers quite easily and illustrate, but it also kind of takes away the value, because the point of the differential is to approximate the change, which seems a bit pointless when it's actually quite easy to work out the real change. I mean, in this case, delta K, the actual change that's been experienced in kinetic energy, will be 12,500 joules, 12.5 kilojoules. Right, that wasn't really that difficult to work out, but it at least illustrates the point of the differential, where dk would be the derivative of that function with respect to v, which is what? Just mv dv, right? That's the differential form. In this case, you know, we've written that dy is f prime of x dx, but frequently we're not using x and y, we're using other things. So in this case, k and v are my x and y. So my function here is 1/2 mv squared as a function of v. M's constant, and so when I differentiate that, I get 1/2 m times 2v, so mv. And so dk will be m, which is 50, times the original velocity, which is 20, times dv, the change that's occurred in v, which is 10. So that's 10,000. Now, you would look at that and say, that wasn't a very good approximation, right? I mean, you're like 25% off, basically. Well, sure. Why is that not really been a great approximation? Because of what I've done. What thing in that question has meant it's not a great approximation? What could I change in my setup to the question that would have made it a much better approximation?
Like from 20 to 21.
Right, perfect. Like that's the thing that's the problem, is it's a huge change. I'm kind of really not being very honest by calling that delta v, because delta v should be a small change, at least relative to what I started off with. So if I've made that increasing from v from 20 to 21, it will be a much better approximation. It would also be a bit more valuable in the sense of, if this was 21 squared, I'd have a lot harder of a job working out in my head. So whilst I put that on the screen to sort of illustrate the calculations that get made, if I had changed this to 21, this thing now I'm a bit less certain about, but down here it would now be 50 times 20 times 1, and so that will be 1,000. Now that's a much closer number to the real change that's occurred. If you actually worked out 1/2 times 50 times 21 squared and subtracted 10,000, you'd be much closer to 1,000 now, because it's a much more realistic use of differentials. Okay, so that was the kind of thing that was going on. Now this is all calculus, you know, don't get me wrong, I'm not teaching you this. This was back in chapter 3.9, or no, 3.8. 3.9. So if you want more review or more practice, this is a ringing that many bells, then go back to 3.9 and read it. But I wanted to remind you of how differentials worked in single variable calculus, because their interpretation is very much the same in multivariable. Right? The differential is still an approximation of the actual change that's occurring, but this time, this would be a very good example of what we're doing, where the thing that or the formula that you're using depends on at least two different inputs rather than just one. So voltage and resistance, something like that. So the setup though, so back in Calc 1, if y was some function of x, then dy with f prime of x dx. Well, in Calc 3, we know every time we used to have a real derivative, we're now going to have some equivalent involving partial derivatives. And so if z is some function of x and y here, then dz, well, I kind of want it to look similar, but what should I use for my instead of f prime? What should I use? Should I use fx or should I use fy? Answer: both. We have to have a combination. So it's partial derivative with respect to x dx plus partial derivative with respect to y dy. So that's the new version of differential. Structurally the same kind of thing, but obviously more terms to it because I've got more variables. And if I had a three-variable function, then it'd be fx dx plus fy dy plus fz and so on. So calculating differentials is not a whole lot different, and using them is not a whole lot different. Still can be asked questions where you're making approximations of change or approximating error. Just use this formula instead. All right, so let me pick an easy problem from the homework just to illustrate this now, and on Monday we'll do some more complicated stuff from this. But let's look at question 22. Which gives me the volume for a right circular cylinder, which is pi r squared h. So in fact, I'm given a multivariable function. V is my output, my dependent variable. R and H, radius and height, are two independent variables because you can change the radius of the cylinder and change the height completely independently. And so the possible errors in the radius, height of delta R and delta H respectively. I wish I had this a bit more carefully. I don't actually give numbers. I'm going to modify the question to give some numbers here. But let's imagine you measure, when you measure your cylinder, measure R equals 20 and H equals 25. But your measuring equipment has an error margin of 0.1. What I would calculate for volume would be pi times 20 squared times 20. So, again, 400 times 5 is 10,000. So 3.14. What's next? Should know this, 1.5. Sounds good. Is that right? 3.14. So multiplied by 10,000. So 3.14.
Are we allowed to leave it as 10,000 volts?
Yeah, absolutely. Yeah, 10,000 pi is because that's a more accurate answer as well. But that gives me my answer. But the question is, what's the margin of error on that? Right? Now, the actual margin of error, I would need to plug in R equals 20.1 and H equals 25.1. Or, yeah, and then for the other end of the spectrum, plug in 19.9 and 24.9, and that gives me my range of values for the actual volume. But what differentials allows me to do is approximate that with dV, which will be V sub R dr plus V sub H dH, to use the notation that's relevant in this case. Instead of Fx and Fy, that's how I'm going to write. So what's my derivative with respect to R? 2 pi RH dr. And my derivative with respect to H? It's just pi R squared. And so I plug in 0.1, because that's the margin of error. It could go either way, but you're never more than 0.1 away from. No, don't overthink it. What you're given in the question will be your dr and your dh. Delta R and delta H will be the same as dr and dh. And
So we're not looking for the range.
No. Yeah, we're looking for the maximum possibility. And so I've got 2 pi times 20 times 25 times 0.1 plus pi times 20 squared, also times 0.1, which is 100 pi in the first case and 40 pi in the second case. So 140 pi is my possible error, which compared to 10,000 pi isn't too bad. Right? I mean, it's about 1.4%. So that's not a massive error. But that's, you know, without a calculator, that's something I can knock out fairly straightforwardly, whereas I would struggle to get delta V here. The question is, I want to know delta V. Delta V is approximately dV. But delta V will be what I get if I plugged in 20.1 squared and 25.1 squared. Sorry, not squared, just 25.1, calculated it and subtracted. And then, like Ash said, you'd also have to do it on the other side of the spectrum. Now, one thing you would notice is if you do delta V, the error wouldn't necessarily be quite the same both ways. What dV will definitely be the same both ways because it's a linear approximation, because it's basically a tangent line. So whichever way you go, you'll go the same amount up one way as you will go down the other way. But it will generally give you the maximum possibility. If dV is acceptable, then delta V will be acceptable in terms of whether an error is okay. So I'll be doing a bit more of this on Monday, but that's really all I have to say beyond just working examples. Right? I mean, that's all you need to know about differentials, really. This is a long chapter, so
Yeah, it's probably not going to be for another couple weeks at least.
26th of October, because there's 10 sections to this chapter. So
Yeah.
it's a long one.
See you on Monday.
Have a good weekend, everyone. Okay, there we go. So the setup for differentials, remember, is on page 904. There is some detail about differentiability on page 905 that I'd like you to read. It's not that big a deal for us, but it is a technical point that's the book's going to assume that you know at various times. So differentiability, it's the same idea as it was in Calc 1, but it manifests in a slightly different way. Remember, differentiability, for a function to be differentiable at a point, then its derivative needs to be defined. In other words, that limit that we have for the derivative exists. I mean, in effect, the same thing here, but of course, that limit definition allows for more than two different approaches. And so the limit itself is conceptually more complicated. But differentiability is the same real idea. But I mean, to some extent, it's like a lot of things. You have to pick a fairly weird looking function before it might not be differentiable. You know, things that are just x squareds and y cubes and sine x, cosine y, and just regular functions. I mean, they're going to just be routine. They're all going to be differentiable. But the book does talk a bit about how you can show that something is differentiable, and it's quite handy. The real point is that you'll see on page 907, they come back to it. They do a few examples on the approximation and error analysis that we did and will do more of. But then they come back to it with the idea that if a function is differentiable, that it's continuous. No, but to prove it's not continuous, you can prove it's not differentiable. Because differentiable implies continuity, but it isn't a requirement for continuous. So you can show something to be not. If you're asked to show that something is not continuous, you could show that it's not differentiable. But anyway, the book, like I said, the book talks about that. And example 5 in the book, I want you to read through a function that isn't differentiable. But what I'm really interested in with the differentials is the idea of approximations and error, as we talked about last time. So, for example, of this problem, so without a calculator, approximate the value of 3.1 squared divided by 7.2 minus 9/7. Now, hopefully you can see that kind of the setup for this is that I've got, you know, something close to 3 squared minus divided by something close to 7 divided by 3 squared divided by 7. In other words, what I'm looking at here is if I've got a function that's x squared divided by y, then what I'm trying to find is f of 3 plus 0.1, 7 plus 0.2, minus f of 3, 7. All right, so that's how I'd want to interpret that question, with the idea that if I'm, you know, this is what it's kind of showing you on right, the differential thing. So in effect, don't forget, this is early on page 904, where it gives you the idea that delta z is the actual thing I'm trying to find is f of x plus delta x, y plus delta y, minus f of x, y. Right, that's what you talk about when you talk about a delta z. That's what you're trying to find. dz will approximate that. So the thing I'm trying to work out here, I might want to call delta z, or I guess delta f 3, 7, since that's what z is. But I'm going to approximate it since I don't have a calculator with dz. So see if you can write down what dz is, and then plug in the relevant x, y, delta x, delta y. So remember, dz is partial df dx times dx. It's partial df dy times dy. So what's partial df dx here? 2x divided by y. And partial df dy? Negative
X squared over y.
negative x squared over y squared. Right, that's y to the negative 1. So that's my dz. So in this case, since x, I'm putting x as 3 and y as 7, dx, of course, is 0.1 and dy is 0.2. In effect, this is delta x, but delta x and dx I'm treating as the same thing, and same as delta y and dy. And so this will be 2x will be 6 over y is 7 times dx, which is 0.1, minus x squared, which is 9 over y squared, which is 49, times dy, which is 0.2. Now, I mean, I said without a calculator. Obviously, this is still not something that is sort of, trivially straightforward without a calculator. But I could, if I get a common denominator here of, I'm going to factor out the 0.1 from both terms. If I get a common denominator of 49, this would be, multiply top and bottom by 7. So 42 over 49. There'd be a factor of 2 left, so minus 18 over 49. So that's 28 divided by 49. which of course is 4/7. So that'll be 4/70, or 2/35. So I can't get it down to a decimal, but you know, at least without too much effort, I can create a fraction as my answer. If you want to really see the point of it, then you do go to a calculator, you put in fact, let's just do it rather than talk about it. If I put in 3.1 squared divided by 7.2, and then I subtract 9 divided by 7, I get, so this thing is 0.049008, so 6 decimals, whereas 2 divided by 35 is 0.057. So you see, I mean, it's not amazing, but it's not bad. I mean, it's what, 8 parts in 1,000. So I mean, I'm closer than 1% error with the approximation. So that's the kind of thing that illustrate. I don't know that you'd say this is really a use of differentials, but it illustrates differentials working. Now you could take this idea and make it much more elaborate in a much larger context where you can definitely reduce processing time in much larger calculations by doing this kind of thing. Because you're effectively making the calculation simply a linear process, you're taking away a lot of the complications. So this could be used to streamline and speed up processing time. But you could also use it for other things as well. So this is, right now, it's really sort of just making sure the concept is illustrated. And then there's some word problems as well, which I'm going to get to. Any questions on this before I move on? Let's look in the book. I'm going to do question 23 in the book. It says the possible error involved in measuring each dimension of a rectangular box is 0.02 of an inch. And the box is measured to be 8 by 5 by 12. Just 0.2. So the box measures as 8 by 5 by 12, but there's an error on every side of well, plus or minus 0.02 of an inch. Right. Question says approximate the propagated error and the relative error in the calculated volume of the box. If you remember back from Calc 1, propagated error means the error that carries through in your calculation. In other words, it's the actual numerical quantity of the error. You know, how much is your volume potentially off when you calculate it? Relative error measures that as a percentage of the measured volume. Because, you know, if I say to you that I've measured the volume of something and the error was 3 cubic feet, is that okay? You say, I don't. Depends what you're measuring. I mean, if your calculation for the volume was only 12 cubic feet and you might be out by 3, that's not very good. Whereas if the thing you're measuring actually had kind of, you know, 4,000 cubic feet and you're only out by 3, that's not bad at all. So your relative error kind of compares the two, and it is often more useful. So basically here, what have I got? This would be 480 cubic feet. Say feet or inches? Oh no, inches, sorry, cubic inches. But I say, I mean, the actual volume could be 8.02 times 5.02 times 12.02. Now again,
But is it minus above?
well, that's one option. So it could equally be 7.98 times 4.98 times 11.98.
So we double the error then?
No. So the error is how far away the maximum possible distance you could be away from the actual result. So if I'm measuring what's right in the middle, my error is one way or the other, but I don't double it because I can't be that far away from it.
All right, so that means we have to do two calculations.
Well, we're not doing those calculations at all. We're doing the differential, which will give you one value, which is the same either way. That's why it's an approximation. So let me show you what we're doing, and then I'll talk about that. So again, this isn't, this is one of those things where if you kind of walked in on this, you'd say, what are you doing this for? Why don't you just work out, get your calculator out, do 8.02 times 5.02 times 12.02, and subtract 480. That's the error. Or do it the other way, do 7.98 times 4.98 times 11.98 and subtract that from 480. There's your error. One of those, whichever is the biggest one of those two is your error. I mean, yes, because this isn't really how you would use this, but this is a very simplified approach to checking that you understand the concept. So it's a question that you would never actually do in real life, but you would use this idea in a more complicated setting. So I don't want you to sort of think that if it seems like we're not really accomplishing much in this problem, you're right, we're not. Just see this as showing how the idea works. But don't look for this to be some really meaningful process, because it isn't in that sense. But what I would say is that my volume basically is XYZ. And in this case, my volume with 8, 5, and 12 is measured to be 480. But I want to know what dV is. And dV will be partial dV dx dx plus partial dV dy dy plus partial dV dz dz. So what is Vx? Right, so yz dx. Vy? xz dy. Yeah, vz. So in this particular case, my y and my z, 5 times 12 is 60, and dx is 0.02. xz, 8 times 12 is 96, times 0.02. xy will be 40. So that's 196 times 0.02, which is what, 3.92? Yeah, 3.92 cubic inches. So that's my possible error. That's what I might be out. So the actual answer could be anything between 480 plus that, in other words, 483.92, or 480 minus that. That's the span that I'm looking at. Right. But also notice, so that's the propagated error, right? That's an actual numerical value that I could be out. And in some contexts, that's the really useful answer. But sometimes I want to know the relative error, and the relative error is dV divided by V, or whatever parameter you're working with. It's the differential divided by the measured quantity, which notice in this case if I divide everything through by v, x, y, z, that ends up being dx over x plus dy over y plus dz over z. So the relative error are the three relative errors added together. So that's 0.02 divided by 8 plus 0.02 divided by 5 plus 0.02 divided by 12. Which, I mean, I guess I could turn into a fraction with a common denominator, but it's not going to be pretty. So that'd be, gosh, what? So I guess my common denominator is 120. So
will it always be dx over x plus dy over y plus dz over z?
if it's the fact that it's linear in x, y, z, you know, it's got an x or y. If it had like an x squared in or a y cubed or something, then no. But it's usually a multiple of those things. It usually winds up being some, you know, maybe like 2 times dx over x minus 3 dy over y or something. It usually ends up being some combination of those things. So if I multiply by 15, so 0.3 over 120 plus 0.48 over 120 plus 0.2.
Would you be okay on the test if we left it as like?
Oh, yeah, I mean, you know, I'm not expecting any of this on the test by any means. But that would be my result. Of course, if you got a calculator, it's different, and you just go straight in. Is what?
Is that a 4 or a 9? If we could calculate it, would we still even need to do this problem then?
Yes, because you're illustrating the point, not actually really doing it. And that's 0.98. So that's 0.00816, which is so this is 0.81%, or sorry, 0.82% if I round it. So pretty low, you know, less than 1% is not terrible.
Do we have to multiply it by 100 then?
That is after I multiply it by 100. So that's 98.
No, I meant like the dB over v. We have to multiply that by 100
to get it as a percentage, yeah. I mean, it comes out as a decimal, so if you want as a percentage.
So what's the difference between writing it out as like dx over x plus dy over y plus dz over dz and doing it that way and just taking like 3.92 over 40? Is that like? Right.
I mean, that'd give you the same result. Okay. Because the reality is you don't really want both of those numbers. You want one or the other, because each one would then give you the other one. You know, if I multiply 480 by this, hopefully it comes out as 3.92 or close, because of the linear approximation. So you wouldn't. Yeah, you're right. Once you've got one of them, you can kind of use it to find the other. But you know, realistically, some contexts want the actual propagated error, others want the relative error. A question, again, I've had this in the past with this section, people like trying to work out why you're doing what you're doing when it doesn't seem to quite make sense, because the questions make it seem like, there are plenty of questions we do in calculus that are legit questions, legit applications of something that you would properly use in context to make this calculation. This isn't one of them. You would never actually use this for any problem like they're giving you here. And I wish they would be a bit more upfront and saying, just the question should really just say, illustrate the idea of differentials by doing this. Show that you understand the concept in a very simplified way. Because anything that will be practical use of this will be much, much more complicated. Not mathematically, but in terms of the number of data points that were in action. You know, like I said, this will really be a programming thing. Or later, it also builds up to the chain rule and exactly the same as back in Calc 1, really. You know, you have differential questions where you're approximating change, and it doesn't really seem a whole lot of point. And then pretty much from the next section onwards, that's not what differentials are for anyway, right? You've completely forgotten about the idea of approximation. Differentials are for substitutions and integration and calculus tools. And it's going to be the same here. Differentials are going to become a totally different thing for us. But this is where they came from. This is one sort of understanding of what they do. Okay, so there are more word problems in section 4, but section 4 is not the one I'm most, you know, interested in, because it doesn't really go any further. Right? What the subsequent sections of the chapter do don't carry on from this at all. This is a very standalone idea. All right. What any questions on that? What section 5 does is move on to consider the chain rule in multivariable calculus. And actually, this thing right here is almost there. Because if I was to divide everything through by, let's just say that everything depended on t, for example. If I divide everything through by dt, then actually that is the chain rule that we're about to look at. So that's how differentials and the chain rule tie together. The differential setup and what we're about to do, but you kind of treat them as separate ideas. You don't really link them together in terms of doing any problems. But this is where they tie together. So that's what we're about to look at next. But there is, well, I think before I do, let me just go back and remind you about Calc 1, the chain rule. Right, there were two ways that you could write the chain rule in Calc 1. Right. If y was some function of x, but x was some function t, then or so let's change that. Write this out slightly different because that's not quite the way we first introduced it. So if y was a function of a function, let's put it that way, of f of g of x, then dy dx was f prime of g of x multiplied by g prime of x, right? That's the chain rule in Calc 1, or one way of putting it. But the other way of putting it was to have y as some function of u, where u is some function of x. Right, that was the other approach. It's the same function, right? Y is f of g of x. But in this sense, you could write it as dy dx equals dy du times du dx. Right? These were the two ways you could write the chain rule back in Calc 1. They mean exactly the same thing, but one's using the derivative notation and one's using the f prime g prime notation. All right. The second one is the one that we're going to kind of take and modify to multivariable calculus, because f prime and g prime don't really have any analogies, right? They relate to the partial derivatives, but they're significantly different. Whereas, I mean, I guess we'll look at two different versions that sort of match up. But this is the one to keep an eye on because the new version will look quite similar. But when I say the new version, actually, we need to be a bit clearer. There's actually going to be two versions of the chain rule in multivariable calculus. So there's two different setups. Oh, you don't prefer, you're either given one or given the other. It's not two different ways to do the same thing. It's two different possible questions, two different possible ideas. So the first possibility is that you have some function of x and y where x and y themselves are both functions of some other variable t. So x might be g of t and y might be h of t. Let's call this z. Oh, sorry, no, the book calls it w actually, so I guess I'll stick with what the book does. I guess w makes a bit more sense because that way, whether it's a function of x and y or x, y, and z, you can sort of stay consistent on that. So notice that w truly is not a multivariable function here, right? This isn't actually what we've been talking about in Calc 3. If I tell you what t is, this tells you x, that tells you y, and so this tells you w. So really, at its heart here, w is just a function of t, and so there is such a thing as dw dt, the full derivative. And the chain rule says that this will be partial dw dx multiplied by dx dt, which notice looks very much like the Calc 1 chain rule. Right? The chain rule that I just wrote down in Calc 1, it wasn't w and x and t, but this basically was what it looked like, except for this is a partial derivative, not a full derivative. And the reason for that is that you are also, there's no reason why I should do that for x and not y, so I'm going to do the same thing for y as well. Which notice I could write as partial dw dx like that, dx dt. Partial dw dy dt. Now that is the chain rule involving partial derivatives, so it is a Calc 3 topic, but ultimately what it accomplishes is to find an actual derivative, not a partial derivative. That is very much a tool for breaking a very complicated function that you need to differentiate into smaller chunks and doing them individually rather than trying to do the whole thing at once. Right? For the most part, that's used as a computational tool because you could always, if you wanted to, do this without partial derivatives. Right? For example, let's imagine, and I'm just going to make something up because I don't have it in the notes, but let's imagine w is x squared y e to the power of x plus y. Well, we'll have that for now. Well, let's say divided by sine y. And x is t squared plus 1, and y is natural log of t cubed plus 1. Right. Be a real mess. There's no way we're doing this. And I wanted to know the derivative of W with respect to T, because ultimately that exists, right? If I decide that T is 3, all right, X is 10, and Y is natural log 28, I can plug those two numbers in here, and that'll give me a numerical value. So I pick T and I get W. So W depends only on T. But notice, to do this without partial derivatives, I can write W as a function of T directly. It will be T squared plus 1 squared times natural log of T cubed plus 1 times e to the power of T squared plus 1 plus natural log of T cubed plus 1.
That seems complicated.
All over sine of natural log of T cubed plus 1. Right? So technically, yes, there you go. There's W as a function of T. You can differentiate this, but it will be absolutely awful. You would need, you've got the chain rule on this, you've got the chain rule on this, you've got the chain rule on this. This is a triple product that would need the product rule twice, divided by this, so you need the quotient rule. This is a function of a function of a function, so you need the chain rule twice. Trying to do that, I mean, it will be pages and pages, and the chances of not going wrong somewhere are pretty slim. As given, even as given, to be honest, differentiating this with respect to X and Y is not great, especially Y. X is not that bad. Partial dW dx here won't be too bad because you're treating Y and sine Y as a constant. But partial dw dy won't be great. These, of course, are nice and easy. dx dt and dy dt are easy. So, if I was doing it this way, I've got to find 4 things. Partial dw dx, not too bad. Partial dx dt, incredibly easy. Partial dw dy, the worst bit of it, but not awful. Partial dy dt, very easy. The way you get your answer will be a big jumbled mess, but at least you would have an expression for dw dt. If you needed to then put t equal to 4 or whatever, you could do it. As opposed to just trying to, in one setup, one line, try and deal with every different rule that's being applied in that expression. So hopefully that would give you a feel for why doing it in this kind of chunk piecemeal process and assembling all the terms together at the end would be a much more preferable approach than to try to do it all at once. Right. So this version is very much a way of taking a complicated function and trying to break it into smaller pieces and deal with them one at a time to then assemble your answer. Does that make sense? Right. Again, for us, it's mostly going to be an illustration of the process. The other version of the chain rule is going to be the one that we use a little more practically. But the reality is there are plenty of practical situations where you might have to differentiate a very complicated function. But I'm not going to give them to you on a test because it's just not a good use of time. The whole point of this is you wouldn't be doing this if the process didn't take a ton of time. If it was easy to differentiate, you wouldn't need this anyway. And if it's complicated to differentiate, this doesn't really make it much quicker. It just, instead of trying to do the entire thing in one line, you're doing it in 4 different pieces and then putting it all together. Say it again.
Kind of like the same thing with getting the normal.
Right. Yes. Exactly the same. Yeah. Generally speaking, the less you're trying to do in one go, the more likely you are to get it right. Mistakes tend to creep in when you're trying to keep 5 different things, 10 different things, juggle at the same time. So I might ask you with a simple version in the test to do this, to the point where you might think, why am I even using the chain rule? Why don't I just do it exactly as I would have done in Calc 1? But I might tell you to do it just so that you can show me you understand this idea. But again, in any meaningful way, it's going to be a long question, whichever way you approach it. So that's one version of the chain rule, where W is a multivariable function depends on x and y, or possibly x, y, z, obviously. You know, if z also depends on t, then you'll just have a third bit, you know, dw, partial dw dz, dz dt. But w depends on x, y, or x, y, z, but those things themselves only all depend on t. That's one version. All right. Second version is a true Calc 3 problem. Where w depends on x and y. I'm trying to remember what letters they still stick with. G and H. Yeah. W depends on x and y, but x and y themselves are multivariable functions. So instead of x being a function of t, x is a function of s and t. And y also a function of s and t. So now in this case, notice w is truly a multivariable function. Right?
Are they the same S and T?
Yeah. So if I tell you s and t, you can work out x, you can work out y, you can then work out w. But w is still, by implication, ultimately a two-variable function. And so now there is no full derivative of w. Now there is only partial dw ds and partial dw dt. So now it's a very similar looking thing to last time, but now everything's a partial derivative. There's no full derivatives anymore because there are no single variable functions here. So partial dw ds is partial dw dx times partial dx ds. But you've got to do the same thing on y because x and y are both as important as each other here. So that's the full multivariable chain rule where everything truly is two variable in this case. You can write this as w sub s equals wx xs plus wy ys. That's a more sort of compact, quick way of writing it. But of course, that's only one of the things I'm interested in because I also need to consider the partial dw dt. And so that will be partial dw dx dt plus same thing with respect to y. Again, I could write that more succinctly as wt equals wx xt plus wy yt. And that's the second possibility of the chain rule. Now, section 5 just takes both of those and presents them one at a time with examples. But whether you have one independent variable or two independent variables, potentially even three independent variables, that's the way it's going to work. Okay. I'll do a bit more of that tomorrow before moving on. But this is very much just a show this in action thing. You know, here's a function, or here's a series of, you know, here's w and x and y, run the process. You know, you're not really doing an awful lot with it right now, but you kind of just, again, illustrate it. There is a note at the end on implicit differentiation that I'll mention tomorrow. But if you're going through the homework, the first few questions, in fact, and the book draws your attention, you know, questions 7 through 12 are exactly what I was saying, where it asks you to compare the two methods. Either run the first version of the chain rule, well, not either. First, run the first version of the chain rule. Second, scrap all that, just write w directly as a function of t and go with the Calc 1 approach and compare the two. So you get to see sort of a side-by-side compare and contrast kind of thing. So I would do the first few of those, as well as any section 4 homework that you've got to do as well. So, all right, like I say, I'll wrap that up tomorrow and move on to section 6 as well.
Thank you.
See you tomorrow, guys. It's recording. So this is 13.5, number 20. It asks you to find the partial derivatives in 2 different ways. So W here, it's not a W. W here is x squared plus y squared plus z squared. And x is t sine s. Y is t cosine s. And z is st squared. So this is a sort of a compare and contrast. Firstly, use the chain rule, as we talked about. Now, obviously, in this case, there are 2 things to find: partial dw ds and partial dw dt. So start by finding partial dw ds, which according to the chain rule is partial dw dx times partial dx ds. Same thing for y, same thing for z. And then the same thing with respect to t. But then secondly, actually create w directly as a function of s and t and do it that way as well. And see what you get. This group of questions is really trying to illustrate, give you practice at the chain rule, but also make you see that sometimes one way's better, sometimes the other way's better, sometimes it's about 50-50. You can't always know ahead of time.
Plug in t, do we need to plug in for x to make everything t in there?
The second way you do, yeah. The second way, you're actually plugging x, y, and z into the function.
And then the first way is I have like 2x times.
Oh, I see. Yeah, your final answer should just be a function of s and t. Yeah. The part of the deal of using the chain rule that way is to then substitute in the result. Yeah. So if we do it the first, I guess you guys still going. I'll give you the element. So partial dw ds using the chain rule will be partial dw dx, so 2x, times partial dx ds, which is t cosine s, plus partial dw dy, which is 2y, times partial dy ds, which is minus t sine s, plus partial dw dz, which is 2z, partial dz ds, which is t squared. Right. And then I need to plug those things back in. So if I plug in x as t sine s, this will be 2t squared sine s cosine s. Y is t cosine s, so minus 2t squared sine s cosine s. Obviously, those terms cancel. And then 2z, which is st squared times 2t squared. So this will be 2st to the power 4. So that's my result.
Would you give us something like this on the test for like easily cancel out, or would you do this?
It depends what the point of it is, really. Maybe. I mean, to some extent, you only realize that it's simple and easily cancels out if you know what you're doing. You know, if you mess up the differentiation, then it's not easy anymore. So it's not like it's an easy question. It just has a result that simplifies a lot if you know what you're doing, which is not quite the same thing. So I would have no qualms against giving a problem like this. You know, if those two terms hadn't cancelled out, it doesn't make the question harder. It just makes the answer uglier. Similar here, partial dw dx. So again, 2x, but this time dx dt is just sine s. Partial dw dy is 2y, and this time cosine s. Partial dw dz again is 2z, but this time it's 2st. It's my partial derivative. But of course, 2x sine s becomes 2t sine squared s, and 2y cosine s becomes 2t cosine squared s, and this becomes 2st squared times st. But those first terms, of course, Pythagorean identity make those two just 2t. And then I've got 2s squared t cubed, which I could factor 2t out of if I wanted, but it's not really necessary, I don't think. So both results turn out to be fairly okay. And of course, this time around, you would actually get that result. Oh yeah, it was 2st, wasn't it? Yeah, sorry. I didn't copy down my own t, so yeah, you're right. 4s squared t cubed, sorry about that. But of course, this one, if you actually just directly substitute at the start, so this in some ways belies the point of doing this problem, because if you actually sub in here, x squared plus y squared becomes t squared sine squared s plus t squared cosine squared s, and then z squared becomes s squared t to the power 4, which of course is just t squared plus s squared t to the power 4. And in that form, then the partial derivatives are very straightforward, right? Partial dw ds, first term disappears, and so you just get 2st to the power 4, as we expected. And partial dw dt will be 2t plus 4s squared t cubed, with a lot less effort really there, but only because of the simplification that happened. So this is nothing more than a practice question and seeing the two things side by side giving you the same result. But you'd never in this situation choose to use the chain rule. The direct, you know, I guess what I'm trying to say here is you don't, in any practical sense, you don't start with this situation. You start with a single function that you're looking to differentiate, and you create the w, x, y, and maybe z, depending, yourself. And you would only do that if the original function was complicated. If it was as simple as this, you would never be remotely interested in trying to create a situation where you then use the chain rule. Whereas, and I'll have to move the screen, but is everyone happy with this? Any questions about this? So the reality is, what do you actually use this for? Imagine we had this. Right, that will be a real mess of a function to try differentiate with respect to s or t. So what I would do is recognize in this case really two key expressions that are reappearing, and so I'd say, okay, well, x I'll write as s squared plus t, and y as s divided by t. And so now I can write w as the sine of x times e to the power y plus the natural log of y squared divided by x. That's a much simpler function to differentiate with respect to x and y, and then x and y themselves differentiate with respect to s and t. That's an example of where you might be interested in using the partial version of the chain rule to make one single complicated line instead a series of chunk lines that you can do one at a time and combine at the end. So whilst a question like the one we just did is a perfectly good illustration of the procedure, and in a test would check that you understand it, it's not how you use it. Okay, this will be more how you use it. Okay, in which case the compare and contrast is meaningless. The only reason I'm even considering the chain rule is because the original version is so messy. So. Okay, happy with that? All right, let's move on and look at section 6. And you'll note that there's a sort of a change in sort of rhythm here. The first 5 sections have very much just been create the concept, introduce the idea of the partial derivatives and differentials and the chain rule. Section 6 onwards is applications of them. Not graphing applications, well, they involve graphs, but not, back in Calc 1, the first big application we used for derivatives was to basically create the graph of a function without using a calculator, right? You went through finding maximum, minima, critical numbers, maximum, minima, points of inflection, concavity, x-intercept, y-intercept, and put it all together so you could sketch the curve. We're not going to do a similar thing here where we do a whole analysis and you can sketch the surface, right? That's just not practical because it's just, we've pretty much seen all the surfaces that are realistic to make sketches of. It's one thing to sketch a hyperboloid of one sheet, but more complicated things are just bordering on impossible to make a good sketch of. So we don't go down that path, but we're still doing sort of applications. And the first thing we look at is something called the directional derivative. And the idea of the directional derivative is what we've already said, picture some kind of surface, right? And the easiest thing here for visual is just a hillside. That's what they use in the book as well. You imagine some kind of hillside. But with an x-axis, a y-axis, and a z-axis. So z is your altitude, but x and y give you kind of your geographic location on the hillside. Well, we've already said that partial df dx and partial df dy, if my hillside is of this form, right, if that's the equation of the surface, then partial dz dx means on your hillside, pick a vertical plane where x is constant, right? So if this is my x-axis here, then pick a plane parallel to the wall. Slice through the hillside with it, that will give me a curve in the hillside. And the partial derivative gives me the slope of that curve at any given point. Right? Similarly, partial dz dy would mean slice through with some y equals constant, x equals constant plane. So that will give you a different curve going down the hillside. That also has slope at different points. But of course, we may well be interested in what about the slope going this way? Right? What if I'm interested in going down the hillside, not parallel to the x or y axes, but at some angle? Well, that's what we call the directional derivative. Right? It is basically the slope in any given direction. Right? Because that might be relevant too. If I'm on a hillside, I might well be interested in which direction is the least steep, which is the easiest path to take up or down. It might not be parallel to x or y, it might be in some angled direction from those. And so the directional derivative is sort of quantifying that mathematically. So what we consider here is, so this is the xy plane underneath the surface. Right? The surface itself is above the screen of some form. But every x and y value projects up to a particular point on the surface. So I might want to know, going in, say this, here's a point, x0, y0, some given values. I might want to know in this direction, what's the slope? Now, I don't mean this slope that I draw. I mean, if I was to move up from that point to my surface and was to go in that direction, what's my slope? I could be going downhill, I could be going uphill, I don't know. Well, the answer will be a number. because the slope is still a number, but I'll need a vector to do it, yes. The vectors are going to get involved for sure. Even though the actual answer to that question, a slope is always a number in the end. It's always a rise divided by a rho.
In that case, is it a two-dimensional or three-dimensional vector?
Let me get to that. I'll get to that in a couple of minutes. So what information can I give to set up a question? Well, the obvious thing really here is that I've got a vector, and I'd like a unit vector here in part of my setup. And one obvious way I could describe it is by simply giving the angle between the vector and the x-axis. That's theta, as we've always, back in polar coordinates, that was theta. Back in then cylindrical coordinates, it was still theta, so we're quite used to that. And if you think about it, this vector will be cosine theta I plus sine theta j. Right, because the I component needs to be the adjacent, and cosine theta is adjacent over hypotenuse, but if this is a unit vector, then the hypotenuse is 1. So the adjacent distance is cosine theta. Similarly, the vertical distance will be the opposite, so sine theta. And you can see the magnitude of that is 1, right? Because magnitude will be square root of cosine squared plus sine squared. So square root of 1. So that's my unit vector giving me the direction. So this line over here, remember how we parameterized a line? X will be x0 plus t cosine theta, and y will be y0 plus t sine theta, because that was how we parameterized the line, right? You needed a point on the line, x0 and y0, and then you added t times the direction vector coefficient. The I component for x and the j component for y. So that's the parameterization of this line. Right, if you want to put it another way, you could say that r of t here is x0 plus t cosine theta I plus y0 plus t sine theta j.
So basically, we just parameterize that line.
Yes.
But is that line a unit vector?
No, that's a line, not a vector. Right. If you think back to chapter 10, in order to talk about a line, we wanted a point and a vector, a direction vector. But the line itself, I mean, a line and a vector can be kind of very closely associated with each other, right? This is a vector, but what I've got there is a line. This vector value function creates that line for me. It's a subtle distinction. It's not really that important, which one it is, because this is only part of the setup. All right. And so what we've got is what? Oh, yeah, because the line is supposed to be parallel to you. The reason I drew you was because it was parallel to the line that I'm interested in. But notice that theta is not a variable here, right? I mean, I could set up different questions with different angles, but once I've decided, once the question has said, all right, what direction are we going? What's the slope? The question's basically fixing theta for you, and so the only actual variable here is t. Right? T is the only parameter involved in this, and so I can basically think, in this direction, what is the derivative? Right. And so if we kind of think about that, let me go to another screen. So let me recap what we've got so far. So z is some function of x and y, but x is x0 plus t cosine theta, and y is y0 plus t sine theta. Now, there's a lot of unknown things here, because I'm talking very generally here. This is just a generalized setup. So theta could be anything, x0 could be anything, y0 could be anything, but they are all fixed in the question. The only thing that actually varies within the question, the only thing that is actually a variable is t. all the rest of the things. The question might say, find the directional derivative of this surface at the point 5, 2 at an angle of 40 degrees. So it's telling you x0, it's telling you y0, it's telling you theta. All of those things are given. So actually, in this case, z is basically just a function of t. We've got that chain rule setup that we've just been looking at, the first version of the chain rule. But notice that the difference here is z as a function of x and y describes the entire surface. Z as a function of t specifically describes the curve in one direction on that surface, right? So this is a surface, this is a curve. It's one of the curves on the surface. So it's like this thing is the hillside, this is a particular path on the hillside. Because you've been, you know, for this to make sense, you've definitely picked a direction already. All right. So when I write here, there is such a thing as dz dt. And this thing here is what I'm calling the directional derivative. Because that will be the derivative in that direction. In other words, the slope in the given direction. But according to my chain rule, dz dt will be partial dz dx times dx dt. Don't forget, dx dt will be a full derivative here. Plus partial dz dy times dy dt. This was the first version of the chain rule that we talked about yesterday. All right. The example I just did earlier at the start of class was the second version of the chain rule that we did yesterday. But I can put in these values now, right? So this is partial dz dx, and partial dx dt is cosine theta. Plus partial dz dy, which I won't know until the question tells me what f of xy is. That's what z is. But partial dy dt is sine theta. So that will give me the slope that I'm looking for. And what we're going to do now is to define something that we call the gradient. You'll see this on page page 922. Oh, by the way, the true notation for this, I mean, this thing that I've written here is a little misleading because it doesn't, it implies that the vector u has got involved. You know, it implies that there is a direction associated with this, but it doesn't actually feature it anywhere in the notation. So the notation that we use, you'll see this on page 920. We write this as d, capital D, with a subscript of the vector u, f of xy. That's not, that looks a bit like a y, but in the book it is a bold type. So be aware that in effect that notation is really just the derivative. It's dz dt in the given direction, but what's important about this notation is that it describes the surface and the direction that you're walking on the surface. So what you really want is the notation to both contain f of xy to tell you the surface and u to tell you the direction that you go. And this doesn't really do that. So this is just a different piece of notation to mean exactly what we're talking about here. But it tells you when you look at it exactly what it's trying to describe. But to some extent, it's yet another version of derivative notation. There's a lot of different ways to write derivative. There's y prime and dy dx, and one or two other more obscure ones. Well, this is another, but very context-based. You only tend to see this when you're talking about directional derivative. But we are now going to define something we call the gradient function. And the gradient function is a vector-valued function. then it's given that notation. Del fxy, as we call it. It's like this, an upside down triangle. Technically, one of the sides of the triangle should be slightly thicker than the others, but that's very difficult to draw. So you see it in the book, but as far as we're concerned, an upside down triangle is perfect. No, that's f of xy. And the definition of this thing is partial df dxi plus partial df dy j. Right, so it's a vector valued function. That's one of the reasons why vector valued functions have to come before this in the book, because when we start to use applications of partial derivatives, we need to know how they work. And so what we can say, and this is an important formula, is that this directional derivative is equal to the dot product of the gradient function with the vector u. Because notice the dot product, if I do the dot product here, remember u was cosine theta I plus sine theta j. So the dot product will be f of x times cosine theta, the two I components, which is exactly what this is, right? Because z is f of xy, so partial df dx and zx are the same thing. And then the j components will be f partial df dy times sine theta, and so you get exactly this result. But this is a very useful way of recording the directional derivative as a property of the gradient vector.
The first way though looks a bit simpler.
It is, but we're going to use this for other things, and so both versions are helpful. Part of the issue is the first version requires you to have u given as an angle, or for an angle theta to be given, which you then create the unit vector with. This version allows u to be given directly as a vector rather than an angle, and so you're not messing around with a calculator. So I could say to you, in fact, let me give you an example of this in use. In fact, let me give you two examples of it in use. One that uses the angle and one doesn't. So find the directional derivative. I'm just going to write dd of this function, x divided by y, at the point 2, 1. Now, you have to be not careful, but sort of think about what's going on here. It's questionable whether you should be using a two-dimensional coordinate or a three-dimensional coordinate. Because obviously if x is 2 and y is 1, then I know the z coordinate is also 2. So technically, the directional derivative, if I'm using it to find slope, then it's actually at a point on the surface, which should have a z coordinate as well. It should be 2, 1, 2. But the fact is, directional derivative, like a lot of things in calculus, is a more abstract idea. Yes, we introduced it in terms of the slope going down a surface, just like we introduced the derivative right from the start as the slope of the tangent line. But it has way more uses than just that. So you kind of want to think of the directional derivative really just in terms of x and y. Z is implied if you need it, but it doesn't have to be there. So the convention tends to be to just give x and y rather than x, y, z, because as you'll see on Thursday when we do an application, you might well use this in a situation that has nothing to do with the surface whatsoever. So finding that along the vector, or parallel to, I should say, the vector u, which is cosine pi over 4i plus sine pi over 4j. In other words, I'm telling you that the angle is pi over 4. The line, of course, isn't, that vector itself doesn't pass through the point 2, 1. So the line itself is parallel to that. You parameterize it, but we kind of parameterized it in the creation of the formula, so we're really neat. So what I would say here is that the, start with the gradient vector. So that's partial df dx, which is 1 over y, I, plus partial df dy, so minus x over y squared j. Just bear with me. just watch what we're doing here, Ash. The reason not for the first method is that this question never specifies that we're dealing with a surface and we're finding a slope. It just asks for the directional derivative. That's one application of the answer, but it's not the only application. The first method was to create the formula by thinking of one specific context. This is more general. So I can specifically put in x to be 2 and y to be 1. And so I will get 1 over 1i minus 2 over 1 squared j. And so there's my gradient vector evaluated at that particular point. U, of course, well, I can write u as square root 2 over 2i plus square root 2 over 2j. And this, to some extent, is what I was saying is you can often both, I mean, eventually in the question and often even at the start of the question, not actually have the angle in front of you at any point. There's really no reason for me to have this angle of pi over 4 involved. I could have just directly given you the vector u, and frequently we will. And so the directional derivative in the direction of u of this function at the point 2, 1 will be the dot product of those things. So it'll be the square root of 2 over 2 times 1 plus the square root of 2 over 2 times negative 2, which is minus square root 2 over 2. Now, to come back to your point, Ash, if the question was specifically interested in the surface z equals x divided by y, then what I have found is if I stood at the point 2, 1 and walked in a direction at 45 degrees to the x-axis, then I would find that I'm walking downhill at a slope of negative root 2 over 2. Well, the negative is what tells me I'm going downhill at a slope of root 2 over 2. But notice that z is nowhere on the screen. So this is more than just an application to surfaces and slope. Right. This is a generalized concept of here's a multivariable function of x and y. There is such a thing as the gradient function. And if I also specify a vector, a direction, then there's such a thing as a directional derivative as well. All right. But it doesn't only mean slope. Okay?
So you did it this way. That's an example.
This is the application. This is the thing that you keep asking about the first version imposes a context onto the question. It implies that there is a z because there is a surface because we're talking geometry. This question is not a geometric question. There is no surface involved here. There is simply a concept of a gradient function and a concept of a directional derivative. We have not yet talked about what we could use this for except for the idea of slope on a surface, but we're going to. Which is why this version is the much better one because it doesn't involve z, and it doesn't. The minute you involve z, you are basically implying that there is an x-axis, a y-axis, a z-axis, a surface in 3 dimensions. You're basically making it a geometry problem. It isn't just a geometry. This can be used in a geometry problem, but it can also be used in a lot of other problems as well. And so we're trying to divorce this from the original context by not having z involved. Make sense? Think about it when you're reading through this section. So the only other, in fact, probably the more useful. Any questions before we get rid of this? Probably the more useful way of asking the question. Maybe what will help illustrate how this is a non-geometric concept in general. So find the directional derivative of the function f of xy equals e to the power x sine 2y. At the point natural log 3 pi over 6. Parallel to u equals 2i. Sorry, parallel to a vector v equals 2i minus 3j. Okay, there are two different ideas that we've got now of R. One is gradient function, which is a vector value function. One is directional derivative, which at the end of the day is a number, because the value is a dot product. So firstly, I want the gradient function. So what's the gradient function going to be? Not quite. What? But what about doing when I find the partial derivative with respect to x? Right, because I'm treating y as a constant. But I don't need the product rule because sine y is a constant. Derivative of e to the power of x is it's just going to be that. That's the other component to be. Right. With the x, all that. So there would be 2e power x. Both are 2 1j's. Happy with that? And I then evaluate that at a given point natural log 3 pi over 6. So that's e to the power of natural log 3. 2 times pi over 6 is pi over 3. So as I'll trip down memory lane, what's e to the power natural log 3? 3. And what's sine pi over 3?
The square root of 3 over 2.
Thank you, Christian. So this is 3 times square root 3 over 2i. Plus 2 times 3 again is 6. Cosine pi over 3 is 1/2. So that's back to 3j. So there's my vector that I get when I take my gradient function and evaluate it at that point. But I also want the directional derivative at this point. So I take that vector and I dot it with, well, I dot it with 2i minus 3j. Why do I not just dot it with 2i minus 3j? I mean, the last example, I just dotted it with my unit vector, right? Why do I not just dot it with 2i minus 3j? Because it's got to be a unit vector, right? It can't just be any vector. 2i minus 3j is giving me the direction, which is the key fact. But I've got to use u, which is why I went back and changed this to v. U specifically needs to be a unit vector. So u, of course, will be v divided by its own magnitude, which in this case will be square root 13. Right, square root of 4 plus 9. So I dot it with 2 over square root 13i minus 3 over square root 13j. So my answer here will be 3 root 3 over square root 13 minus 9 over square root 13. Which, I mean, realistically, by this point, I might as well have as a decimal. But I mean, if I don't have a calculator, which I mean, I have a calculator with me, I mean, good enough. That's what it is. I mean, that's a negative number, right? 3 root 3 minus 9 will be negative over square root 13. But if I did put it in, I guess I've got one on my phone. That's negative 1.055. Now again, that number is just an abstract floating concept without any application in what I've got here. This was just, here's a function, here's a point, here's a direction, find the directional derivative. If you wanted to imagine this as a surface, and this has given me a point on the surface, and this has given me a direction to walk, then that will be the slope. But the question doesn't actually include any of that, and so it exists in isolation of that concept. Like I said, on Thursday, we'll look at examples that have nothing to do with surface, but more, looking at the direction in which a parameter changes.
Can't we then make the z a parameter of f of x and y, and then do the first one that way?
But yeah, but the minute you say z, you're implying a third dimension, and so you're implying a geometry.
Or you could just be implying a relationship.
Trust me on this one, actually. It's not going to be there because you don't use it unless you do. You could do, but you don't. That's just the convention. You can try fighting that battle with the math world, but I don't think you're going to win it. That's when you're looking at the questions, that's what you're going to see. But I say next time we'll look at other applications which might make you feel a bit better about it. All right, guys. See you on Thursday.
Negating this angle, that math problem.
All right, so this is 13.6, number 24. And it gives us a function of x, y, z equal to xy plus yz plus xz. It gives us a point, 1, 2, negative 1. And it gives us a vector v, 2i plus j minus k. And so what the question wants to know is the directional derivative of this function at that point in the direction of v. All right, now this is where the idea of a geometric application is going to fall apart a bit, because for this to be a geometric application, this will be a slope on a 4-dimensional surface, which obviously is not in any way practical. But I can still talk about the directional derivative hypothetically. This thing. So remember what you do, you find the gradient function, which is, we write as del f, which is fxi plus fyj, and in this case plus fzk. You evaluate it at the point and you dot it with the appropriate unit vector. So see if you can put all that together to get a numerical answer.
Supposed to plug it in for the point first?
Well, I'll let you think about that.
Like when we get the fill, then we plug that in for the point, and then we dot that with the.
Right, because the unit vector that you'll be dotting it with has nothing to do with the point. That's just a given expression.
Would the answer change if you dotted it and then plugged in the point?
No.
No.
The only time it would change is if you try plugging in the point before you differentiate it, because that would be really bad, because you just get zeros across the board. So what is the gradient function here?
xy plus yz plus. It would be y plus z, x plus z, y plus x.
So it's y plus zi. That's what you get when you differentiate that with respect to x. The yz term, of course, disappears because I'm treating that as constant. Plus x plus z j plus x plus yk. Happy with that? The vector value function. And so del f at the point 1, 2, negative 1 will be 2 minus 1, so 1i. X plus z is 0, j, and x plus y is 3k. And so my directional derivative at the point 1, 2, negative 1 will be that vector, I plus 3k, dot with what?
Unit vector of v.
Right, that unit vector. So I need to find the magnitude of v, which will be the square root of 4 plus 1 plus 1. And so I'm dotting this with 2 over root 6i plus 1 over root 6j minus 1 over root 6k. And so that'll be 1 times 2 over root 6 plus 0 times 1 over root 6 minus 3 over root 6. So negative 1 over root 6 or negative root 6 over 6 if I do rationalize. That's my directional derivative, right? The answer is always a number. It's a dot product. Okay?
So the directional derivative tells us the direction that line goes in?
It does in 2 dimensions. In 2 dimensions, it gives us, or one application of it would be the slope if you were walking on that surface in that direction at that point.
And what does it tell us in 3 dimensions?
Well, I mean, abstractly, it doesn't tell us anything. It's just an idea. I mean, if you could picture a 4-dimensional surface at a point on that 4-dimensional surface and you're walking in the direction of a 3-dimensional vector, if you were able to picture that, then it would give you the slope. But you can't, so it doesn't. So right now, it's just a calculation. In the same way that if I ask you to find the dot product of 2 vectors, I can't tell you automatically what that number means. There are different applications in different contexts, but abstractly, it doesn't mean anything. It's just a number. But we're about to come to an application of the gradient that shows you this in a non-surface interpretation. Because the thing to bear in mind here is there's an implication to what we've said. Right? We've said that the directional derivative, and I'm just going to switch this back to 2 dimensions for now, just for ease, is the gradient vector dotted with the unit vector in the direction that you're talking about, right? That's what we just used to calculate this. But bear in mind what the definition of the dot product is. The dot product of those 2 things is the magnitude of the first thing, so the magnitude of the gradient vector, times the magnitude of u times the cosine of the angle between them. Right? Well, what can I do? What do I know there that will help me simplify? What can I say about that statement there that helps me? What's the magnitude of u? 1, right? Because it's a unit vector. So this is the magnitude of the gradient vector times cosine theta. What's the maximum value of this directional derivative? Right, it's the magnitude of the gradient vector, right? And it occurs when theta is 0, right? Cosine theta is equal to 1. In other words, the gradient vector points in the direction of maximum increase. right? Because that's what the directional derivative is, right? It's the rate of change. It's the increase or decrease that you're experiencing. If it's a surface, then it's an increase or decrease in z, in altitude. In other words, slope, as we've talked about. But the directional derivative is basically the change in output. And so the maximum value you can get is when the vector that you're talking about, the unit vector you choose to use, points in the same direction as the gradient. So that means that the gradient vector points in the direction of maximum increase. That's the real value of the gradient vector, is it tells you what direction your quantity is increasing fastest. Or put it another way, you could also say it tells you which direction it's increasing least by going in the exact opposite direction. Because obviously the minimum value is minus the magnitude of the gradient function. And so that's the key fact here, is that the gradient function points in the direction of maximum increase. And so if you have a situation where something is seeking out the greatest increase, for example, the example we're about to get to, a heat-seeking particle. If you have a heat-seeking particle placed on a surface with varying temperature, what path is it going to take? I mean, you know that it's eventually going to head towards the hottest point on the surface, but what path is it going to take to get there? That's what the next question's about. So let me kind of show you an application where we use the gradient vector. So we're going to have a question where a surface has a temperature at a point xy, so temperature distribution given by T, and the temperature at some point xy is going to be 15 minus 3x squared minus 2y squared. And we have 3 questions that we're going to look at in this pretty much for the rest of the class period. So first question. Oh no, sorry, actually 4 questions, because the first one has sort of 2 parts to it. Find the direction of maximum increase, maximum temperature increase. If you're at the point 1, 2. And what is this increase rate? So that's the first question with 2 bits to it. Second question is, what is the hottest point on the surface? And the third one is really where we're going. The third one's the main question, which is find the path taken by a heat-seeking particle placed at that same point, 1, 2. It would, but what path will it take? Well, let's find out. Because short answer, no, it won't take it. It won't take that.
But a heat-seeking particle generally locks onto the highest temperature and then hits for it.
You'll see. Just bear with me. Actually, don't get ahead of the game. Just we'll be talking about it. It does, but it seeks out the hottest point in its immediate vicinity, not the hot. It can't know what the hottest point on the plate is. All it knows is at my particular point, which way. Right. So all it's going to do is go to the nearest point that is hotter than all the rest of its nearest points. That will not necessarily be on. You'll see. This brings also the core of the idea of geodesics and general relativity as well. Objects don't always take the shortest distance. If you remember doing the cycloid and the idea of the tortichrome problem, the surface that an object will get from point A to point B fastest when you release it, it's not a straight line, it's a slope, it's a curve rather. All right, so, well, let's answer the second question first. What is the hottest point on that surface? What's the highest value of T you can possibly get here? 15, right? When does that occur? Right, so the hottest point is the origin, because every other point is going to be 15 minus something. So it's x squared and y squared have to be positive. All right, direction and maximum increase at the point 1, 2, and what is this increase? Well, as we just said, the gradient function points in the direction of maximum increase. So what is my gradient function here? Minus 6xi minus 4yj, right? Because it's partial dt dxi plus partial dt dyj. Everyone happy with that? Right. And so at the point 1, 2, that will be minus 6i minus 8j. So that's the direction of maximum increase. What is the maximum increase? Well, that's the magnitude. So that'll be the square root of 36 plus 64, which is square root of 100. So 10. Now, we haven't established any units in this, but let's say 10 degrees C per meter or per inch or whatever unit of distance you choose to use, but it's a rate of change of temperature with respect to distance. But in this sort of abstract setup, I don't really need any units. Just the maximum increase is 10 units per unit, if you put it that way. So those are the two simple setups, but that's kind of bringing up the point that Asher was making is, let's think about this. If I'm at the point 2, 1, has everyone got all this? Can I move this screen?
How far can the particle sense then, I guess, is the question, is the radius of
It can only, that's kind of the point of calculus, right? Is it's all about microscopic increments. Like the only thing this particle can detect is in every direction, in its absolute immediate vicinity, what the temperature is, and it's going to pick the hottest one. It is exactly how a heat-seeking particle has no intelligence. It has no understanding. It can't.
No, but it has typically it has a large radius, because otherwise it would just loop in on itself, because it itself would be a hot object.
No. It doesn't have any inherent temperature. It just detects the temperature around it. But if the surface around it is hotter, then it's not going to detect itself. And you wouldn't use a heat-seeking particle that is hotter than the surface that you're putting it on. So, plus its sensor doesn't have an engine. sensor is determining the environment. All right, actually, I feel like you're just looking for a way to make this more complicated than it needs to be. It detects the surface around. If you want to think of it as a completely idealized hypothetical thing where it doesn't have any temperature, fine, it doesn't matter. All right, but we're at the point 1, 2. And we decided that the direction of maximum temperature increase was negative 6i minus 8j. I'll put it another way, if I factor 2 out of this, minus 3i minus 4j. In other words, this vector is going 3 units back and 4 units down. So 3 units back and 4 units down will take me to the point. I haven't drawn this very well. It's heading to the point negative 2, 2. And you'll notice that that does not actually pass through the origin. Right? So the direction it's heading at that moment isn't taking it towards the hottest point on the surface. But that's okay, because it's not looking for the hottest point on the surface. It's just looking in its immediate environment. What's the hottest point? And the hottest point there is in that direction. Once it moves slightly and gets to a new point, it will reevaluate all the points around it, decide which direction is the maximum increase, and then head off in that direction. So basically, its path will be a series of microscopic straight lines that together are going to form some kind of path that may or may not be a straight line. And clearly, in this case, it's not going to be a straight line, because that straight line isn't taking it to the hottest point. It's taking it in roughly the right direction, not taking it to the hottest point. So what we're going to need to do is find the actual path that it takes. All right. So how are we going to do that? Well, I'm going to need to introduce you to the most basic kind of differential equation technique to work this out. This is something that in differential equations we pretty much lead off with, but we can kind of introduce it here because it's something that you basically already know. So what we're going to do instead here is to just let the path be some unknown parameterization, right? It's going to have some function of ti plus some function of tj. I'm going to try and work out what x and y need to be. But what I do know is that r prime, remember, which is dx dt I plus dy dtj, as we talked about in the last chapter, that will always be tangent to the curve, right? Whatever your path is, remember, we talked about this in the previous chapter. If you've got some RT that's giving you some kind of path, then at any given point, R prime is always tangent to the curve. So the tangent to this path, well, that must line up with the gradient function, right? Because the particle is always pointing in the direction of maximum increase at that particular point. So R prime, in other words, the vector that is tangent to the path at any point, must be in the same direction as del t, right? The gradient function. So what we know, or what we need to be true, is that my R prime must be some multiple of del t. Right? I need those two vectors to be parallel. And vectors are parallel when one is a multiple of the other. I don't know what that multiple will be. K is just some constant. I don't know why I've underlined K. That's not supposed to be a vector. Del t is a vector. Del t is a vector valued expression. So in this case, dx dt I plus dy dtj is equal to k times del t, which if you remember in this case was minus 6i, sorry, not minus 6i, that was at the specific point, minus 6x rather, I, minus 4yj. Right, that was the gradient function at any point, because I'm starting at the point 1, 2, but I'll be very quickly moving to a different point as this heat-seeking particle searches out hotter points to move to. Which, if this is true, tells me two things. It tells me that dx dt must be minus 6kx, because the I components need to be equal. And dy dt needs to be minus 4ky, k being the same in each case. Now, this is where I need to just briefly introduce a basic idea from differential equations, because both of those things are differential equations. They're what I would call first order differential equations because it involves the first derivative, nothing higher. But a technique of solving differential equations that you always want if it works is to rearrange the expression so that all the terms involving the dependent variable on one side and all the terms involving the independent variable on the other. So in this case, I want to rearrange this so that all the x terms are on the left. So I'll divide both sides by x. And all the t terms are on the right. Now, 6k is just a constant. So that could be on either side, basically here. But it's easier to leave it on the numerator. So that's a reorganization so that my x terms, including the differential dx, are together. And the t terms, of which there is only the differential, in this case dt, are together on the other side. And basically, if those two things are equal, then their antiderivatives will be equal as well, up to a constant. So what's my integral of dx over x? Natural log x. Or what about negative 6k integrated with respect to t? Right, negative 6kt. Now, you might be thinking, why didn't I do a plus c on the left and a plus c on the right? Well, answer is I only need a constant on one side, right? If I added a constant to both sides, the point of plus c is it's any constant at all. I have no way of determining what that constant is. It's just a constant. So if I wrote plus c on the left and plus c on the right, then I'd just subtract one of those constants and end up with this. But in the same way, if this was natural log x plus 7, this was minus 6kt plus 10, well, I'd just subtract 7 from both sides, and then this would be a plus 3. But as long as I've got a constant on one side, that's all I need. Because really it represents the difference between the two constants, which is itself a constant. Yes, we're going to do that for a while. I'm going to let you do it for a while. But I haven't quite finished yet, because I want really x itself. So if natural log x is that, then x is e to the negative 6kt plus c. But of course, the rules of exponentials tells me that's e to the negative 6kt multiplied by e to the power c. And one of the points that we frequently get into in differential equations is we just need to keep things as simple as possible. This c is supposed to just represent something being constant. You need some unknown constant in your answer. Well, e to the power of a constant is a constant. Right? That's a very unnecessary way of writing a constant value. So I would just write this as c e to the negative 6kt. Right? There's no point leaving it as e to the power c, because whatever that c is, I could just pick a different c in the final version. Right? But the point is, it's not a known constant here. It's not supposed to be something that's a fixed value I just don't know. It's literally supposed to be any value of c you like. all of those, there's not one solution to a differential equation. There's an infinite number of solutions. Any multiple of e to the negative 6kt works here, as you will see if you try plugging it back into the equation. Try doing the same thing for y. See if you can work out what y is, taking the same approach there.
But now we have two different constants.
Right, now the constants, so I was going to do this after, I'm going to go back and call this C1, because I'll get a different constant when I do it for y, and I need to acknowledge that they're not the same thing. I can't use C for both of them, because the implication will be that's the same value. So second time around, we'll use C2 when we get to the end, but just do the work and see.
This typically have, problems like this typically have natural log speeds and all that.
Yes, they usually do. They don't have to. There are problems where they don't, but they're certainly not uncommon. Let's put it like that. So if dy dt is negative 4ky, then I can rewrite dy over y to be minus 4k dt. Integrate both sides. That's natural log y. This time is minus 4kt plus some constant. So y is e to the negative 4kt plus a constant, which is e to the negative 4kt multiplied by a constant. And so y I'll just call C2 e to the negative 4kt. Now, that's a parameterization of my path. I would like a direct equation of the path ideally. The question wants to know what the path is. Well, a parameterized version's fine, but notice here if I was to square both sides here, then x squared is c1 squared e to the negative 12kt, and similarly y cubed will be c2 cubed e to the negative 12kt, because if I can eliminate t and get a direct relationship, then that's my equation. And so y cubed is equal, or y cubed divided by c2 cubed is the same thing as x squared divided by c1 squared. Right, those two things are both the same thing, e to the negative 12kt. Or you can think of it as substitution, whichever you prefer. I'll put it another way, y cubed is c2 cubed divided by c1 squared as x squared. But again, that's just a very elaborate way of saying a constant, right? A constant cubed divided by another constant squared, let's just call that c3. So y squared is c3, sorry, y cubed is c3 x squared. Or if you prefer, y is c4x to the power 2/3. You could regard either one of those as. So that's the path that this will take. Now that's the path it will take wherever you put it. I'm specifically putting the particle at the point 1, 2. So I need, that's an infinite, that's a family of paths, right? There's y equals 1x to the 2/3, or 7x to the 2/3, or 29x to the 2/3. I want the one specifically that passes through the point where I'm putting the particle. So the fact that I need the point 1, 2 to be on the path implies that when y is 2, x is 1, and so C4 here must be 2. So that my particular path is y equals 2x to the power 2/3. But all of those paths will follow, all of those paths are what the particle will follow if you place it at any given point. Now you can tie this up going right back to the idea of level curves, right? Let me just kind of show you this in action now, Alex. I'm switching over to Desmos, which you won't be able to see, unfortunately, but if you email me, I can send you I'll send you a copy of what I'm doing, or you can just put it into Desmos yourself, basically. Is 15 minus 3x squared minus 2y squared equals some constant. So these are level curves, right? If you pick C, then you're basically picking a curve on which all the points have a constant temperature. So let me just change my data here. I want let's have C go from 0 to 5. So C equals 0. Those are all the points. I guess I should let this go all the way to 15 to be logical. So if I go all the way to 15, of course, I shrink down to the origin because that's the point where the temperature is 15. But if I want to know where my temperature is 11 or 7 or whatever, they're the level curves, right? Here are the different paths I can take. The thing to notice, though, is notice it doesn't matter what level curve I choose and what path I choose. That path always intersects the level curve at 90 degrees. Because the level curve is a curve of constant temperature, right? So if your particle was to go along the level curve, it's seeking out the exact same temperature. It's not seeking out an increase or decrease in temperature. It kind of feels logical that the direction the particle should go is 90 degrees to the level curve, because the level curve represents the temperature staying the same, and the particle's looking for the temperature to change as much as possible. So 90 degrees kind of makes sense for that. And basically your gradient vector will always point normal to your level curves, because that's what they do. Level curves talk about a quantity remaining constant, and gradient vectors seek out the maximum direction of increase. And so, and I could put in here, like say, if I leave my path the same, obviously I've got two paths depending on which side I actually put the particle. So let's just focus on the right side here. But if I could leave my path the same and change my ellipse, notice it doesn't matter, it stays, it's always 90 degrees, right? Those two, the intersection is always 90 degrees. Or I could leave my ellipse the same and change the path. The path is always going to stay 90 degrees. So basically, your level curves and your gradient vector are closely tied together in that they are always normal to each other. And so this kind of goes back to what you were asking, Asher. Let's find the version where this is the one that contains the 0.12. So all the different level curves, right? It doesn't quite go in a straight line. Notice at the 0.12, at the 0.12 here, the vector is heading down here. Right, that's what we had at the start. Because right here, the direction of maximum increase is this way. But as soon as it moves a bit, now the direction of maximum increase is this way. And then it'll move a bit, now it's this way. So it's constantly adjusting its path until it eventually takes it to the origin. But it doesn't go in a straight line because that's not the path that the temperature increases at its maximum. So it's going to take a curve because all the particles seeking out is in its absolute instantaneous vicinity, what's the hottest point? And eventually it'll make its way to the origin, but not necessarily, in fact, very rarely on a straight line. Right, it's possible to go in a straight line, but chances are not. What situation, given everything I've just said, what situation would mean that it goes in a straight line? What would that mean about the level curves? What kind of level curve will create a straight line to the origin for the path? Circle, right? If it was a circle, then, you know, normal to the tangent of a circle is the radius. So you would follow the radius straight to the middle. But anything other than a circle, any kind of ellipse like we've got here or whatever, it's not going to do that. Right? So there are some questions in the homework that give you that idea. Some abstractly, and then some that are actual word problems. The heat-seeking ones, there's only actually 2 of those, 59 and 60, so definitely do those. 57 and 58 are very similar, but 59 and 60 are exactly what we've just done with different numbers. That's the kind of thing I'm going to ask you on a test. So, I mean, do the other questions building up to it. There's plenty of questions about the gradient and the properties of the gradient, but make sure you definitely do 59 and 60. If you're not sure about 60 because there's no solution, then you can ask me. Okay. So no class tomorrow. Enjoy your full break. See you on Thursday. Any questions, Alex?
No, sir.
I can send you some screenshots from Desmos to replicate what we just did if you want to see, or you know, work it out yourself.
I think I might be okay.
Hi guys.
All right, have a good one.
So on our kind of journey to redo the Calc 1 procedures, but scaled up to 3 dimensions instead of 2, we're kind of reached a point where in Calc 1, you were given some function of x that represented a curve. And your job was to find the equation of a tangent line to that curve at a given point. All right. Basically trying to find the straight line that best represented the curve's behavior at that point. Well, the Calc 3 equivalent of that is for you to be given a multivariable function, which we now know represents a 2-dimensional surface. I don't know if I'll get a good diagram off. Two-dimensional surface and be given a point. And now there's no sense in which there's a tangent line there. there is instead a tangent plane. Right, now our job is to find the flat two-dimensional plane that best reflects the surface's behavior at that point, if you like. So now we're kind of looking for some plane that kind of best fits what's going on. So, you know, if I kind of had this as my surface and I pick this point here, well, then the plane will be the one that kind of shears along it, right? I mean, it's one of those things that is a very easy kind of intuitive feel for the concept. Whether the math is easy is a different story, but conceptually what you're being asked for is a fairly straightforward idea. Ash. 7. And so that's going to be the aim of this. Okay. The way we're going to create the theory is basically to say, well, let's think about all the different curves that could be on that surface passing through the point. So basically, if I think about, say, this curve that is kind of following the surface, well, this curve will have a tangent line, right? Once you've got a curve, you've got a tangent line. And if I then pick a different path along the surface also going through that point, well, this curve has its own tangent line. And basically all the different curves that you could draw all have their own tangent lines, and collectively they will create the tangent plane. So the tangent plane is basically a collection of all the tangent lines, but there's an infinite number of them, because there's an infinite number of paths along that surface passing through that point. Right, again, if you want to think of like this as a mountainside, pick a point on the mountainside, there's lots of different paths that all cross through that same point, and each one would have its own tangent line at that point. And the tangent plane is all those tangent lines collected together, basically. Yes.
So are we going to try and use traces to get?
No, we don't need to use traces. We can use it comes straight after the gradient because we can use the gradient. So what we're going to do is let's put this in. So let's consider a surface where z is some function of x and y, but you know, when I write that, some of the surfaces we've done actually you don't write z as the object. Sometimes we've done surfaces where you've written a combination of x squared and y squared and z squared, for example. So, you know, I should put that in quotes in the sense of it doesn't have to be explicitly z as a function of x and y. It could just be some overall expression that relates x, y, z. So really what we want is to rewrite this as a 3-variable function f of x, y, z equal to 0. It could be equal to any constant, to be honest, but equals 0 is sort of the easy one to kind of write out. So, for example, you know, if I did go back to some of my surfaces in chapter 10 that we did, sorry, chapter 11 rather, not chapter 10, in 11.6. So, for example, a hyperbolic paraboloid, you could have something like z equals x squared over 3 minus y squared over 7. Well, I could just rewrite that as x squared over 3 minus y squared over 7 minus z equals 0. And so any equation can be rewritten so you've got a function of x, y, and z equal to 0. Well, I say equal to any constant will actually work, but we just write 0 as our sort of easiest approach. And then we'll consider a path on the surface well, this is going to be one of our vector valued functions. All paths in 3 dimensions, remember, we write in terms of vector valued functions. So that'll be some function of ti plus some function of tj plus some function of tk. So on the path, well, on the path, I know that x, y, and z are given functions of t, but since the path is on the surface, I also know that this combination holds as well. So on the path, this isn't just f of x, y, z. Each one of those is a function of t. So notice I'm back where I was at the start of the first chain rule that we did. When we talked about the chain rules, we had 2 possibilities. The first one was that we have a function of x and y, or in this case x, y, and z, where those things themselves only depended on one variable. Right? So actually, in this case, there is only one independent variable. If you pick t, this will tell you what x, y, and z are, because they're all functions of t, and then the top line will tell you the combination of those things that's equal to 0. Yeah, I mean, ultimately, big F is just a function of t. Yeah. And so we can use the chain rule. So if we apply the chain rule here, that tells me that if I differentiate this, and this is where if it was any constant, it's still valid because I'm differentiating. So regardless of whether this uppercase F is equal to 0 or 7 or 2 or whatever, when I differentiate it, I'll get 0. So the chain rule tells me to differentiate F with respect to x and then multiply by dx dt. Then differentiate with respect, partial derivative with respect to y times dy dt. Partial derivative with respect to z dz dt, and that will be equal to 0 because any constant differentiates to 0. But here's the key point, is that that left side, of course, is actually the same thing as the dot product of fxi plus fyj plus fzk dotted with dx dt I plus dy dt j plus dz dt k, right? Because that's how dot products work, right? If I do the dot product of those 2 vectors, I multiply the I components to get f sub x dx dt. I multiply the y components to get f sub y dy dt, etc., and then I add them all together. But the first thing is the gradient, right? That's the definition of the gradient function. Right, back in section 6, if you look back to page, I know it's only last week, but it always seems a long time ago after fall break. But the gradient function defined on page 922, back then we were just using the gradient of a function of 2 variables, but now we've got a function of 3 variables, but same concept. So this thing here is the gradient of f of x, y, z. This thing here, of course, is r prime. Well, the derivative of r with respect to t. Right? Which is what I get when I take this line here and differentiate everything through with respect to t. So what this is telling me is that by definition, for any curve, this is just any generic curve on the surface. For any curve at all, the gradient function dotted with dr dt is 0. But of course, dr dt, remember, is the direction of the tangent vector. If you remember, the tangent vector, unit tangent vector was r prime divided by its own magnitude. So dr dt points in the direction of the tangent vector. So what we're saying is that for any curve you like on this surface, the tangent vector to that curve at this point is orthogonal to the gradient vector, because the dot product is 0. And when dot product is 0, it means both two vectors are at 90 degrees to each other. And so any curve you like, you've got a tangent vector and a normal vector and a gradient vector that are normal to each other. But remember, the tangent plane is all of these tangent vectors. So basically what this is telling us is that this thing here, the gradient vector, is normal to the tangent plane. But if you want a plane, remember, what do you need to write down the equation of a plane? Point a vector, which vector? The normal vector, right? So question is going to give us a point, because it's got to tell us which point on the surface we're interested in, and the gradient function will tell us the normal vector. So it gives us the two things we need to write down the equation of the tangent plane. So actually this ends up being a really pretty straightforward idea. So I'll show you an example of how you will do this. But this is among the easier of the sections and the questions that you're going to get here. So an example of find the tangent plane to the surface 4z equals 5x squared plus 2y squared at the point 227. Now, about 4z equals 5x squared plus 2y squared will be one of those elliptic paraboloids. It's like a bowl. And so I'm trying to find at the point 227 there'll be a tangent plane to that surface at that point, and I want the equation of it. Well, I can rewrite this as 5x squared plus 2y squared minus 4z equals 0. Which means that this is my f of x, y, z. You got?
Now we can do the del operator.
Right. So what will del f be?
Oh wait, no, because they're plus 4y minus 4.
Right. The gradient vector, gradient operator is a vector, gives you a vector quantity. But I specifically want to know what that is at the point 227. So that will be 20i plus 8j minus 4k. And that's my normal vector. So what is the equation of the plane with that normal vector? How do you write down the equation of a plane once you've got the normal vector? Either, because you haven't worked out D yet. So this will be 20x plus 8y minus 4z is something, D. Of course, I've got a common factor of 4 there, but I can either take care of it now or I can take care of it afterwards. How am I going to work out D? Right, I know this plane has to contain the point 227 because that's the point on the surface that I'm finding the tangent plane to. So if I plug in 227, then 40 plus 16 minus 28 is D. So that's what, 28. And so the equation of my tangent plane finally is 20x plus 8y minus 4z equals 28, which by rights I should simplify down to 5x plus 2y minus z equals 7. So that's the equation of my tangent plane. Now, it's not like on my diagram I can see whether that makes sense or not. It's not like I can visually judge. You know, tangent lines back in Calc 1 were quite handy in that you could make a quick sketch and see if your answer looked right. See if the slope looked right, see if the y-intercept looked right. You can't do that here. You're just going to have to accept. It does, however, at least make sense. You know, I can at least justify that this makes sense as my normal vector, right? Because my normal vector here, coming out at this point, it's certainly, if I can visualize the normal vector, it's going in the positive x direction and the positive y direction, but the negative z direction is going down. So the fact that it's positive, positive, negative at least has some, you know, that gives me some faith that this makes sense. In fact, notice that the gradient vector has a minus 4k. Right? It's got nothing to do, it has no variable involved. The k component is always minus 4. And if you think about that surface, any point on it at all, the normal vector is pointing down. Right? There's no place on that surface where the normal vector can be pointing up. So that kind of makes sense too. All right. Of course, if you're at the origin, it's pointing straight down. But everywhere else, it has an x and a y component too. So that's the process for finding the tangent plane. But notice, I mean, the math here was gradient vector, which is just, you know, partial derivatives. Sub in the values. That gives you the normal vector. Write down the equation of the plane. Sub in your point. I mean, every math here, there's some calculus, but it's easy calculus and then some easy algebra as well. You can even, of course, be asked, you'll notice if you look at the title of the section, it's tangent planes and normal lines. Because as well as having a tangent plane here, there is also a line that comes straight out. A normal line to this surface. But again, you already know everything you need to know, right? What do you need to know? The equation of a line, a point on the line, and a vector parallel to it, i.e. point, 227, vector, the normal vector is the vector that you're pointing in the direction of. So n would also be the u as we called it back in chapter 11. So if you wanted the normal line here, we said that n was 28, negative 4. So this is one where I probably would, because with the u vector, all that really matters is the ratios, right? Just the proportion. So 5, 2, negative 1 would make life simpler. As long as it's in a 5, 2, negative 1 ratio, then that's pointing in the right direction. And so what's the parametric equations of the line, remember, would be 0.227, so I've got 2 plus 5t, y would be 2 plus 2t, and z would be 7 minus t. That would be the parametric equations of the normal line. That's what we would have done back in chapter 11. Back in chapter 11, we gave parametric equations of a line. Now, I've combined that into a vector valued function, so I would write it as 2 plus 5ti plus 2 plus 2tj plus 7 minus tk. So there is the normal line to that. Okay. So that's basically what you're being asked to do in this section. You're given a surface, you're given a point, and you're asked to find sometimes the tangent plane, sometimes the normal line, sometimes both. Any questions on that? Let me give you one to try. So 17 to 26 of this ask you for the equation of a tangent plane and a normal line. So let's look at let's have a look at question 26. So I've got y natural log of xz squared is equal to 2. And the point they're giving is e2, 1. Obviously, the point has to fit the equation. So notice if x is e and z is 1, then this is the natural log of e, which is 1. So 2 times 1 is 2. So you can see that fits the point given. So this basically is my f of x, y, z. Like I say, it doesn't matter, it doesn't have to be equal to 0, it just has to be equal to a constant. Because you need something that when you differentiate it using the chain rule on the left side, the right side is 0. So see if you can work out the gradient function. See if you write down what del f is. Then specifically work out the gradient function at that point. And then that will be your normal vector for the tangent plane and your parallel vector for the normal line. See if you can do that. Both. Well, let's just check that you get the derivative right, because obviously that's pretty key. Don't forget here, whenever you're differentiating logarithms, it's generally helpful to kind of use the properties of logarithms to split it up rather than trying to do the whole thing in one. So you might be better here taking the log of x z squared, so with the natural log of x plus the natural log of z squared, which of course is the natural log of x plus 2 natural log z, right? That's how logarithms work. That's generally an easier thing to differentiate. So with that in mind, what is the derivative with respect to x of this thing? So I should have, I guess we want y here, so y is multiplying this whole thing. So if I differentiate this with respect to x, what do I get? Treating y and z as constants, differentiate that with respect to x. What's the result? No, because the 2 ln z I'm treating as a constant, right? But if I distribute here, this is y natural log x plus 2y natural log z. Right, that's the function that I'm dealing with. What do I get if I differentiate that with respect to x?
Y over x?
Y divided by x, right? Y is a constant. Natural log x differentiates to 1 over x. The 2y natural log z term just disappears because that whole thing is treated as a constant. So that's the I component. What about if I differentiate with respect to y? Right, I mean, I could leave it, in this case, I could leave it as just the ln x z squared in the original, because here this is now y times a constant. So if I differentiate with respect to y, I just get the constant. Or I could have left it in the expanded form as I put in the green. Either way is fine here. What about if I differentiate that with respect to z? 2y divided by z. Okay. And so at the point e2, 1, what will I get? Well, I'll get 2 divided by ei plus the natural log of e times 1 j plus 2y divided by z is 4 divided by 1k. In other words, 2 over ei plus j plus 4k. Well, it's a bit of a mess because of 2 divided by e. There's nothing much I can do about that, but that's what it is. So that's my normal vector in this case. Or when it comes to the line, it's the vector that back in chapter 11 we called u to give the direction component for the normal line. All right. So let's put this together. The plane will be 2 over ex plus 1y plus 4z equals a constant. But I know this plane needs to contain the point E21. So when I plug that in, if x is e, 2 over e times e is 2, plus y is 2, plus 4z is 4, so d is 8. So the equation of my tangent plane is 2 over ex plus y plus 4z equals 8. Right. Meanwhile, the normal line well, the x component will be the point where I am, so e plus the I component of n, so 2 over e times t I. For the j component, it will be 2 plus 1 times t. And for the k component, it will be 1 plus 4 times t. So that's my normal line here. Obviously, this e is making things a little messier than some of the other problems where you'll just have constant, or you'll have a rational, even integer coefficients. But so be it. I mean, e is just still a number. It's fine.
For the Bell operator, I get that you spread it out so that would be easier. But what if
you didn't? It's still fine. So if I differentiate this with respect to x, right, I'll have y, and the derivative with respect to x, the derivative of natural logarithm is u prime over u. So if I differentiate this with respect to x, I'll get z squared divided by x z squared. So the z squared will cancel, that will leave the x. And if I differentiate with respect to z, I'd get 2xz divided by xz squared. X cancel, one of the z's cancel, there's my 2 over. So it still works, but you have to think a bit more about it in that sense than if you expand. But if you're way back in Cal 1, we did logarithmic differentiation. It's like a long time ago. We haven't really touched it much since. But logarithmic differentiation primarily was a way to differentiate an extremely complex expression piece by piece. But it was built on the idea that you can take logarithms and divide them up into smaller, more manageable chunks, all added or subtracted. And that's always an option. But in this case, that's 50-50. I don't know that you're making it much easier, but nor is it taking too long. So whichever you prefer. Most of these don't have logarithms, so not a big deal. So that's basically what's going on this whole when you go through. The other thing you'll see, example 5 kind of illustrates this. So bear in mind, saying here is back in Cal 1, given a curve, you have to find a tangent line. Cal 3, you're given a surface and have to find a tangent plane. But you can kind of mix those things together. If you have 2 surfaces, and we've already looked at this, there was a question in the last test. If you have 2 surfaces, their intersection is a curve, right? Back out one, you have two curves intersect the point. You intersect two, you take a dimension. So if you've a curve and two curves intersect the point, two surfaces intersect in a curve. For example, let's imagine got you've got some, I suppose, some kind of dimensional ellipsoid, and you've got some kind of elliptic paraboloid as well. They will intersect in some kind of right intersection of those things where they will be itself curving 3 dimensions, curve on both those surfaces at the same time. Right. Point of this curve actually has a legitimate tangent line. So you can still take the idea of surfaces and eventually finish with a question asking you about a tangent line as well as a tangent plane. The point being, of course, that if this point is on both surfaces, it's on both the ellipsoid but on the elliptic paraboloid as well, then both of these surfaces will have a tangent plane, right, at this point, right? The ellipsoid has a tangent plane, the elliptic paraboloid has a tangent plane. Two tangent planes cross in a line, right? If you take two tangent planes, their intersection will be a tangent line, right? And so you could be asked that. That's the other question that's coming is, here are two surfaces that are intersecting each other. Find the tangent line to the curve of intersection at this point. Well, let's think logically about what's going on. If this is my tangent line, well, my ellipsoid has a tangent plane with a normal vector, and my elliptic paraboloid has a tangent plane with a normal vector. What can you tell me about the tangent line to do with these two normal vectors? Perpendicular to both, right? How do you find something that is perpendicular to two different vectors? Oh, the dot product, cross product, right? We said when we introduced the cross product, we said one of the properties of the cross product is the result is perpendicular to both vectors that you started off with. So basically the process is going to be, all right, I want to find a tangent line to this curve intersection. I'm going to find the normal vector to the first surface here, which I would have done if I was finding the tangent plane anyway. I'm going to find the normal vector to the second surface, and the cross product of those two things will give me the direction I'm looking for my line. Right? But I think we'll do that tomorrow. I don't know. I don't want to rush through this. But when you're doing the homework, if you read through example 5, it will show you that in action. And again, it's pretty straightforward. You're finding the normal vectors. Every question here, you'll find the normal vector, right? Gradient vector is normal vector. And then you do something with the normal vector. And in these problems, you take the cross product of two and interpret the result. And so page 935 and 936 shows you that, and an associated concept of angle of inclination of a plane, which again, if you read through, it's very clearly presented. But tomorrow I'll start by doing an example of those before moving on to section 8. But I don't think you'll have any trouble with this, but in the homework, 7 to 16 are just finding tangent planes. 17 to 26 are tangent planes and normal lines. 27 to 32 are what I've just mentioned. So you might want to, you could try those, or you could wait till the weekend, whichever you prefer. Same for 33 to 36 as well. But certainly everything through 26 you should be able to do for tonight's homework. All right. Oh, sorry, and that's just completely right. We're going to be online tomorrow. Right, so don't come to class. I will On Blackboard Collaborate. I'm just trying to think if I can do it live or if I have to post a recording. I will email you. I might be able to do it live. This is all. We are having some childcare issues that have just fallen apart. Very short notice on us this week. So I'll email you. It might be live, or it might be. Either way, I'll record it. So even if you can't do it live, the only thing is you can't ask a question, I guess, on the chat. But beyond that, you can just watch the recording later. So. Oh, did I not give you yours back? I remember that I was having some issues with your take home. I thought I'd sent you that. Let me check that. I'll send it to you. For some reason, I did. I've never had anyone submit it through Blackboard before, and I couldn't.
Thank you.
I didn't know where to turn it in.
No, that's fine. I mean, normally just email it to me directly. What you did is fine. It just what I was using for everyone else's wouldn't open that properly, so I wasn't able to do it. But I know where it is now. So I thought I'd done it, but I might have. Every class I've had did a test last week, so I've kind of lost track of what I've done with each one. So I'm afraid I might have let that slip through the cracks, but I'll get it back to you. I don't put them online. I just keep them in my own grade book, but I send you the grade. So if you haven't got it, then I definitely haven't done it yet. So I'll do it. I'm sorry about that. Oh, Christian, I've seen you just come back in. I just mentioned to everyone else, tomorrow's class will be online, possibly live or possibly recording. I will email, but definitely not in the classroom. So, is that all right? Okay, guys. Sorry for the issues with today's class and this having to be a recording. If you do have any questions, you can email me or just ask me on Monday. But remember from yesterday, we were saying that the gradient vector to a surface at a point will also be the normal vector to the tangent plane. And so that's kind of our way into finding the equation of a tangent plane to a surface, which is the new version of finding a tangent line to a curve. And I finished by pointing out that if two surfaces intersect and form a curve of intersection, back in Calc 1, two lines intersected at a point, well, two surfaces in Calc 3 intersect in a curve. And that curve at a point will have a tangent line. Now, to find that line, we can make use of the fact that it will be perpendicular to both the normal vectors of the two tangent planes at that point. So let's imagine we have the following two surfaces. We've got a sphere. The equation of the sphere is x minus 2 squared plus y squared plus z plus 5 squared equals 22, but I'll write it as minus 22 equals 0 because we've been generally writing the function equal to 0, but it doesn't really matter because you're going to differentiate that constant anyway. And then we've got an elliptic paraboloid. And the equation of this is x squared plus y squared minus z minus 27 equals 0. So one of these is a sphere centered at the point 2, 0, negative 5 with a radius of square root 22, and one is an elliptic paraboloid, one of these bowls that opens up. But they'll intersect at a point. They'll intersect at a curve, and one of the points on that curve will be the point 4, 3, negative 2, because that fits both of the equations, right? If you sub those two values, that fits both the equations. Therefore, it is one of the points of intersection. There will be a whole curve of points of intersection. But the question is, at the curve of intersection at that point, what is the tangent line? Well, the way we can find it is if we consider this function here. Oops, sorry, not this bit at the end, not the equals 0. This can be uppercase f of x, y, z. And this function here can be uppercase g of x, y, z. Then I can find the gradient function for both of those. So del f will be 2 times x minus 2i plus 2yj plus 2 times z plus 5k. Right, the minus 22 disappears because whatever you're differentiating with respect to, that's already a constant. And so del f at the point 43 negative will be 2 times 2, so 4i plus 2y, so 6j, and 2 times z plus 5, which will be 6k. Okay. Which in terms of you know, a normal vector, all we really need is the direction, so the reduced or calculation a little easier. So you could use that, but if you wanted to factor out the 2 for the cross product, that will keep life a little simpler. Gradient function for g will be 2xi plus 2yj minus k. And so at the point 43 negative 2, the gradient vector here, in other words, the normal vector to the surface g at that point will be 8i plus 6j minus k. Right? Don't be tempted to put in the negative 2. That's not how that's going to work. Okay. So that's going to be my normal vectors. And so the tangent line, well, the direction vector for the tangent line will be perpendicular to both of those. So what I need to do is find the cross product of those two things. And so I need to go ahead and do that. Just give me a second. And so if I work that out, that'll be ijk. My first vector, I can use the 2, 3, 3. So I could use 4, 6, 6, that's fine, but I might as well use the reduced form, and 8, 6, negative 1. And so if I work that out as a cross product, I will be minus 3, minus 18, so negative 21. J will be minus 2, minus 24, so negative 26, but of course I would make that I change the sign on J. And for K, it'll be 12 minus 24, so negative 12. And so that's the direction vector for my line. The line, of course, contains the point 4, 3, negative 2. And so I can use my parametric equation idea to get the vector value function for the line. So that'll be 4 minus 21 ti plus 3 plus 26 t j minus 2 minus 12t, which I can factor that negative out, so 2 plus 12t. Okay, and so that will be the tangent line to the curve of intersection at that point. The book also just points out that you can use the same idea to find, if you do have a tangent plane, one thing we're interested in a tangent plane is it's the angle that it makes with the XY plane. And so what we'll have is this, we've got y plane, and then I've got some kind of plane at some angle with some normal vector n. Well, obviously the normal vector to the xy plane is k. Go straight up out here. So in effect, what I want to know is what is the angle between these two things, right? That's what I'm really interested in here. The angle between the two planes is the same as the angle between the normal vectors to the planes. And if you remember, the cosine of an angle between two vectors in general is the dot product divided by their magnitudes. That's sort of the general formula for angle between two vectors, which in this case, one of the vectors will be the normal vector to whatever plane we're talking about that we'll have worked out. The other is just k, divided by the magnitude of n, and times the magnitude of k, but of course k is a unit vector, so that just has a magnitude of 1. So this formula that you will see on page, where's it gone? Page 935 will be the angle between those two things. In fact, you'll see they stick an absolute value sign because you might as well take the smallest angle you can take. N can point in two different ways, and so either angle makes sense, but the one between 0 and 90, the quadrant 1 angle, really is kind of the one that makes the most sense. So there are some questions that involve that as well. All right, let's move on to section 8. That just finished up section 7. But if we move on to section 8, quick recap, as we keep doing, back to Calc 1, the idea of critical numbers and relative maximum, relative minimum points. But back in Calc 1, if you had I'm going to redraw that. I don't like the way that's come out. So back in Calc 1, let's make this bigger. If you had some curve, y equals f of x, then our relative maximum or minimum points were our relative extrema, places where the well, this one's a bit questionable. We'll come back to that. Places where the graph either had a horizontal tangent line or it had no tangent line. I didn't mean to draw it in as if it was a tangent line there. Just that point. There's a relative minimum, but there's no tangent line because the function's not differentiable there. There's a sharp turn or a cusp in the graph. And so what we kind of fixed in Calc 1 was the idea of critical numbers. Oops, well, that's gone yellow. Critical numbers. And critical numbers were either where f prime of x was equal to 0 or f prime of x was undefined. Right? The critical numbers were a combination of any place where one of those two things was true. And relative extrema, relative maximum, relative minimum points could only occur at critical numbers. Critical numbers didn't guarantee a relative maximum or minimum. They could equally have been points of inflection, but you would never find one anywhere except for a critical number. And the way we tested these things was the second derivative test, which basically said if f double prime of x at a critical number is positive, then that was basically telling us that the graph was concave up, and so that was a relative minimum. If f double prime of x was negative, then it was concave down, and we had a relative maximum. And if f double prime of x was equal to 0, the test failed. And you knew nothing about whether that was a maximum or minimum point, or maybe not either of them, maybe a point of inflection. So that was the kind of Calc 1 overview of extrema. There was also stuff like the extreme value theorem, the fact that if you're actually looking at this on a closed interval, then there will be an absolute maximum and an absolute minimum if the function was continuous, but for the most part, this was the general thing. Well, we're going to have a very similar idea in Calc 3, but this time for surfaces to have a relative maximum or relative minimum point. This time there are no tangent lines anymore, there are tangent planes. And if a surface is going to have a relative minimum, let's give me a second. Let's say there we've got some surface. If a surface is going to have a relative minimum, then basically that's going to happen when its tangent plane is horizontal. Right? In other words, the tangent plane has a unit vector of k. And so remember, if this is the surface z equals f of xy, then that's basically saying f of xy minus z equals 0. And so we need, if this is uppercase, we need f sub x to be 0 and f sub y to be 0. Because only the k part can be part of the normal vector, or it wouldn't be a horizontal tangent line. So critical numbers now occur when both partial df dx equals 0 and partial df dy equals 0. All right, they both have to be 0 or undefined. It's not enough for one of them to be 0, they both need to be 0, or if either of them is undefined, that could be a critical number as well. They don't both need to be undefined. If one's undefined, then we would count it as a critical number. And again, like last time, critical numbers are the places where you might get a relative maximum, you might get a relative minimum, but it's not a guarantee, just like before. And so that's what section 8 is basically detailing. So for example, let's take this function. And again, don't forget, extrema and critical numbers are not purely a property of geometric shapes. So whilst we might set this up with surfaces and z and horizontal tangent planes, critical numbers exist outside of that. There doesn't need to be a z involved, there doesn't need to be a surface involved, there doesn't need to be any geometry involved. A function abstractly has or can have critical points. So let's imagine I had x squared minus y squared minus 2x plus 6y plus 5 as a function, right? I could make that into a surface, but I don't have to. So partial df dx here will be 2x minus 2, and partial df dy will be minus 2y plus 6. And so my critical point, I write critical numbers before, I really should talk about critical point here, because these things always come as a pair, right? There's an x value and a y value for critical point. Well, the only possibility for partial df dx is it's 0, can't be undefined, and that'll happen when x is 1. partial df dy will be 0 when y is 3 and can't otherwise be non-existent. So I've got the one critical point here when x is 1 and y is 3. If I was treating this as a surface, give me one. So if I was to consider this as a surface, then that is the only point that I might find a relative maximum with the horizontal tangent plane, or relative minimum with the horizontal tangent plane, or possibly some weird thing happening, some strange discontinuity or non-differentiable, or it may be none of those things. But that's the only place I could find it. There couldn't possibly be a relative minimum anywhere except the 0.13. Right, so that's the only place I need to go looking. But the question becomes, well, how do I know? And again, how can I take this away from purely the arena of geometry and make this a more abstract thing? What do we have that will test whether this thing is a maximum or a minimum or neither of those two things? Do we have something equivalent to the second derivative test? Basically is the question, and the answer, as you might expect, is yes, but it's more complicated. It's what we call the second partials test. And you will find it on page 943, and there's considerably more going on in the second partials test than there was in just the straight second derivative test of Calc 1. So for the second partials test, you need to consider a few things. And if you look at page 943, you'll be able to kind of follow along with this. You'll also see on the diagram how they show you that saddle shape that we looked at as one of the shapes from chapter 11. If you do have a surface as a saddle, kind of where you sit on a saddle has a horizontal tangent plane. It's flat at that point, but it's neither a maximum nor a minimum point because the saddle goes up in some directions and down in the other. So there's an example of how you might have a horizontal tangent plane, but not a relative maximum or minimum. So for the second partials test, well, we already know that fx and fy need to be 0. I wouldn't be testing this at all if it wasn't a critical point. But then I go further and I test something that we call d. And the quantity d is the second partial derivative with respect to x multiplied by the second partial derivative with respect to y minus the mixed partial term squared. Right? Why it is, we're not going to get bogged down on it. It's quite a complicated derivation. You just basically just accept this as something that gives you the result you're looking for. So that quantity tested at your critical point do one of three things. All right, I can have d can be positive. But if d is positive, then actually it matters whether the second derivative purely with respect to x is positive or negative. So actually I'm going to consider two different cases where d is positive. One where this fxx term is also positive, one where it's negative. If that's the case, then this is going to be a relative minimum. And case 2 will give me a relative maximum. Notice in terms of just these terms, that's basically very like the second derivative test of Calc 1. If the second derivative is positive, relative minimum, second derivative negative, relative maximum. But there is a precondition that d must be positive as well. If d is negative, then it's irrelevant what that expression is. You will get what we call a saddle point, what I just talked about. Now we call it a saddle point because on a saddle shape on a surface, it's a point with a horizontal tangent line, horizontal tangent plane rather, but it isn't a maximum and it isn't a minimum. But the phrase saddle point kind of transcends to just be the result of any analysis here. But a saddle point is neither a relative maximum, nor is it a relative minimum. It is the three-dimensional surface equivalent of a point of inflection. But we don't call it that because it doesn't quite make sense to call it that. It doesn't quite do the same thing as a point of inflection does. The fourth option, of course, is that D is 0, and just like before, that means the test fails. And so you're going to run that analysis every time. Now, you might be wondering why here, why was it fxx that we looked at? What's so special about that instead of fyy? Notice they're actually interchangeable. Because for D to be positive, if you look at D over here, here I'm subtracting something that's definitely positive. I'm subtracting something squared. So the only way that D can be positive is if this first term is positive as well. In fact, more positive, it has to be bigger, right? And the only way though that product can be positive is if they're both positive or they're both negative. And so they're kind of interchangeable. To say that fxx has to be greater than 0 is functionally the same as saying fyy has to be 0. If they didn't both do the same thing, then D couldn't be positive in the first place. So it's fxx just for ease of writing. But if you really feel strongly that fyy deserves its kind of moment of glory, then you can use fyy instead. It's the same rules, same conditions. And so in this example here, which is a fairly easy one, fxx, of course, is just 2. fyy is -2, and fxy is 0. All right. And so D in this case, actually, it doesn't matter what the critical point is, right? These things have nothing to do with X or Y, they're just fixed in place. So D here is 2 minus 0 squared, so -4. So in this case, this is actually a saddle. In fact, this whole shape is a saddle shape. If you look back on, what was it, back in chapter 11.6, when we did this, back on page 801, you'd see that this is, we call it a hyperbolic paraboloid, but it's a saddle shape and it has no relative maximum, no relative minimum points at all. Okay, but that's basically what you do on these problems. When you're given a function, you find the critical points, if any, and then you test those critical points using the second partials test. So let me give you another example. Let's say fxy here is e to the power xy plus 2x minus y. All right, so we're going to need to list our first and second partials. So partial df dx, well, of course, it will always be this same function using the chain rule times the derivative with respect to x, which is y plus 2. Fy will be that function times the derivative of the numerator with respect to y, which will be x minus 1. Fxx will basically be the same thing again, so it'll be y plus 2 squared, because the y plus 2, of course, you're treating as a constant here, so that's a constant multiple. And fyy will be x minus 1 squared to the xy plus 2x minus y. The mixed partial, though, of course, whichever one I do, I'm going to need the product rule as well. If I differentiate partial df dx up here with respect to y, well, I've got the product of two functions both involving y, so I need the product. So the derivative of y plus 2 is 1 times the function plus y plus 2 times the derivative of that with respect to y, which will be x minus 1 to the xy plus 2x minus y. So my critical point here, well, don't forget the exponential function can never be 0. So the only way that fx can't be undefined, right? There can't be any value of x or y that make that not exist. So y needs to be -2 and x needs to be +1. So 1, -2 is my critical point here, and it's the only critical point. But I then need to test it, and so fxx at this point, 1, -2, will be 0, because when y is -2, doesn't matter what the exponential is, right? When y is -2, that's 0 squared at the front. And similarly, fyy will also be 0, because x is 1. But fxy, the first term will be 1 times e to the power of xy, which is -2, plus 2x, which is +2, minus y, which is 2. Second term is 0 again, because those coefficients become 0. And e squared. All right. And so d here will be 0 times 0 minus e squared, all squared. So minus e to the power 4, which is definitely negative. And so again, that will be a saddle point. Now, both my first two examples are saddles, but to be honest, if I got something different, you'd be able to interpret that differently as well. I think I want to spend a bit of time in class on Monday on this. I don't want to just leave this as online when you can't ask questions. So I have another example, but I'm going to save that till Monday. So I'm going to stop it there. Hopefully you're okay. Hopefully that all made sense. You can read through section 8 and follow what's going on. They show you several examples of all this. But if you do have any questions, I say email me or just bring them with you on Monday and I'll go through them. But we've got, Monday is allocated to this section. We're a bit ahead here, so we've got plenty of time on Monday to do that. So hope you guys have a good weekend. I'll see you on Monday. It's recording. So again, just to continue with our comparisons, as what I said. So Cat 1. We had the idea of optimization, and there's two pieces to optimization. There's just the concept of relative maximum, relative minimum, critical numbers, and then there's also optimization on a specific interval, right? So the overall theory in Cat 1 would have a question like find the absolute maximum and minimum on some function f of x, or sorry, I should say, of some function on some interval a to b, right? And we had the theory that said that there would be such a thing. There would be a maximum minimum, provided what? What was the one thing we had to stipulate for there to definitely be a maximum and a minimum value of a function on an interval? Right, it has to be a continuous, or at least it has to be continuous on that interval. It could have discontinuities elsewhere, but it would have to have continuity on that interval. So what was my method? No, where the first derivative is equal to 0. Right? So find your critical numbers, and so you would test, you test f of a, f of b, and f of any critical numbers that happen to be in that interval. And of all of those values, the biggest one will be the maximum and the smallest one will be the minimum. Because the only possible places that can happen is either at a critical number, because they're the only places you can get relative maximum or minimum points, or it may simply be at one of the endpoints where you're just, you know, cutting a function. If, let's imagine our function look like this. Well, if my interval happened to be, let's say, A to B, in other words, I'm looking at this particular piece of the graph. Well, you can see, I didn't draw that. I meant there to be a clear maximum there. So let me just try it. Make this go. So in this case, you can see that the maximum will be here at a relative maximum. That also happens, by the looks of things, to be the maximum of the entire function, regardless of how far we go. But my minimum point, of course, is here. There's nothing special about that point in terms of the function. It just happens to be where I cut the interval as it carries on decreasing forever. So that would have one value at a critical number, one value at an endpoint. All right. That's in effect what we are doing now. The classification of relative extrema was done by the second derivative test. So the second derivative test classified relative maximum and relative minimum points, or possibly failed when you try to use it. All right. So we are now in a similar situation, but we're actually going to have this spread over two sections because, as you can probably imagine, this is a bit tricky. Because this time, if I was to try and do this in Calc 3, now I'm trying to find the absolute minimum point of some multivariable function, but it won't be on an interval anymore. It will be on some region, right? Some domain given in terms of the xy plane, right? So this time I've got, now I'm drawing the xy plane again, but this time just to draw the region. I'm not representing the function here, but I will have some region R representing where I'm testing the function. And so this time, as for equivalent, I will need critical points, which is what I talked about on the video. Critical points where fx and fy are both 0. And any of those inside the region will be of interest because they are possible relative maximum and relative minimum points. But the tricky bit, of course, is now the equivalent of testing at the two endpoints is now testing at every point on the boundary, right? You know, the boundary represents possible locations for these maximum minimum points. In Calc 1, the boundary were the two endpoints, right? The two ends of the interval were the two places I needed to consider. So that's just two things to test and I move on. Here, there are an infinite number of possible places to consider, right? This boundary has an infinite number of points. So I'm going to have to deal with the concept of how do I test on the boundary. It clearly can't simply be a case of cycling through every possibility because I would have to just keep going indefinitely. And so that gets its own chapter, or sorry, its own section. Section 10, the last thing that we'll do, that we'll get to tomorrow, I might get to start it today, but mainly tomorrow, is going to deal with that. So back in Calc 1, you just kind of did this in one big lump because it was find the critical points, easy, differentiate and put it equal to 0, test it there, and at 2 extra points, the 2 endpoints of the interval. Here, it's a much more complicated idea, right? But the first bit of it is very similar concept. Find the critical points. All right. The testing on the boundary is going to get its own section in section 10. But as I said to you last time, you know, your critical points, you have to solve where fx is equal to 0 and fy is equal to 0. And then you classify them. This pen is not doing so good. And then you will classify them by considering this idea of what we call D. This is not a particularly obvious thing. It's not something that kind of leaps out as being an obvious thing to consider, but the second partials test will classify those things for you. So you consider the product of the 2 straight second partials minus the square of the mixed partials. And there are 4 possible situations, as I've put on the video. Either D is positive, and as I said on the video, if D is positive, then you can be sure that fxx and fyy have the same sign, right? The only way this can be a positive number, since I'm subtracting a positive number here, this thing has to be even bigger. So this has to be positive. D couldn't possibly be a positive number if this wasn't positive, which means that both of these are either the same, either both positive or both negative. And if they're both positive, then we've basically got the equivalent of the second derivative test from Calc 1. Positive second derivative means concave up, means relative minimum. If they're both negative, means concave down, means relative maximum. So if D is positive, then it's one or the other. It's a relative minimum or it's a relative maximum. If D is negative, then it's one of those saddle shapes. If D is negative, then it's basically saying that it's either concave up with respect to x and down with respect to y, or vice versa. And if it's concave up in one direction and concave down in the other, then you've got that saddle situation. And so it's not a relative maximum or a minimum. It is, in effect, the new version of a point of inflection. But we don't call it that because it's not the same thing. It's just a similar idea. And if D is 0, then the whole test tells you nothing. And so that's what I was talking about on the video. And section 8 is sort of abstractly just giving you that idea to run with, giving you some functions to test, making you think a bit about what that means about the graph, and so on. So let me give you one more to practice. And then section 9 just turns that into word problems, where you may have some naturally occurring restrictions on your variables just because there's some application there. And some basic sometimes the boundary is not a difficult thing to deal with, but in general it would be. So see if you can find and classify the relative extrema for this point. No, I'm just giving it to you. So x squared minus 6xy plus y cubed plus 40. No, because it's not an equation. It's a function. If I put it equal to 0, that would make it an equation. that would give y as a function of x, and so that would now be a curve right there. So, so partial df dx here will be 2x minus 6y. Partial df dy will be minus 6x plus 3y squared. All right, make sense? And so I need to solve those as a system. So this is, you know, some of the previous examples, you just got an equation involving one variable, so you can solve it nice and easily. In this case, well, so I need to put these equal to 0. So in the first case, that means that 2x is 6y, or x is 3y. And so if I substitute that into my second equation, this is 3y squared minus 6x is now minus 18y, which I can factor 3y out of. And so either y is 0 or y is 6. And of course, if y is 0, then x is also 0. And if y is 6, then x is 18. So I've got two critical points here, 0, 0, and 18, 6. Those are my two critical points as far as this function is concerned. They're the only possible places I might find relative maximum, relative minimum, or saddle points. But as to what they are, I'm going to need to actually work that out. So fxx here is 2. Fyy is negative 6. And fxy, sorry, fyy is negative 6y rather. Positive 6y. Know what I'm doing. Right?
Yes, yeah, that's right.
Happy with that? And fxy is negative 6. That's where I was getting ahead of myself. And so d here, in general, will be 12y minus 36. When I plug those values in. And so as far as these points go, well, 0, 0, then d will be negative 36. So what does that mean? It's a saddle. And in this case, 18, 6, d will be 12 times 6, so 72 minus 36. So d is 36. What does that mean? I mean, in and of itself, it means it's either relative minimum or relative maximum, right? That by itself doesn't tell you definitively what it is. What do I need to then look at? fxx, which is always 2, regardless of where you are. And if that's positive, then it's a relative minimum, right? Don't forget, you always have this in Cat 1 as well. It's slightly counterintuitive. You feel like positive result should mean maximum, but it doesn't, right? If your second derivative is positive, then it means you concave up. But concave up always means relative maximum, relative minimum. So this is a relative minimum. Okay? Happy with that? All right. I mean, that's about as much algebra as you're going to see in a problem like this. There have been slightly easier ones, but ones where you actually have to substitute one equation into the other might produce multiple critical points and therefore different possibilities. At no point are we ever going to worry about actually graphing this and thinking about what the surface looks like. All we know is that if we did model the surface, we'd have one saddle point and one relative minimum point, no relative maximum points. Okay, well, section 9 is from a math point of view, is the same thing, but this time the functions will have meaning. There's actually going to be some kind of context to them, which might also put some limitations on what x and y can actually equal. So let me give you just some examples. Moving to 12.9. So here's an example. Find 3 positive numbers whose sum is 15 such that their product is a maximum. Just, if it's an example from the book, I'd number it. But generally, I want to leave those for you. Now, this again is sort of it's going to help to cast your mind back to Calc 1 when you got optimization problems. Your issue with optimization problems was always to express the quantity that you were trying to optimize and the constraint that you were working to. Right? Sometimes called the primary and secondary equations, or sometimes known as the objective and constraint equations. Or I guess objective function, the thing that you're trying to optimize. So my objective function here well, if we call these three numbers x, y, and z, that's usually the way to. Sometimes there'll just be two variables, sometimes there'll be three in these problems. So my objective function is f of x, y, z, and it's the product of the three things, right? That's what I'm trying to optimize. Notice I'm trying to maximize it. It's pretty easy to minimize this. If one of the numbers is 0, then the product will be 0. I know technically they can't be 0 because I said three positive numbers, but if one of them is like 0.000001 or something like that, then obviously the product's going to be tiny. So minimizing the product, actually, it's quite interesting because as set up, you can't minimize it, right? The answer can't be 0 because none of them could actually be 0, but there's no minimum, right? Because you just keep getting closer and closer and closer. If I'd said three non-negative numbers, that'd be a much more straightforward idea because one of them could be 0, or in fact even two of them could be 0, and then the product is nothing, and that's as low as you can get. As it's set up, the idea of the minimum's a bit more nebulous, but that's okay because the question's not asking about that anyway. It just wants to know about the maximum. So what's my constraint here? Right, all three of them must add up to 50.
Do we need like a separate like three equations so that like x is greater than 0, or is that?
You'd usually, it depends how relevant it is, but yeah, you would usually write down the range of values that make sense for you. So like say in this case, my range of values really, x has got to be greater than 0 and less than 15. Obviously it can't be 15 because that would make the other two 0 and then they wouldn't be positive. And same for y and same for z. It's the same constraint on all three. Now, sometimes that's more relevant than others. That kind of side of things is going to get involved a lot more when we move into section 10 and consider the boundaries. For now, it's, you know, these problems are set up so very much the boundary isn't going to be, it's a common sense, not what you're looking for. Now, what happened in Calc 1 usually was that originally your function was actually two variables. Really, although Calc 1 is single variable calculus, Calc 1 and Calc 2, as we said, there were occasions when actually multivariable functions snuck in without really being described as such and got involved. So to give you an example of the kind of thing that happened back in Calc 1, you might have had like find area of a rectangle if you had a finite amount of fencing to create the perimeter, with perimeter equal say 20 or something like that. Right? Those are the kind of problems. And so what you did was you set up the rectangle with x and y, and you said that the area was x, y, the perimeter 2x plus 2y equals 20, and then we plugged that in to create a single variable function. I know I'm going way back here, but you'd say, okay, y is 10 minus x, and so the area now is x times 10 minus x. And at that point, you're now down to a single variable function. You can do all your calculus on it. But actually, for a moment, we created a multivariable function. We just never really thought about it as such because you were never going to deal with that in its own right. You were always going to quickly rewrite it into a single variable. And I bring that up really just because we're doing the same thing scaled up here, right? I've got a 3-variable function, which I now know how to do calculus with. It's not like that's out of range, but my constraint is going to, in effect, take one of those variables away, right? Every time you impose a constraint on something, it's like you are removing a variable. Here, I removed a variable to leave 1 left. Here, I'll still have 2 left. And so what I can say, and it's kind of up to me how I do it, you know, which variable I remove, but I can write that z is 15 minus x minus y. So now this is no longer a 3-variable situation, because if I know 2 of them, the third one is fixed by the constraint. And so now my function isn't a function of x, y, and z anymore. It's just a function of x, y. Specifically, it is 15xy minus 15x squared y minus 15xy squared. And so that's the thing that I'm trying to optimize. And again, it's not like we don't have the concept of finding a critical number, or a critical point rather, with 3 variables. I mean, it's not difficult to think fx is 0, fy is 0, and fz is 0. But the second partials test would not handle that. We'd need something else, and that won't be the case.
What was that 15 distributed? Like, 3 times?
Oh, I have absolutely no idea, because it's been a long day and my brain isn't working properly. Is that your question too, Christian?
Yeah, I was gonna ask that question.
Yeah, because I'm an idiot. That's why. There you go. That's what it should be. So see if you can find the critical point or points, and think about the second partials test here. Again, just because common sense tells us that something will be a maximum doesn't mean that you don't still have to kind of do the math to show it definitively. Like, rarely in math is trying to claim that something is obvious going to fly. You need to kind of be a bit more thorough than that. So if I find my two derivatives, I'll get that. I can factor them both slightly, and they both need to be equal to 0. I mean, not just one, they both need to be equal to 0. So let's take my second one. Think about this. Well, there's two possibilities here. Either x is 0 or x is 15 minus 2y. Right? So either of those situations can create the partial df dy being 0. But then I need to take those and plug them into the first one to guarantee that true. So if x is 0, that means that y times 15 minus y is 0. Or if x is 15 minus 2y, that means y times 15 minus 2x. Sorry, try that again. 15 minus 2x, so that will be 30 plus 2y minus y equals 0. And so in the first case, that means either y is 0 or y is 15. But of course, I could take two approaches. I could say y is not allowed to be 0. Y is a positive number. But even if y was allowed to be 0, that's clearly not a maximum. Right? If y is 0 and x is 0, then z will be 15. The product, nothing, which clearly isn't a maximum. But again, I can't really just say clearly like that. I need to go a bit further. But testing the boundaries is a little tricky. So that's the kind of thing that will have to be put on hold until we've covered section 10. Similarly, if y is 15, then x is 0 and z is 0. But either of these are going to represent maximum points. Right. It's very easy to think of three numbers that add to your 15 and their products bigger than 0. Let's put it that way. So I know that they're not what I'm looking for. They're not the maximum points. Did you have a question, Ashley? Yes. I don't want them equal to. I'm not interested when they're equal to each other. I'm interested when they're both equal to 0. If I set them to each other, I'll be getting more solutions. Because I don't care if they're both equal to 2. That's not of interest to me. They both need to be 0. So I'm kind of taking that in a sequential approach. Then over here, well, again, 1 equals 0 is an option. Again, I'm interested in it. And so finally, this one, which is going to give me, sorry, this should be math 30 plus 4y, not 2y. Then distribute math 2. So this was going to give me 3y minus 15 equals 0. So y equals 5. And finally, I'm getting something that might be viable. And of course, if y is 5, means x is 15 minus 2y, so also 5, and that means z is 5 as well, which you probably could see coming. I mean, it's not a particularly surprising result that the situation that I end up interested in, but all three numbers are the same. But that mathematically shows it. If I think about three numbers adding to 15, actually this product 5 times 5 is 120. The other numbers you pick will be less than that. You pick 2, 2, 11. Well, that's 4, 4. I pick 4, 5, and 6. That's 120. Nothing else will give me a product as big as 125. But to prove it, I'm going to do this formally. Let's call over here the fxx going to minus 2y. Fyy will be minus 2x. And the mixed partial fxy will be 15 minus 2x minus y. No, minus 2y. Sorry. And so D will be 4xy minus 15 minus 2x minus 2y all squared. Now, this is where you can properly see that if either x is 0 or y is 0, that's a saddle. Right? Because the first term in D is 0 and the second term is 15 minus 15 squared. But if I put all three equal to 5, specifically put x and y both equal to 5, that's going to be 100 minus negative 5 all squared. So D's positive, but fxx and fyy are negative. So it's a relative maximum. So that kind of proves what common sense had already told me, that this is going to give me a relative maximum situation. Okay. That makes sense? Everyone happy with that? Christian.
Actually, I'm just trying to figure out, I was trying to work with this, and I think I got something like very different here. It probably might have been.
These do take a bit of practice. It's weird because, you know, from a straight math perspective, there's very little calculus here. You know, I mean, you've got partial df dx and partial df dy, but it's the most, like, it's pretty much the first thing you ever learned in calculus was the power rule, and that's the only rule going here. But there's quite a lot of algebra, and you can get a bit rusty on solving equations. It can actually be quite a lot of time pass in the calc sequence between the process of solving equations. You have to go back and remember, what does it mean to solve an equation? If two things multiply to 0, what do I have to consider? What does it mean to solve a system of equations, and how do I do it? So these questions are well worth practicing to, mainly to give you practice on that, solving equations, rather than, it's not going to give you much practice on calculus. It's very straightforward for the most part, but it will give you practice on the process of dealing with that.
D is positive, right?
Right?
Doesn't that mean it's a minimum?
No, D's positive. It means now you go look at fxx and fyy, and fxx and fyy, they're negative. But if D's not positive, then it's either a saddle or the test fails. Okay. So yeah, the section 9 questions, and this is the kind of thing where, you know, each question's different. There's several examples in the book. I would not worry about the least squares stuff, right? They tie it up to the idea of least squares in statistics. To be honest, the only thing I really think you need to read are the first 2 pages of section 9. It then really kind of goes down the rabbit hole of least squares, and I'm not bothered about that. So in terms of the homework, I would say you can go as far as number 20, and I wouldn't go any further. There's a lot of least. I mean, there are certain, you know, if you were statistics majors or something, I'd probably be way more interested in doing that. But where we're going and for what you're generally here for, it's not something that we need to spend our time with. But 1 through 20 will give you a variety of different contexts. And I'll do one more tomorrow before we go on to section 10. But I have nothing left to teach you. I mean, you know everything you need to know. It's just a case of practicing the problems, really. So try 1 through 20, and we'll finish up. Tomorrow and Thursday, we'll do section 10. Then we've got 2 review days and then your tests. All right. Record. That's a more conceptual. So I think I'm going to firstly do a more numerical version of a problem, and then I'll do that one if that's okay. Just because I think the one I have in mind anyway will kind of lead quite well into that problem. So I think that'll kind of illustrate. So is that okay if I just do this problem first and then I'll come back to 14? For one thing, I think it'll just help you see that problem a bit better. So this is what, it's not from the homework, it's what I had lined up, but it's kind of related to that in some sense. So this question is find the volume of the largest box that can fit below the following surface: x squared plus 2y squared plus z squared equals 60. Well, I say fit below. I guess I should say fit inside, because that's a ellipsoid. So it's related to that example that you asked about, Christian, except that this isn't a sphere, it's an ellipsoid, because it's not got the same coefficients for x squared, y squared, and z squared. But in effect, what I'm kind of thinking here is, you know, I've got my x, y, z axes, and so this is some kind of ellipsoid, and I'm trying to fit a box inside this. And I want the biggest box I can. Well, I think it's pretty common sense to say that the biggest box that can fit inside is going to touch the surface, right? If it wasn't touching the surface, then I could clearly fit a bigger box inside. And if it's going to touch the surface, if it's going to be a rectangular box that touches the surface at all of its corners, then it's going to have to basically have its center of the box at the origin. In other words, all the different vertices of the box will be, all the x, y, and z axes will be axes of symmetry, I should say. Would be the easiest thing. So what I'm going to do is just basically consider this point here to be x, y, z. Right? If I can find that, then my other points will be things like minus x, y, z, or minus x minus y, z, or whatever. But my box here, when I actually draw the box, you know, in effect here, the dimensions of the box will be 2x by 2y by 2z, right? Because if x, y, z is where I've labeled my corner, then the box will go down to negative x and across to negative y and so on. So the widths will all be twice those things. So the volume of the box, which will be a function of x, y, z, will actually be 8 x, y, z. And the constraint, of course, is that that point is on the surface. So the constraint is that x squared plus 2y squared plus z squared equals 60. So that creates the objective function, the thing that I'm trying to optimize, and the constraint that I'm working on. Right? But I've set it up by simply applying some basic geometry and common sense to the situation where to get the biggest box I can get, I need to locate where one of the corners is, the corner in the first quadrant, and logically then I know where all the other corners are as well. And that will give me the volume of the box. So see if you can find and classify the critical points here using that setup. I'll give you a few minutes to try doing that. And then I'll take this because it's a similar concept to the idea of number 14. Okay, so there's my rearrangement. I can rearrange my constraint for any one of the variables. It doesn't have to be z, but just chose to make z the subject. Notice I'm making z the positive square root because the way I've labeled x, y, z, they're all positive in the first octant here. And so that reduces my volume function to just being a function of x and y. So that's the function I'm going to want to find critical points and then run the second partials test. Yes.
Could you have done anything with like square rooting it first, like the constraint? I mean, like I'm doing both sides, like reducing it.
You can't reduce. I mean, it's not like you can square root each term or anything, right? You can't distribute square roots. So there's no alternative to rewriting it that way. So if I go to my next page, so v of xy here is 8xy square root 16 minus x squared minus 2y squared. And so partial dv dx, I'm going to need the product rule and the chain rule, will be 8y square root 16 minus x squared minus 2y squared plus 8xy, and then chain rule gives me 1/2 of 16 minus x squared minus 2y squared to the power negative 1/2 times negative 2x as the derivative of my inner function. All right. In other words, what have I got here? I've got, well, if I factor 8y out of these two terms, I've got the square root of 16 minus x squared minus 2y squared. Over here, the 1/2 and the 2 will cancel. But if I factor out 8y, I've got minus x squared divided by the square root of 16 minus x squared minus 2y squared. Okay. Which, if I get a common denominator here, in other words, if I pull out a square root 16 minus x squared minus 2y squared on the bottom, in effect, I'm rewriting this term here as 16 minus x squared minus 2y squared divided by its own square root. Right? I mean, basically anything in math, if you've got the square root of something, you can rewrite it as it's the term divided by its own square root. It's multiplying top and bottom by that square root expression. Which means that this will now be 16 minus x squared minus another x squared, so minus 2x squared minus 2y squared. Obviously, I could factor a 2 out of that as well, but no, that's particularly necessary. Then v sub y, that will be 8x square root 16 minus x squared minus 2y squared plus 8xy, and again I'll need the product rule. So 1/2 16 minus x squared minus 2y squared to the negative 1/2, and this time I'll be multiplying by negative 4y. So in this case, I'll factor 8x out. I'll get square root 16 minus x squared minus 2y squared. Here the 1/2 and negative 4 cancel, so I'll leave behind negative 2. And so I've got minus 2y squared over that square root. Which again, if I was to pull out a common denominator of my square root term, This time I'll have 16 minus x squared minus 4y squared. Okay, so those are my two derivatives, which both need to be equal to 0, of course, or undefined. Well, notice it is possible for them to be undefined here, right? I'm just going to go. Well, I'm just finding the critical points right now, for reasons that I'll mention as we're doing it. So is everyone happy with these two expressions before I move on to the next page? So partial dv dx was 8y divided by the square root of 16 minus x squared minus 2y squared times 16 minus 2x squared minus 2y squared. And v sub y was 8x divided by that same square root times 16 minus x squared minus 4y squared. Now, like I say, notice it is possible for one or both, well, of course it will be both at the same time, to be undefined. No, even if one's undefined, that would be a critical point. But if 16 minus x squared minus 2y squared equals 0, that would represent a critical point. But not really surprising, right? Because if x squared, 16 minus x squared minus 2y squared is 0, well, that's z squared, right? That was originally what we said z squared was. And so if that's 0, then z is 0, and so the volume of the box is 0. So not surprising that that represents a critical point. In fact, it represents an infinite number of critical points. That's not just one, right? Anywhere where x squared plus 2y squared equals 16 represents a critical point, but one that is a guaranteed minimum value, right? Because that's giving me a volume of 0. I can't get anything smaller than, you can't have negative volume, so that's definitely a minimum. But the question asked me specifically for a maximum. So I'm not really interested in those points. But what is in effect happening here is, remember we had the ellipsoid. The ellipsoid. Well, that represents an ellipse, and that's the ellipse where that ellipsoid intersects the xy plane. It's the trace, basically, of the xy trace of the shape. So not surprisingly, if my box had a point located anywhere on that, it's got no third dimension, so it's got no volume at all. So yes, those are critical points, but they're not what I'm being asked to find in the question. Equally, to say that Vx is 0 and Vy is 0, which I need both of those to be true if we're looking at the 0 rather than undefined. Well, obviously x equals 0 and y equals 0 works, right? That's also a critical point. But again, 0 volume. This time my box is basically a spike coming out the origin. It's only got a z component, which again I'm not interested in. So I don't want x to be 0 and I don't want y to be 0. So what I'm looking for is for those two things to both be 0. In other words, I need 16 minus 2x squared minus 2y squared to be 0. And I need 16 minus x squared minus 4y squared to be 0. Right. Which basically gives me a system of equations to solve. Put it another way, x squared plus y squared needs to equal 8, and x squared plus 4y squared needs to equal 16. And so if I subtract those, 3y squared must be 8. So y squared must be 8/3, meaning y is the square root of 8/3. And if I substitute that back in, if y squared is 8/3, then x squared plus 8/3 equals 8. And so x squared is 16/3. And so x is the square root of 16/3. Which obviously that simplifies down quite a bit because of the 16 on top. But to some extent, I really just want decimal versions of this anyway. This is a very practical question. And so, you know, that will be just fine. So that's my critical point here. That's going to give me a non-zero volume. Of course, z here, z squared is 16 minus x squared minus 2y squared, which is also 16/3. And so I'd find that my max volume occurred when x is square root 16/3, y is square root 8/3, and z is square root 16/3 again.
Do we not care then about the max volume, or do we only care?
Well, the question was to find the maximum, the largest box that we could fit underneath. Now, technically, we're not fully done because I haven't run the second partials test. I really put this one up for you to see that the second partials test here is going to get really quite messy because I'll need Vxx. Well, look what Vx is. Right, I'm going to need the quotient rule and the chain rule to get Vxx. Same for Vyy, and Vxy is going to be even worse because for Vxy this is a product and a quotient rule and a chain rule altogether. So this will be an example of one where you know, the second partials test will be a real mess. And common sense here has really told us clearly this is the biggest. I know it's not this represents either the maximum or the minimum volume. I know it's not the minimum because it's not 0, so it must be the maximum volume. Right, and that product down there, if you worked it out numerically, is that maximum volume. Okay, yeah, sure.
Will you use something like this on the test?
Not if I'm expecting you to use a second partials test now.
Thank you.
The second partials test will be something, I'm more interested that you know how to use it and what it means, rather than you spending 10 minutes on a very lengthy derivative. You know, Calc 1 was where I checked you could differentiate properly. I by now trust that you can differentiate. I'm only really interested in you knowing the correct method rather than doing something super complicated.
Thank you. I saw where this problem was going, and I was like,
Yeah, it would be. There are times when you kind of just fudge the issue and let common sense just do its things. But that would be the result, and that kind of leads into your question 14, Christian, because it's a very similar setup, except this time it's a sphere and a box, but it's the same idea. It just doesn't give you any figures, right? It doesn't give you any specifics in terms of things. It just says, show that the rectangular box of maximum volume inscribed in a sphere of radius r is a cube. But let's kind of approach it similar to this. Any questions before I get rid of this? So same idea, but this time we've got the box has a volume, which again will be xyz. Sorry, 8xyz. But this time the constraint is that x squared plus y squared plus z squared equals r squared. That's the equation in my sphere. So very similar with two differences. One is it's a sphere on an ellipsoid, but also r squared is a bit more nebulous, right? R is some parameter, but we don't know what it is. But it's not asking us here what the volume is. It's asking us to show that it will specifically be a cube, which is kind of common sense, right? I mean, if you think about it, you'll probably expect a cube to be the biggest box you can fit inside a sphere. But to prove it, well, again, z here will be the square root of r squared minus x squared minus y squared. And so my volume as a function of x and y will be 8xy times the square root of this thing. And so v sub x will be 8y times the square root plus 8xy, and then I'll have to differentiate this, so 1/2 r squared minus x squared minus y squared to the power negative 1/2 times negative 2x. The 1/2 and the negative 2 cancel, and just like before, if I factor 8y out of that, I'll get my square root. And then I've got an x and a negative x left on this side, so minus x squared divided by that same square root. Which, if I take that common denominator out, oops, x there, will leave behind r squared minus 2x squared minus y squared. I kind of raced through that a bit because it's almost identical work to the last problem with just some different coefficients. All right. And I'm not even going to do the work for Vy. I'm just going to write down the result and let you kind of reason through it at home. But there's a lot more symmetry to this, so the exact same thing's going to happen. Except this time I'll get 8x over the square root of r squared minus x squared minus y squared. Exactly. Now it's r squared minus x squared minus 2y squared. Thank you. So those are my results for Vx and Vy. And again, same argument as last time, critical points. Well, if that denominator was 0, that's a critical point. But if the denominator is 0, then z is 0. So my volume is 0. So definitely not a maximum representation. Equal x and y can both be 0, but again, that's definitely not what I'm looking for either. The results that give me minimum volume are easy to find, but also uninteresting. I want to know where the maximum volume is, and so the maximum volume occurs when r squared minus 2x squared minus y squared equals 0 and r squared minus x squared minus 2y squared equals 0. Which means that 2x squared plus y squared has to equal r squared, and x squared plus 2y squared has to equal r squared. Well, neither one will quite do. You'd need to multiply one of them by 2 and then subtract. We eliminate, and either one would work. But it's not difficult to see that I have numerical answers here because I don't know what R is, but I do need x squared and y squared to be the same thing. The only way this is possible is if x squared and y squared are equal. All right. I mean, I can prove that by if I multiply the first one by 2 and leave the second one alone and subtract 3x squared will equal x squared. But if 3x squared equals r squared. In other words, x squared equals r squared divided by 3. Then so is y squared. Sub that back into the system of equations. If x squared is 1/3 r squared, then 2y squared needs to be 2/3 r squared. And so on. And what matters is not what x and y are, so much as the fact it must be equal. Notice, of course, if x squared is r squared over 3, that implies y squared must also be r squared over 3, which implies z squared must also be r squared over 3. Z squared is r squared minus x squared minus y squared. And so I've shown that all 3 x, y, and z are all the same, therefore it's a cube, because all 3 sides are the same line. And that's what it's asking for.
These are rectangles, because for that previous details of something where
So that's because it was x squared root 3. So it is coincidence to some extent. And it's not probably somewhat likely because components are decent. It doesn't have to be. Yeah, right. It doesn't be squared. But I could make one where you have a 3 on the bottom. Probably a multiple of 3, but maybe not. So. And there's you that it has to be a cube. Okay. Those questions are well doing like 1 through 20 because, you know, sometimes in math work where there's, you know, 60 questions, they're really all the exact same process, one or the other. Different numbers, different functions, and maybe slightly increased difficulty, but same approach. Things were problems that are different from each other. So really necessarily this a lot. You're feeling more confident. It's not like work in a field you do for the 6 or something like that. But definitely kind of time. 1310 deals with the idea of the table where it said, you know, example we did with soil, you know, you've got critical points on the whole boundary. There's a whole boundary. I can't test at every point on the boundary. It's not possible. Now I worry about it because I only knew volume 0, so it represents what I was looking for. But in general terms, if it's complicated than that, what if I have an expression to optimize and a constraint where I can't just easily see what the result is? Well, section 10 gives a way of doing that that is very elegant approach to this thing. It's something that I always enjoy teaching because it just gets to some of the more artistic beauty of math, I guess you might say. Let's look at the example that they're giving as their introduction, because I think it's as good as you can get to some extent. They present the idea of trying to optimize really what we just did. Trying to find the largest rectangle that you can fit inside an ellipse. So there's an ellipse, which is, I mean, they specifically use x squared over 9 plus y squared over 16 equals 1. But don't read anything into those numbers, that's just some expression. And they want to find the biggest rectangle that they can inscribe inside that. And so it's very similar to what we've just done, but actually flattened down to 2 dimensions and so a bit easier. And so again, you know, I haven't drawn this very well. This should have more symmetry than it does. But same argument, we'll call this xy. And so the volume, sorry, not the volume, the area rather, so in 2 dimensions will be 4xy, right? 2x times 2y, the dimensions of the rectangle. and the constraint is x squared over 9 plus y squared over 16 equals 1. Now, it's not like we couldn't do this the way we just have done. In fact, I mean, this is really a Calc 1 problem. You could make y the subject of your constraint, substitute it in. You will now have your area function just as a function of x. So now we're back to Calc 1, where it's just like the critical point, first derivative test, second derivative test, etc. But it's a good setup because it also kind of illustrates the way you can do this with more complicated functions. So bear in mind what I'm trying to do here is to maximize the area function subject to that constraint. All right. Now, let's just think about all the possible values I could get from my area. In other words, let's think about that being equal to some constant c, where c can be 7 or 12 or whatever it want to be. In other words, what I'm really looking at there are my level curves that we talked about, right? You know, it seems a long time ago now, but right at the start of this section. So what they make the point in the book is we could rethink this idea of saying, okay, here's my ellipse. And I want to think about all the different values that my area can take. 4xy equals c. In other words, think about all the curves where 4xy equals c. Or to put it another way, y equals c divided by 4x. And I'll think about that for c equals 1, 2, 3, 4, 5, etc. Well, they're all hyperbolas, right? I mean, y equals c divided by 4x will look like this, or it will look like this, or it will look like this, or it will look like this. These are all my different hyperbolas where, and I'm going to write in here like c equals 1, c equals 2, c equals 3, but I don't actually know. I don't know exactly what c values they are. I'm just writing them, for example. But in effect, what you're doing is any point on one of those red curves represents your rectangle having a fixed volume. All right, everywhere on the c equals 4 curve, for example, basically means if I take this point, or this point, any one of these points, and make it the top right corner of a rectangle, then that's the area I'm talking about. All right? So if my point is on here, it will have a volume of 4. And again, this is almost, well, I am certain this isn't 1, 2, 3. This is probably like 5, 10, 15 or something like that. In fact, just to make that point, let's renumber these because I don't want to make it look like something along those lines. And so what I need is for my point to satisfy the constraint. In other words, my point needs to be on the ellipse. So this isn't going to work because this hyperbola doesn't touch the ellipse, right? Neither is this one, right? These are nice big areas. It's, you know, if all I'm saying to you is, here's an area, 4xy, maximize it, well, there is no maximizing that. You just make it as big as you like. The bigger x gets, the bigger y gets, the bigger your area gets. But I have to stick to my constraint. So whilst these have nice big areas, they're not okay because they don't satisfy x squared over 9 plus y squared over 16. Similarly, this one here does, right? This one, there's 2 different places on this hyperbola that satisfy that. So this one does have 2 points that satisfies it, but it's not the biggest area, right? Because there's a bigger area here that also has 2 points that work. So what I want is the hyperbola that just touches the ellipse at the very edge, right? Basically, yes. So what I'm really looking for here, I would specifically like this hyperbola that tangentially touches the ellipse at that point, right? That's sort of a graphical way of thinking about what the question is saying, trying to locate this particular point. But the point that it makes, which Asher just alluded to, can I move on to the next screen? Everyone happy with this? If that happens, oops, sorry, that's not what I meant to do. If that happens, so I've got my ellipse and I've got my hyperbola. At this point, the tangent line to the ellipse and the tangent line to the hyperbola are the same thing, right? Right? For that to happen, they must have the same tangent line. Well, the only way that the tangent lines can point in the same direction, remember, tangent lines are normal to the gradient functions. So basically, my red graph, my hyperbola, has a gradient function. So let's imagine this is g of xy equals some constant. And down here, this is f of xy equals some constant. So the two graphs are there. Well, the normal vector, or the gradient vector rather, to my red graph, del g, points in this direction. And the gradient vector to my green curve, my ellipse, points in that direction. In this case, they're diametrically opposite, but basically one is a multiple of the other. The only way that two graphs can share a tangent line is if their gradient vectors are scalar multiples of each other. So what I know is that the gradient vector of f at my point, this point here, that I'll just call AB, that I'm trying to find, that's the answer to my question in effect. The gradient vector of f at AB is some multiple, and we call this lambda, of the gradient vector of g at that point. And this thing lambda is called a Lagrange multiplier. It's a numerical value that represents the you what?
It's for optimization purposes, right?
Yeah. But notice, remember what this means. The gradient vector of f is fx I. Let's try again. Is fxi plus fyj. And over here, the gradient vector of g multiplied by lambda is lambda gxi plus lambda gyj. And so the only way those two vectors can be equal is if f partial df dx equals lambda partial dg dx, and partial df dy equals lambda partial dg dy. I also know that actually the way I've set this up doesn't quite, I don't want to go back and change it now because we're right out of time, but in the book they would have switched around which one they call F and which one they call G. So I guess the way the book set it up is G is the one that has the given constraint. The way I've drawn it, F, this isn't quite true. I've written equals C and equals C. Well, for one thing, I shouldn't be using the same letter because they're not the same thing. But this one is fixed by the question. The question will tell you what this value is. You're trying to work out this constant. That's kind of the purpose of the question, is you to work it out. So I should have switched those round. G, the way the book does it, G is the one that's the actual given constraint, not F as I've drawn it. So hopefully, I'll show you in examples on Thursday where this is going. But notice that there's three things I don't know here. A and B, which are the real things I'm looking for here. A and B is kind of the critical point. And lambda, which is just sort of a part of the process. It's almost like a catalyst. I need it, but it's not. I need it to do the whole process, but it doesn't actually tell me the thing that I'm looking for. But if I've got three things I don't know, I need three equations. Those are two of them. The third one is simply whatever the constraint equation actually is. So this represents a system of three equations in three unknown terms. A, B, or in the book x0 and y0, they call it in the book, and lambda. So that's the setup. On Thursday, we're just going to spend time doing examples where we actually use this method, and I'll show you how it works. For now, just focus on the section 9 homework. And read through section 10, but don't try any problems. So that'll be Thursday's job. I just wanted to get the theory created for you. So.
You said chapter 9, and first thing I was like,
Sorry, section 9.
I was very confused for a second there.
So we'll do that Thursday. Friday and Monday are both review, and then Tuesday's your test. So a week today is next test.
So it's called a Lagrange multiplier?
Mm-hmm. Well, lambda itself is specifically a Lagrange multiplier. This is known as the method of Lagrange multipliers. But
does it have anything to do with Lagrange points, or?
No, well, beyond the fact that the same man found them both.
Okay.
But I mean, Lagrange did a lot. I mean, he was very involved in this. But no, a Lagrange point is more of a property of. I mean, it's a geometric property, but to do with gravitation and interaction.
Yeah. It also deals with optimization, though. The Lagrange points. Because I mean, Lagrange points would make good spots for like resources and natural resources.
Well, I mean, the original form of a Lagrange point was where you kind of have a gravitational sweet spot. So it wasn't really optimization or anything, but it does transfer to that. But originally,
Gotcha. That's the way I know it. Because a lot of people use Lagrange points for like. I read a lot of sci-fi, so I know a lot of people talk about Lagrange points as like sweet spots for like the.
Section 10, then the last section of the chapter, this idea of a Lagrange multipliers. So like I said, is basically a very elegant way of dealing with the idea of optimizing some multivariable functions subject to some constraint. You could even extend it to optimizing a variable of 3 functions subject to 2 constraints and so on. Now, they are not necessarily things that couldn't have been done a different way. I mean, in Calc 1, we did that. This is just an elegant way of doing more complicated problems. But just, I'll remind you of the setup before we do examples. So you'll have an objective function that you're trying to optimize. Which will typically be a function of x and y, but maybe a function of x, y, and z. And then some constraint, which you can express in the form of a different function of x and y being equal to a constant. I mean, effectively, the constraint tells you what requirements you're placing on x and y. And Lagrange's equations, which you will see on page 957. The theorem here for Lagrange means that you solve 3 equations simultaneously. The first one is that partial derivative of f with respect to x is equal to lambda, where lambda is some multiplier. That's called a Lagrange multiplier. Partial dg dx. Same thing with respect to y. And then finally, the original constraint equation itself. There are 3 things there I don't know. X and y, where now x and y are the location of the maximum or minimum value, and then lambda itself. Whether lambda has any physical significance or not will depend on context. But by and large, lambda's not what we're trying to find, but we may need to find it in order to find x and y. So let me give you an example of how this can be used. And in this example, I can relate it back to Calc 1 as well. So this one's more illustrating how it gets used rather than really being the best method here. Okay. Any questions before I go on to do? Find the maximum and minimum value of the function x squared plus y squared subject to the condition that 2x minus y is equal to 4. Now I can sort of logically reason out here what I'm going to see. So bear in mind, I'm looking for, I want to consider all the points where 2x minus y is equal to 4. In other words, all the points on a straight line. So bear in mind, if I rearrange that constraint, y would be 2x minus 4. So it's this straight line here. Slope 2, set 4. And I'm trying to consider, for all the points on that line, what x squared plus y squared is. Which, of course, is basically the distance of that point away from the origin squared. Right? If I think about the circle, x squared plus y squared equals r squared. You know, whatever point I pick here, the function I'm trying to optimize is the distance of that point away from the origin squared. So talk to me about the question setup. I'm asking for the maximum and minimum value of this. No, so the stuff that goes before 13.10 is more when you're working with no constraint. 13.9 is really just finding critical points. This isn't finding critical points. This isn't finding where fx is 0 and fy is 0. This is finding all the points on this line, which point gives me the smallest value, which one gives me the biggest one.
Wait, how does this tell you the smallest of the largest value? Because critical points define smallest values?
There amongst, but see what we're doing here is if you think back to Calc 1, when we were testing on an interval, we'd find critical points inside the boundary, and then we'd test the two boundary values as well, right? The two ends of the interval. The problem is now that our boundary, such as it is not just 2 points now, it's all the points on this line. This is the constraint. So I'm just, you know, there's a very good chance, I mean, well, we can see that here, right? What is the critical point to this function? If I asked you to find the critical point to this function, what is it? It's 0, 0, right? With the origin. Because I'd do partial df dx is 2x, and partial df dy is 2y. So the only way both of those are 0 is if I'm at the origin. So my critical point's the origin. But I'm not being asked for that here. I don't want to know what the overall maximum or minimum value of this function is. I want to know specifically on this line which point represents, of all of those points, which one is the biggest, which one is the smallest. So basically, let me put it another way. One of those things makes sense and one of them doesn't in terms of maximum and minimum. Which one? But so, my question setup in general was find the maximum value that function can take on the line, find the minimum value that function can take on the line. Actually, one of those really doesn't make sense. Which one?
The maximum.
Maximum, right? Because there is no maximum. The further you go, the bigger x squared plus y squared is going to get on that line. But if you think of the function as being the distance from the origin squared, well, you can go as far as you like from the origin on this line, and you'll never have gone as far as is possible. So there is no maximum value, but there is a minimum value, right? And you can hopefully kind of picture it. It's almost like I'm picturing growing circles here until one of the circles just grazes the line. But as to exactly where that happens, that's what I'm trying to work out. So that's really the point. So I set it up to find maximum minimum value, but really there's only a minimum value. But this is nothing to do with critical numbers, and it's nothing to do with the second partials test either. The second partials test only tests critical numbers. That's not what I'm trying to find here.
So if you wanted us to do the second partials test, you give it an area with no constraint. But if you wanted us to find where the line is all that, then you give us something like this.
Well, eventually these things will kind of get mixed together. So think back to Calc 1. What you really do with a problem is you find all the critical points inside the interval, and then secondly, you test the two endpoints of the interval, right? And then having done all of those things, you collect all the answers together and say, all right, which is the biggest number, which is the smallest number. Now, eventually what we'll be doing here, the ultimate question, I guess, here will be find the maximum and minimum value subject to, let's say, and this isn't a great one because it doesn't really quite make sense here, but I could say 2x minus y is less than or equal to 4, which is now not just a line, it's a half region of the plane. It's one side of the line. So now what I'd do is I'd test everywhere inside the region, i.e. look for my critical points and consider those. And then I'd test everywhere on the boundary, which is now not a case of just testing 2 points, it's testing the entire constraint. That's what Lagrange multipliers does. Lagrange multipliers is a much more elaborate way of testing the points on the boundary, and it has to be more elaborate because now my boundary isn't one number, it's a whole set of points on a line or a curve or something like that. And so really sections 8, 9, and 10 ultimately get fused together into one big question, which is to test a function on a region of the plane. What I might say is find the maximum and minimum values of a function on this region here, call it R. Well, there's basically two things going on here. There's section 8, which would say find the critical numbers of the function, or at least find the critical numbers that happen to be inside this region. And then section 10 says, oh, and also test on the region, on the boundary of the region. And then mix everything together to get your final answer. But for now, I'm just going to focus on the Lagrange multiplier thing. When we do the review tomorrow on Monday, I'll look at how you can actually mix those two things together to make one big question. But let's go back to this problem. So let me show you how the Lagrange multiplier version works. And this one's a pretty straightforward one. But equally, it's so straightforward that actually Calc 1 would do this nicely. But here's my function. And g of xy here is going to be 2x minus y, because g of xy is some function of x and y that's equal to a constant. Okay. And so I've got three equations. I've got f sub x equals lambda g sub x. Well, in this case, what's partial df dx? 2x. And what's partial dg dx? 2. So lambda equals x. right? I don't know what either of those things are, but I do know that they're the same value. Partial df dy is asked to equal lambda partial dg dy. It's the same lambda, right? That's important. So partial df dy is 2y. Partial dg dy is -1. So that's negative lambda. And then the third expression is just the original constraint. So I've got 3 equations in 3 unknowns. Well, some kind of substitution is going to help me here. So if lambda is x, then 2x is 2 lambda. Minus y, well, y, of course, is negative lambda divided by 2. So minus y is plus lambda divided by 2. And that's equal to 4. Well, 2 lambda plus lambda over 2 is 5 lambda divided by 2. So lambda here is 8/5. But lambda is really not what I'm particularly interested in. What I want to know is the point. Again, and I'm going to try and make sure I don't fall into the trap. It's really easy to call this a critical point. It isn't. It's sort of a critical point of all the points on the line, but that's not what it's called. But my point that I'm interested in is, well, x is lambda, so that's 8/5. And y is negative lambda over 2, so negative 4/5. And if you look back to that diagram where I drew the circles, well, that's a reasonable location for the point I was looking at. X positive, x is 1.6, y is negative 0.8. Now, what this doesn't have is a second partials type test to decide whether something is a maximum or a minimum, but you test the function at all the points you get. Now, if there's more than one, that's fine, because one of them will be the biggest and one of them will be the smallest, and you're good. If you only get one, like in this case, where I can say that the function when it's 8/5 and negative 4/5 is x squared plus y squared. So it's 64 over 25 plus 16 over 25, so 80 divided by 25, which is what, 3.2? (16/5) basically. So I know that that represents either a maximum or a minimum. How do I tell which one? Well, basically pick any other point on the line and see if it's bigger or smaller. At any other point on the line, of course, for example, if x is 2 and y is 0, that's an obvious point from the line. Well, f of 2, 0 is 4. So I can see that because that's bigger, then this must be a minimum. It can't be a maximum because I've just found another point with a bigger value already. That's not on the line. This is specifically only points on the line. If we mixed it, now if we mixed them together, yes, then you would say f of 0, 0 is nothing, and so that's the minimum, and there is no maximum, because the further you go. But this wouldn't be a great example of that. I'll come up with much better examples of how you can mix the two together. But let's just not miss the fact that you actually all have known how to do this problem for a long time, right? Because if I go back to Calc 1, if I gave you this problem there, 2x minus y is 4, so y is 2x minus 4, and so this function can now be written as just a function of x, subject to the constraint, because now this is x squared plus 2x minus 4 all squared. In other words, so this will be 4x squared plus 1x squared, so 5x squared minus 16x plus 16. And so where do I get my optimal values? Well, the derivative will be 10x minus 16. I want to know where that's equal to 0. So x is 16 over 10, which gives me 8/5. And then I plug that back into the original equation to work out what y is. Right, so that would have been nice and easy back in Calc 1 too. But that one I was really just trying to illustrate for you how Lagrange multipliers works. I'd also noticed the Lagrange multiplier was really straightforward too. But it did involve creating and solving a system of 3 equations, which is never, you know, that straightforward, regardless of how simple it is. But the point being that as these equations and functions get more complicated, trying to do it the Calc 1 approach becomes more complicated too. The Calc 1 approach does assume that you can find f prime, which will be fine, and then that you can put it equal to 0 and solve, and that can get trickier and trickier as these things go through. So Lagrange multipliers come more and more into their own as things get more complicated. For example, I'll give you this problem. So optimize this function. So x squared minus xy plus y squared. Subject to a constraint of x squared plus y squared equals 1. Now this time, if I tried to do it the Calc 1 way, well, I've got a couple of issues. One is that I can't actually write y as a function of x, right? Y will be 2 different functions of x, so I'd actually have to do the whole process twice. That's one issue I've got when I substitute it in. And the second one is that if I substitute it in now, f of x will be x squared minus xy, so minus x root 1 minus x squared, plus y squared, which is 1 minus x squared. In other words, 1 minus x root 1 minus x squared. Or possibly 1 plus that for the other version. So I'd have to consider it twice. But that, you know, by the time you're out of Calc 2, you should be convinced that this isn't a nice, simple function to be dealing with in calculus. This kind of function tends to cause more problems than other things in calculus. So you could do that, but differentiating that and then putting it equal to 0 and solving isn't trivial anymore. So that's a possibility, but now let's consider here what the Lagrange theorem version looks like. So here's my f of x, and here's my g of x. So write out the 3 equations, and then just have a go at solving them. See what you get. Bear in mind to consider every eventuality here, every possible result. So there's my system of equations. I'll plug them in. This one's tricky because you don't just get that, you know, a direct relationship between x and lambda or y and lambda. So you have to kind of be careful with this. Ideally, because lambda is not really of interest to us beyond we might need it to work out what x and y are, if we can eliminate lambda, that's not a bad thing. So notice here I could multiply everything in the first equation by y. So we'll get 2xy minus y squared equals 2xy lambda. And then in the second equation, I'm going to multiply both sides by x. So minus x squared plus 2xy is equal to 2xy lambda. But I can't tell you every time this is how you solve the system. Right? This is when you need to be good at algebra. Right? Because how you solve the system will change from question to question. You just need to be on how you go about solving equations. There's a reason why you need to be very good at algebra before you can do calculus. You need to be ready to solve systems like this. But notice here, this is because now both of the right sides are the same, then I know that 2xy minus y squared is the same thing as minus x squared plus 2xy. In other words, x squared and y squared must be the same thing. The only way that those two equations are possible is if x squared equals y squared. Which means that I can then plug that in here and say, okay, that means that 2x squared is 1. So x squared is 1/2. And so x is plus or minus the square root of 1/2. Right? But x squared and y squared are the same thing. So if x squared is 1/2, then so is y squared. And so y is also plus or minus the square root of 1/2. But do notice there's actually 4 combinations here, because x and y don't have to have the same sign. So they could both be positive, they could both be negative, or one could be positive and one could be negative. So there's actually 4 points I need to test here. Right? When it actually comes down to it. I'm going to move on to the next screen. Has everyone got this? Can I erase this screen? So I need here to actually test square root. So, and obviously square root 1/2 is 1 over square root 2. I can do that. So I need to test that, which will give me x squared. Here is 1/2. Minus xy is minus 1/2. Plus y squared is 1/2. So my answer will be 1/2. But then I also need to test when x is negative and y is positive, which this time will give me 1/2 plus 1/2 plus 1/2. So 3/2. Same thing when x is positive and y is negative. I get 3/2 as well. And finally, if both are negative, I get the same as my first result. So this is my minimum value, which occurs at 2 different places. And this is my maximum value. Occurs at 2 different places. You pick any other point on that circle. Remember, the constraint here is that x squared plus y squared equals 1. So you pick any other point on that circle and plug it in, your answer will be somewhere between 1/2 and 3/2. For example, what about if I pick the point 1, 0? That's a point on that circle. Well, that'll give me x squared minus xy plus y squared, which I can see is clearly between. It's not minimum and it's not maximum, because there are points on that circle less than 1, also points greater than 1. You pick any other point on that circle, you'll never get a value that's not somewhere between 1/2 and 3/2. And those are the 2 places you get the 1/2 and the 2 places you get the 3/2. Okay?
So either you solve for lambda or find a relationship between x and y?
I mean, ultimately, you're solving the whole system. So, I mean, the true solution to the system will be a value for x, a value for y, and a value for lambda. It's just that to answer the question, you don't actually need lambda. So if the process, like the first time we did it, we just had to find lambda in order to finish the problem. In this case, I didn't. But I could go back and work out what lambda is in each case here. I just don't need to. You know, that's more of a catalyst to the problem. It's there, but it's not the answer to the question. But there are times when finding lambda will be a necessary part of the process. But ultimately, your answer are the x and y values. Okay. Now, here's one where I said I wouldn't do this till the review, but it's easy enough to just do it now. Let's imagine now. So, and again, notice there's no second partials test. I got more than 1 point, so I just test the function at all of the points and look for the smallest and the biggest. Right, that's my process. The fact that I've got 2 different values showing up tells me one's minimum, one's maximum. But let's imagine we slightly adjusted this now to say find, or I guess I should still say optimize this function x squared minus xy plus y squared on a region of the plane x squared plus y squared is less than or equal to 1. So what I just did was to test that function on every point of the circle. And basically what I found was at these 2 points, it was 1/2. At these 2 points, it was 3/2. And every other point is somewhere between. But now I'm actually interested in the whole region. You know, let's imagine, for the sake of argument, that this function represents a temperature distribution in a circular region. And so I want to know what's the hottest point, what's the coldest point, not on the boundary, but now of the entire thing, on the boundary and inside as well. So this will be a 2-stage process. Stage 1 will be critical points. So I still want my fx, remember 2x minus y, and my fy was minus x plus 2y, but this time I want to know whether both equal to 0. And so y is 2x, which means that this is minus x plus 4x, so 3x is 0, so x is 0, so y is 0. So my critical point here is the origin. If there was more than 1 critical point, I'd consider that too, but I'm only interested in critical points inside the region. If a second critical point had been the point 2, 2, I don't care, because that's not part of the question. The second part will be everything we just did, the Lagrange multiplier. And that's what gave me the 1/√2, 1/√2, etc. And then the third thing is I test the function at every critical point and all the points that came out of the Lagrange multiplier test. And so now I've still got all of those things from before. Right, there were 4 of them, I'm just going to write down 2. But now I'm also interested in testing at the critical point as well. Of course, is 0. So now the question is that I have a minimum value at the origin and a maximum value of 3/2 here and here. Right. So these are no longer minimum values because once I'm allowed to go inside the region, there are cooler points still. Not on the boundary. These are the 2 coldest points on the boundary, but the origin is colder than those. However, these are still the hottest points because there are no more, it doesn't matter what values you pick, you'll never get bigger than 3/2 on or inside that region. So that kind of mixes section 8 and section 10 together, right? Section 9 was just word problems. So section 9 and section 8 are just one mathematical idea. Section 8 was the math of it. Section 9 was the application of it. But that's a question that has taken both of those ideas and put them together into a single concept. Right? Does that make sense? Happy with that? So if you're given a region of the plane rather than just a curve or a line, then you do both critical points within that region and Lagrange multiplier on the boundary. Okay, make sense? Any questions? What we've done so far have been functions of 2 variables, and so you've ended up with a system of 3 equations, because you'll always have your variables plus lambda. So if you've got 2 variables, x and y, you'll have 3 unknowns, x, y, and lambda. You need 3 equations. If you had a function of 3 variables, so let's imagine I'm optimizing this function. So I'm just going to make it the product of x, y, and z with a constraint that 2x plus, minus y plus z equals 6. This is that I've taken sort of the idea before. Previously, we've sort of had, in effect, finding the maximum and minimum areas of rectangles under a curve. This is now effectively the maximum or minimum volume of a box under a plane. So it's the same concept, just all scaled up. But this time, what I would say is that my Lagrange equations are that fx is lambda gx, fy is lambda gy, but of course this time I also have derivatives with respect to z as well. And so it's not a big deal. Yes, I've got 1 more variable, but I will naturally have 1 more equation as well. So the Lagrange multiplier equations, you have as many as the number of variables you have plus 1. The plus 1 being the constraint equation. See if you can solve that. Yeah. Again, if X I'm saying we box a plane, well, the only thing required is that part of the box is somewhere on the plane. So you make the box usually you'll start the plane. But the box is too small, it won't reach the plane. So you'll have minimum no matter. So there's my system of equations. Again, you have to get a bit creative on how you solve these. And there's no one way to do it. But I could, for example, take these two and say, okay, well, considering these two, if I divide the two left sides and the two right sides, then y divided by x is -2. In other words, y is -2x. Or, of course, z could be 0 and lambda would be 0. That's the other possibility. So I do have to consider that. But z equals 0 doesn't make a whole lot of sense. Well, that's maybe not true. I'll come back to that. So if z is 0 and lambda is 0, well, that would mean that x, y would have to equal 0. So at least one of x and y would have to be 0 as well. So that's one possibility. Or say y equals -2x, which means that if I substitute that into the third equation, x times y is now -2x squared is equal to lambda. And so x would be the square root of negative lambda divided by 2. Now, that's okay. It just means lambda's negative. You don't say I can't take the square root of a negative number. Because you can't take the square root of a negative number, that means lambda has to have a negative value here. All right. Y, therefore, well, y is -2x, so that would be -2 square root of negative lambda over 2. You had a question? Actually.
I was just wondering, why didn't you use lambda as the jumping word to set the other stuff, so you don't have to deal with workers?
Well, one way or another, I'm going to have to, I mean, square roots are going to get involved. What are you suggesting?
I was saying that since y is equal to 2 lambda and xy is equal to lambda, 2xy equals yz.
Right, but that's one equation.
And then you can use xy equals -xz.
Oh yeah, I mean that's effectively you're doing the same thing as me, just in a different order. But you'll end up with something squared eventually.
There's one square thing, but it cancels out on the other side.
Okay, if you see a different way, I mean I'm just ballparking it. If you see a different way that doesn't do it, that's fine. There is no one way of doing it. As long as you get the answer, that's completely fine. And so I could then substitute this in here. Xz will become square root of negative lambda divided by 2 times z, and that's negative lambda. I'm running out of time here. So I could solve that. So z now would be square root of 2 divided by negative lambda multiplied by negative lambda, which will be square root of negative 2 lambda. I think I've made a mistake here now. I tell you, let's finish this one tomorrow, right? Because I don't want to go back and waste your time when we're already over time, but I also want to get the right answer. I do know what the answer is supposed to be. The answer is supposed to be 1, negative 2, 2. All right, but I think I've gone off on a wrong tangent here right at the start. So remind me, we'll start this one tomorrow and I'll go through. But if everyone's got it, then that's fine. You don't need to see me go through it. Will that be a maximum or minimum? It's going to be a minimum, right? If you want to know that, just pick any other x, y, z value that satisfies the requirement, such as z equals 6. Plug it in, and you get an answer of 0, whereas if you plug that in, you get an answer of negative 2. Right? So, sorry, negative 4, not negative 2. Yeah, I mean, I'm absolutely sure you're right. I couldn't, from what you were saying, it wasn't. Oh yeah. That's a much better idea. Yep, absolutely. Yeah, I've gone off on a little rabbit hole with. All right, any homework questions? Happy with it? I mean, I've got an example that will kind of cover sections 8 and 10 rolled together here, but if there's any homework questions, I can do those first. But if not, all right, so I want you to optimize this function. So we got 4x squared plus 2y squared minus 4y plus 7. Subject to 4x squared plus y squared is less than or equal to 1. So this is the one that's really the direct sort of analogy of the Calc 1 stuff, where you would optimize, back in Calc 1, you would optimize a function of x on some interval a to b. And so you had to consider the inside of the interval and then the 2 endpoints. Well, here we don't have an interval, we have a region of the plane. And so you have to consider the interior and any possible critical numbers there, and then the boundary itself where you want the Lagrange multiplier thing. So there's basically 3 stages to this. Stage 1 is to find the critical numbers, or at least the critical numbers inside the region. Step 2 is to run the Lagrange multiplier analysis and find the points on the boundary that offer possible maximum and minimum. And then the third part is to actually evaluate the function of all of those things collectively and pick out the biggest and the smallest. Whether they're inside the region or on the region, you'll have to see. But a problem like this is basically, part 1 is 13.8, critical numbers, and run the second partials test 2. Part 2 is 13.10, Lagrange multipliers, and then part 3 is just putting it all together for an answer. So see what you get. Try to spend a bit of time doing that. Oh yeah, it is. Yeah, if it's a continuous function, it always will be. You should get 0 both ways for f of x, y.
I wasn't thinking, I was trying to take f of x, x, y or something.
So first thing I want to do here, find my critical numbers. So partial df dx will be 8x. Partial df dy will be 4y minus 4. And so my critical point will be 0, 1. It's the only one. As to what it is, well, I mean, for this problem, it doesn't really matter. You know, in the same way that back in Calc 1, you didn't really need to run the second derivative test if you were finding the absolute maximum and minimum on an interval. But since this is kind of, in effect, a review by this point, let's try and roll everything together as much as possible. So in terms of the second partials test, D will be fxx, which is 8, times fyy, which is 4, minus fxy, which is 0. So it's... No, be careful with that. It's positive, therefore it's a maximum or a minimum. If it's positive, you then go look at fxx or fyy, whichever you prefer. And in this case, since fxx is positive, then it's a minimum. All right. But if that's it's really easy to do that, to think D positive means conclusion, but actually D negative means conclusion. D negative means saddle point, no maximum or minimum. 0 means nothing, test just isn't working. D positive means now you go look to see if it's a maximum or a minimum. All right, so this thing here is a relative minimum. All right. Secondly, gosh, this is really running low on charge or something. Secondly, I'll run my Lagrange equations. So I've got fx is lambda gx, fy equals lambda gy, and g of xy is a constant. So is what my Lagrange multiplier equations are. In this case, of course, this is my g, and equal to a constant is actually equal to 1. In part 2, I'm specifically interested in the boundary where that thing equals 1 rather than is less than 1. So fx is still 8x. Gx is also 8x. So this is 8x lambda. Fy would give me 4y again. Gy, of course, is 2y. Sorry, minus, thank you, minus 4 is 2y times lambda. And then finally, I've got that 4x squared plus y squared is equal to 1. So what does this first equation tell me? It tells me lambda equals 1. Or x equals 0. Right? You're going to consider every possible situation that will solve the problem. So there's actually 2 scenarios I need to think about here, and I'll need to take them one at a time. So if I take lambda equals 1, that means that 4y minus 4 is equal to 2y, which means that y must equal 2. And if y is equal to 2, hang on, is that right? Oh, I've miscopied this. I'm sorry. I was about to say that doesn't make any sense. This should have been less than or equal to 4. I mean, yeah, I could do it with 1, but obviously I don't. Y can't equal 2 there. Sorry, I've miscopied my own problem. It doesn't change anything of the work so far. Because if I try putting y equal 2 in when it's equal to 1, I get an imaginary value for x. but it'd still be the square root of -3. It'd still be an imaginary number. Be plus or minus an imaginary number, but that's, I mean, it's a valid question, but it's not. I'd rather do a question where there's more meaningful answers for illustration. So sorry, I don't know where I saw that one from. So if y is equal to 2, that means x is equal to 0. Which, of course, notice I have also the possibility there of x is equal to 0. But if x is equal to 0, that means y squared is 4, which means y is plus or minus 2. Yeah, yeah. I mean, you can get a repetition of solution from that point.
So would you have 3 critical points here?
Well, again, don't forget, these are actually critical. You gotta be careful with your terminology. Only the 0, 1 is a critical point. But I have 3 points that I will test that my function at. I will test at 0, 1, 0, 2, and 0, -2. All right, and so my function, and I'll squeeze it on one page rather than, although I'd normally do another. So f of 0, 1, of course, will be 2 minus 4 plus 7, so 5. F of 0, 2 will be 8 minus 8 plus 7, so 7. And f of 0, -2 will be 8 plus 8 plus 7, so 23. And so here's my minimum, and here's my maximum. So if, for example, this was volume level in a room where the room was basically an elliptical room given by that boundary, then the loudest point would be at 0, -2, and the quietest point will be at 0, 1. And 0, +2 actually winds up being neither one thing nor the other. Basically, 0, 2 is the quietest point on the boundary, but that's not the quietest point in the entire region. So it winds up being not a part of the answer.
Then what would it have?
You wouldn't consider it because you're only interested in real solutions. So if they're not both real valued, then it's not actually a point that you can consider.
But a negative value inside the square root times a negative number outside the square root doesn't make it a positive number.
Yeah, a negative number inside a square root is imaginary.
Where did you get the x equals 0 from?
I've been looking for anything that makes this true. So if x is anything except 0, then lambda needs to equal 1. But if x is 0, lambda could be anything. That'll still be true. So in effect, you've always got to remember, this is one of those things in math where you kind of get settled into routines and forget that there are rules about them. So when you say lambda is 1 there, what you're doing is dividing both sides by 8x, right? Well, the reality is that the rule in math is you're allowed to divide both sides of an equation by a number. You are not allowed to divide both sides of an equation by a variable. Right? That's not okay because variables can be 0. So what we should be doing with this, the formal approach that people rarely do, but when you see something like this, what you should be doing to solve it is subtracting 8x lambda from both sides and then factoring 8x out of that but you're not supposed to divide through by x ever, or anything involving x ever. So the formal way of doing it is to create a polynomial equation and solve and say, well, if those two things multiply to 0, then one of them 0 or the other one's 0. Now, because dividing through by stuff so frequently works as a shortcut, you almost forget that there are rules about it. But you do have to be careful, because that will mean you lose solutions to problems, right? If you divide through by a function, that's fine, as long as you bear in mind that you have just ruled out the possibility of that thing being 0, the thing you just divided through by. Because if that thing is 0, that's automatically a solution to the original problem too. And so you do have to be careful with that, because in a problem like this, you can lose one of your points that you're supposed to be testing, and it might be the one that gives you the maximum or something. So do watch out for that. The official rule is same with multiply. You can't multiply both sides of an equation by something involving x, because again, if x is 0, you've just messed stuff up badly. So really, everything's supposed to be manipulation and factoring. Really, the 0 factor property says that if two things multiply to 0, one should be 0, actually should get used way more than it does in math. It usually only gets used in quadratic equations, but it actually should get used a lot more. So,
is that only with like multivariable?
no, any. I mean, if you know, it's amazing how often, if you say to someone in algebra, do that, and they'll say, okay, I'll divide both sides by x, and so x is equal to 1. Well, yeah, x equals 1 works, but so does x equals 0. It's a quadratic equation, it should have two solutions. But because they think, oh, I'll just divide both sides by x, missing the fact that that's not okay if x is 0. And if x is 0, that also satisfies the equation. So it's been true ever since algebra. Right. Well, it's because if you divide by something that could be 0, you are in effect ruling out the possibility. The fact that you're dividing by x, you are implicitly saying, I am now no longer considering the possibility that x is 0, because otherwise what I just did isn't valid. But of course, the very fact that you've chosen to divide by x is because it was there as a factor on both sides, and therefore x equals 0 actually did work. Any time you've chosen to divide by something, then that being 0 must have originally been okay. And so you're kind of basically taking one of your solutions out of the arena in doing so. Now, again, don't get me wrong, no one's ever going to mind if you do like divide both sides by x, so long as you also bear in mind separately the possibility of that thing being 0. You know, as long as you don't lose any solutions, then no one's going to worry too much about the specific way you write it down. But the minute you lose a solution, obviously, then you're not going to get full credit because you're not fully answering the question.
So the other solution always just equals 0?
I mean, not quite, in the sense that you could have divided both sides by like x minus 1. So the other solution is always whatever you divided by being 0, but that might mean that x is 2 or something like that. But I mean, yes, to some extent, yeah, it's there underneath it all.
I'm like questioning everything.
Yeah, and I mean, don't get me wrong, I do the same. I still think I'll divide both sides by x squared or something. But it is one of those things that's deceptively tempting when it really shouldn't be. And there's a degree to which schools and then us in college should do a slightly better job of teaching to always look to factor rather than to divide. But that is truly the way it should be done. So. Okay, so any other questions? Right, let me for the rest of today, for the most part, just recap, because this has been a long chapter. I mean, level curves seem a long time ago now, especially since we had full break in the middle. What do you say?
That was this chapter.
Yeah, I know. Believe it or not, that was the first thing we did in this chapter. But yeah, we're going back quite a way. So, I mean, this chapter does sort of feel like two halves. The first half is very much just introducing the concept of multivariable functions, you know, as an idea. The second half is actually doing stuff with them, but it is all together. So yeah, so section 1 is the level curves idea. And so you can expect a question where I ask you to sketch the level curves of a function. Remember, that just means put the function equal to a constant and sketch the resulting graph, which will be an x, 2 dimensions, be on the plane. And don't forget to label the level curves. Level curve diagram is no good if the curves aren't labeled with the output value of the function. So, you know, for example, if you know, if fxy is say sine x minus y. No, actually sine of x and then subtract y. And so I'm interested in where that's equal to some constant value, which I could rewrite as saying y equals sine x minus c if I want. And so when I come to do my level curves, well, if c is 0, then it's just y equals sine x. But if c is 1, now it's sine x minus 1, so the whole graph has been shifted down 1 unit. Sorry, if it's try that again. If it's 1 unit, it would touch the x-axis, I guess. So there's c equals 1. C is negative 1. So y equals sine x plus 1. Now it's 1 unit above. And so on. And I mean, how many do you do? Well, the question is likely to tell you. But these would just be a load of sine waves all kind of fitting above each other. And the visualization of it, of course, is that the c value corresponds to where the z point, you know, or the, yeah, where on the z-axis it is. So c equals 0 means actually on the plane. C equals 1 means 1 unit out. C equals negative 1 means 1 unit. And so basically this is a sine wave that's sort of angled out the board. It's kind of a thick wave coming out of the board at some angle of 45 degrees, basically. But it's a way of representing a multivariable function without having to actually draw a 3-dimensional graph. You know, if I tried to do this 3-dimensionally, then I guess it kind of looks like, you know, kind of, that's terrible. Never mind, forget that.
Yeah, it's like I'm making a bunch of speed bumps.
That wasn't going well, was it? Hopefully you can imagine it better than I can draw it. But we're sort of done with the surface point. The whole idea here is level curves take the place of that. It gives you a more manageable way of representing what's going on without having to actually draw it. But you do need to label those curves corresponding. But that's what section 1 was really doing. I wouldn't worry about level surfaces because in effect it's the same idea, but now you've sort of doubled up. Now you do have to draw surfaces and you're still having to label them as well. So level surfaces is kind of the best way we've got of representing a 4-dimensional situation. But I'm not going to ask you that. So you simply have to do this kind of thing.
I was just wondering, like, how do we?
Yeah, that's the kind of thing where without some kind of software, you're not going to have to, you're not be able to do that. Section 2.
Actually, draw it without software. If we put anything on the paper, you probably would have.
Yeah, I certainly wouldn't be in a position to say that yours isn't good enough because it'll be better than what I would have done anyway.
Not those little surfaces.
Section 2 is a lot of detail and a lot of technicality, but building up to the idea of a limit. And the main thing I want you to be able to think about in section 2 is showing that a limit doesn't exist. Right? The concept of showing a limit doesn't exist by considering two different ways of approaching whatever point you're approaching, whatever limit is shown, and getting a different result in those two directions. So you need to know what's in section 2 because it informs what comes afterwards. But in terms of me actually asking you questions in the test, it will be along the lines of either show that this limit doesn't exist, or as we learned a little bit later on, I could say that show this is not continuous, and you could show that something is continuous by showing that the limit doesn't exist, because part of continuity requires a limit to exist. So to some extent, that's the same question, just in two different disguises. Show that the limit doesn't exist, or show that the function is not continuous at this point, either way. But that's what section 2 is doing when you read through it. Section 3 introduced the partial derivative. You know, by this point, you've been finding partial derivatives long enough that section 3 should look pretty easy when you go back now. You know, there were some applications of what partial derivative means, but even those to some extent were placeholders until you got to the idea of the gradient. The gradient has really taken those and built them into a much bigger idea. So most of section 3 now is, you know, I'm not really going to ask you questions lifted directly from section 3, but because section 3 question just, here's a function, find all the partial derivatives. Well, you're going to have to do that, but now you'll do it as part of a bigger question. You know, now you'll be doing it to find the gradient, or to find the critical number, or whatever it may, or to solve Lagrange's equations, or whatever. So section 3 is just a skill introduced that you've then used ever since, basically. Section 4, differentials. Make sure you know the idea of differentials, and there will be a word problem dealing with that, an approximation problem. There's going to be two types of word problem on this test. One is approximation by differentials. One is optimization from section 9, you know, finding the maximum or minimum value of something.
Differentials was the thing where like we took where we did not the delta, but the delta.
Delta x, yeah, and so delta x being approximated by dx. And there's a formula on page 904 that kind of everything's built around. So when you read through that, you see that. But section 4 is very much a standalone thing. Section 5 was the two versions of the chain rule. And you'll need to know that. That's the kind of thing that the test questions are going to be a bit of a cheat, because I'll be asking you to do something with that isn't really practically useful. I'll just basically say to you, use the chain rule to differentiate this. And it might be that in reality, you might choose a different method, but I'll want to see you show that you understand the chain rule. And it might be a bit of an artificial question in that I'm just telling you that you have to do it that way, whether you like it or not. Well, no, you'd have to work that out, because the question will determine that for you. That's down to, so remember the two types of chain rule basically dependent. In both cases, z will be some function of x and y, right? You can guarantee that. But then the question becomes, does x and y just depend on t? Or does x and y depend themselves on more than one variable? Right? If it's the first version, then it's the first version of the chain rule. And technically, it's not a multivariable question at all. At its heart, z actually only depends on t. And so in the first question, the thing you're actually finding is not a partial derivative at all. It's really just a different approach to a problem you've already been able to do, except instead of trying to do the whole thing in one single complicated step, you break it down into smaller individual steps. Whereas in the second case, now there is no full derivative, but there's partial dz ds and there's partial dz dt. And the chain rule gives you those things. That second one is the more overall useful one in math. So when we do engineering, calculus, when you're doing partial differential equations, I mean, there's a ways to go before you get to that, but that chain rule gets used a lot. The first chain rule only ever gets used if you feel like it. You never need it. It's just an option. The second one is required at times. So, you know, but you need to know both. You should be aware of how both work. And that kind of marks the end of part one, where you're just getting the whole idea in place for multivariable functions. Section 6 is where you start using them. So section 6 introduces the idea of the gradient function and a directional derivative. So reminder, the gradient function itself is a vector value function. Right, that harks back to the earlier chapter where if you've got a function of f of xy, the gradient function itself is a vector. But we introduced it by finding a directional derivative. It actually got brought into play by considering the idea of a directional derivative. And the notation they used for that, you see back on, let's see where they use it, back on page 922. So this notation means the directional derivative in the direction of this vector, u, of this function. So I think section 6 is quite complicated because there's several different ideas all closely related, but they're fundamentally different concepts. And this you found by doing the dot product. But what the directional derivative meant was f of xy gives you a surface.
And u is a unit vector, right?
U is a unit vector in some direction, and you'll be given a point somewhere on the surface. So when I'm right, I mean, really, I guess this should be a, b rather than x, y, because there's specific values associated now. It's not x and y in general, it's a specific point on the surface. So what that's really saying to you is, okay, go stand at that point on the surface and face in the direction of u. This thing will tell you what the slope is in that direction at that point. Now that basically relates back to, of course, what originally, back in section 3, what fx and fy were. Notice if this vector happened to be the I vector, in other words, if I was facing in the x direction, if I dot this with I, I'll get fx times 1 plus fy times 0. In other words, I'll just get fx. So fx is the directional derivative specifically in the x direction, which is how it was introduced. It basically said, take a surface, intersect it with a plane parallel to x. That will give you a curve on the surface. And fx represents the slope of that curve. That's how it was introduced originally. Same with fy in the y direction. But you kind of don't need those once you've got to here, because this gives you the slope in any direction. So now you can think, okay, I've had a point on a surface. I can work out the slope whichever direction I go. That's what the directional derivative is. So the physical meaning of fx and fy has kind of been absorbed into this as a single concept.
And you would give us, like, we would be given the point, and we would be given.
You would have to be given the function, because that's the surface, the point, and the direction. All three. Without all three of those, you don't have a well-defined question. Because I need to show you what the surface is, I need to tell you where to stand, and I need to tell you what direction to go. But the gradient function itself is a part of that process, but it also has its own meaning. And the gradient function, remember, points in the direction of maximum increase, which helped us a lot with the heat-seeking particle question. Now, a heat-seeking particle question I will put on a take-home, mainly because I don't think it's fair of me to expect you to solve even a basic differential equation earlier than the course of differential equations. So whilst I don't think it's that difficult, I think it's the kind of thing where you should be able to look up reference material to help you. So yes, I'll put on, and it won't necessarily be heat seeking, but it'll be a question that involves something that's trying to find its way to either the maximum point or the minimum point of something. I mean, it will, yeah, basically, yeah, you'd want to point. I mean, I'll do maximum just to not worry about that, but something could be seeking out in the minimum. And don't forget that, you know, as we saw, that often doesn't end up being a straight line because it doesn't know where until it gets there. So it just has to do everything incrementally. But that heat-seeking particle question was also in section 6. Section 7 was tangent planes and normal lines. That's pretty routine. As long as you know what, you know, as long as you're ready for those questions, they're all the same. They're all fairly routine. There's not really any complicated math in there. It's just a case of knowing what the question's asking and what, you know, what a normal vector is and how to use it to some extent. So I think those questions wind up being fairly easy points on this test. And then finally, sections 8, 9, and 10 were what we've just been doing. Section 8 is critical numbers, second partials test. Section 9 is applications, word problems. Section 10 is Lagrange multipliers. But again, they can easily be merged together like the first question we did today. So Monday, I'll just be examples of this. So on Monday, just bring, when you're studying over the weekend, you know, bring specific problems you want to see worked, or maybe just I'd like to see another heat-seeking particle or whatever. Any like generic questions now? I don't really have enough time to do actual examples, but any general questions about the chapter or the test?
Does the section review in the book, does that help?
Yeah, I think they always help. The only thing to watch out for is occasionally we'll skip over, you know, like I didn't do every last detail. So there may be some questions in there that will look very unfamiliar because we didn't do them. Although we haven't missed over much in this. So I'd say, generally speaking, yeah, I always think those are good problems. They come into their own, this chapter not so much, they come into their own when it's important in a test that you're, what's a good example? Think back to Cat 2, right? When we were doing chapter 8, the integration techniques, and you've got integration by parts, trig integrals, partial fractions. Your problem with the homework is if you're doing problems from the partial fractions section, it's not, you know what to do, right? You know it's going to be partial fractions. You don't have to think to yourself, I wonder if this might be integration by parts because it's in the partial fraction section. So it's good practice, but then when the test rolls around and it becomes important that you look at a problem and think, all right, I'm going to try this one by trig substitution. The review problems will give you much better practice at determining which particular method should be used than the homework problems will. But in this chapter, I don't think you'd ever get mixed up. I mean, the questions look so different from section to section. So yeah, definitely, but there are times when even more so, I would say, yeah, for sure. Next chapter will be one where you'd find that very useful. Ash.
What's the problem usually? How much
That's a good question. It'll be more loaded towards the later stuff because the later stuff incorporates the early stuff, right? Like I said, section 3 is really just teaching you how to do partial derivatives. In the test, that will now just be a part of a find the maximum and minimum value question. You know, in doing so, you will have to find partial derivatives. So, you know, a lot of the earlier stuff was really just setting up what the later sections did. So yeah, I mean, there'll be a level curve question, there'll be a limit question, there'll be a chain rule question, a differential question, but for the most part, I'd say it's you'll find the later stuff, the application stuff, a bit heavier. So. But yeah, study this weekend, and then Monday is whatever you want to see examples of. All right, and budget for the take-home part of this, I will be expecting back on Friday. So plan your next week to leave time to do a take-home at some point before Friday.
Thank you so much. I will see you Monday.
All right, have a good weekend, guys. I honestly haven't decided yet. Beyond putting something like a heat-seeking particle, it's
just the really long ones.
I was going to say, take-home isn't really always necessarily about topic so much as how long I think a question will take. And you know, there's a few sections where I could write a longer question. So until I do that, I won't entirely know.
Like the thing we did in class today, because that's
right.
Happened in the past.
Right. Yeah. But the thing is that also is a few sections rolled together, and so I don't mind a longer question if it's representing several sections. I don't want one question being long that only represents one thing on there. But, so.
Thank you.
Cool. 13.9, number 12. Maximum volume, the material for constructing the base of an open box costs 1.5 times as much per unit area as the material for constructing the sides. For a fixed amount of money, find the dimensions of the box of largest volume. Okay, so we've got an open box. So 13.9, number 12. So we got an open box. I.e. there's no lid. So dimensions of the box, well, let's make this X, Y, and Z for the dimensions of the box. So the thing I'm trying to optimize is the volume, which is obviously just X, Y, Z. But subject to a constraint that the total amount of money I've got to spend on the box is finite. Now, what is that amount of money? Well, the base, so let the cost of the cost of the material for the sides. Sides can be, let's say, C dollars per square foot, something like that. All right. And so the cost for making this, well, I've got two sides that have an area of XZ, front and back, right? That has an area of XZ, and so does this side at the back. So they will cost their area times C. Then I've also got the other two sides, which will both have an area of YZ. I guess, well, actually, C they've already used in the question, haven't they, as a finite amount of money. So I guess I should use something, let's use P, I guess, for this. I'll need to use C later. So I guess the price, let's call it, of the material for the sides could be P. And then I've got the base, which will be xy. Just one of those, though. There's no lid to this. But of course, that costs 1.5 times p, because it's a more expensive material. So let's write it as 3/2 p. And that's equal to c. Okay. Because it says that the base is 1.5 times as much per unit area.
We're not allowed to have calculators on this, right?
Correct. Yeah.
And what about, like, say, I think one section involves, like, finding the angle of inclination.
Yeah, I'd just say find the cosine of it. You know,
Oh.
if I said to you find cosine theta, then you wouldn't need a calculator for that. You're right that you need a calculator to actually find the angle, but I'd set it up so you can answer the question without a calculator, or put it on the take home if it needed a calculator. So.
Cosine is cross product, right?
No, dot product. Sine is cross product. So here's my expression. So let's the volume is still low, isn't it? I mean, if you take the lid off a box, it doesn't change the volume of the inside.
But the inside is empty, right?
Well, the volume is what it could. I mean, if you filled the box with water and then took the lid off, you'd still have the same amount of water inside. So the volume is the space inside, which isn't affected by just remove. I mean, obviously, if you remove the side, then the water would all fall out.
I was thinking more along the lines of the sides.
Yeah, so it changes how much material you need to make the box without actually changing the volume of the box. So I could kind of simplify this a little bit. If I multiply everything by 2 divided by p, just to try and clean this up a little bit. Yeah, multiply everything by 2 divided by p. That will give me 4xz plus 4yz plus 3xy is equal to 2c divided by p. The point is really here that from a calculus point of view, a constant's a constant, right? This c can be absolutely anything here. The question doesn't change with the value of c, nor does it change with the value of p. This is just a generic question where we're keeping those two things fixed. So 2c divided by p, I'd be much better off just saying, why don't we just call this c? Or if you hate using a letter we've already used, then maybe I'd call it a or something. But it's just a constant, and I'm just confusing matters by writing it as a combination of constants. But all that matters is when I differentiate it, it's going to be 0. Now, by this point, I know I've got Lagrange's equations. Right? I actually could approach this as a Lagrange multiplier equation, but in 13.9 it wasn't expecting that because it hadn't introduced them at that point. So since this was a 13.9 question, let's stick with it as a 13.9 question. So I want to try and make one of the variables the subject here. Let's just go with z. All right. So if I subtract 3xy from both sides, then what will be left behind is the 4xz plus 4yz. In other words, I can factor z out of that. And so z is some constant a minus 3xy over 4x plus 4y. Right, that's my constraint rewritten to express one of the variables as a function of the other two.
you have to consider now x and y being 0?
Well, not in this case from a purely practical point of view, that I wouldn't have a box if x and y were 0. So you're right in terms of what I was talking about, that if x and y were both 0, that's not a valid step. But word problems usually bring with them implicit domains which take care of that problem. And in this case,
Oh, yeah, because the volume would be 0.
right, and I literally wouldn't have a box anyway. So, you know, the problem is kind of really insisting that x, y, and z are positive valued. And so you're right to think about it mathematically, but you get to pull that kind of trick with word problems and sort of justify things by common sense in that way. In the same way that I wouldn't have to ever worry about x being negative here either. And so my volume function now can be written as just a function of x and y. So it'll be xy times a minus 3x squared y squared all over 4x plus 4y. And a can be absolutely any value here and it won't change the answer.
You're getting that from the XYZ?
Yeah. And so basically what I'm looking for now are the critical points of that function. And then, you know, I technically should do a second partials test as well, but it's pretty obvious that I'm trying to maximize the volume here. I mean, minimizing the volume would be easy. I'd just make any one of those three infinitesimally close to 0. And my volume would be, you know, basically spend all my C dollars on the base and with a microscopic side, and there's a volume of almost 0. Mathematically, just a limit where it actually is 0. So minimizing the volume, A, why would I want to minimize the volume of a box anyway? And B, common sense tells me how to minimize it. What I want to know is how do I maximize it? So, you know, in that sense, the second partials test isn't really necessary in this context, as it would be in a more abstract kind of me giving you a function and say, find and classify the critical points. You know, if I do that, not in any kind of word problem context, then there's no obvious implication. You can't read anything into the context of the question to determine whether you're finding a maximum or a minimum. You just have to run the second partials test on it. But in a case like this, I think you'd be just fine just doing what we're doing. So let's think about it. So V is xya minus 3x squared y squared divided by 4x plus 4y. And so I need to know what Vx is. Well, I'm going to need my quotient rule here. So that's the denominator times the derivative of the numerator with respect to x, which would be ya minus 6xy squared, all divided, minus the numerator. Oops, gosh, doing this very well. A minus 3x squared y squared times the derivative of the denominator with respect to x, which is 4, all over 4x plus 4y all squared. Now I don't want to spend, this is quite a lengthy problem. I don't want to spend the whole class on it, so I'm just going to do the Vx and leave the rest, you know, as an exercise to do if you want. Notice I don't have to worry about the denominator because that can't be 0 meaningfully, and therefore it doesn't matter. You know, what I'm interested in is Vx either being 0 or undefined. Well, it can't be undefined, and if it's 0, I only care about the numerator. So basically, I can pretty much forget about the denominator here and just try to find the, yeah, actually.
This problem on the test, it looks like it would definitely be a lot simpler to do Lagrange. So would we be
Right.
able to do Lagrange?
Yes, absolutely. Yeah. And again, you know, the trick of writing test questions is to find a question that is deep enough for me to check that you understand the concept, but quick enough that you don't end up spending 20 minutes of your 55 minutes on one thing when I've got a whole chapter to test you on. So, I'm not going to ask you a question where it ends up being 80% messy algebra, because that's not what this chapter is about. This chapter, I need to know, do you understand the concept of critical numbers? Do you understand the concept of optimization? Do you understand what the gradient function tells you? Do you understand what a partial derivative is? There's inevitably going to be some algebra along the way. It has to be, but it can't become the dominant part of it to me. So I try and write questions that mean that, the non-chapter 13 material that you'll need is either fairly low key, or it's just something that's important. There are some things like integration skills, derivatives. To some extent, part of what we're doing here is the quotient rule, right? You learned that back in Calc 1, but it's so important, it never goes away. I'm quite happy to make that a major part of a question, because if you're not getting the quotient rule right, honestly, you don't deserve to be getting the credit for the question. So some things are important enough that they never go away. But other things, like little details of, solving equations, if you know that you need to solve the equation, that's what I care about. I'm not going to give you a cubic equation to solve where you suddenly end up spending 20 minutes trying to factor the thing. So, okay, so in this case, what do we get? Well, if I distribute here, so to put Vx equals 0, I get 4xya minus 24x squared y squared plus 4y squared a minus 24xy cubed minus 4xya minus 12x squared y squared. And notice that I get a 4xya minus 4xya disappears, which is good. Notice I also have a y squared running throughout everything else, which I can factor out. So if I factor y squared out of this, that leaves minus 24x squared plus 4a minus 24xy minus 12x squared. So I should have made this is minus 36x squared. Yeah, because I have minus 24x squared y squared and then a minus 12x squared y squared as well. And I know y can't be 0, so I can divide both sides by y. And so what I end up with here is that 36x squared plus 24xy is equal to 4a. That's what I require. And so y is, I guess, 4a minus 36x squared divided by 24x.
I think, shouldn't there be a plus right over a plus 12x minus?
Oh yes, sorry, you're absolutely right. Thank you, Christian. Oh, that changes things, doesn't it? So that should have been minus 12, not minus 36. Thank you for that. And of course, I've got a factor of 4 running here. So y actually is going to be a minus 3x squared divided by 6x. Now I'm going to stop it at this point because the question wanted to know what the dimensions of the box need to be. Well, basically what I'm really looking for is y in terms of x and z in terms of x, right? Because the dimensions are going to be along those lines. So if I know what x is, then that's y, and I can plug both of them into the original equation to get z. So I've now got that as well. But you're absolutely, I mean, Lagrange multipliers will be a much, I mean, in some ways this is good in that it's given us a bit of a reminder of how this works, but maybe more than any other example we've done so far, it's shown you why Lagrange multipliers will be a nicer approach to that. I'd do it, except we did one of those the other day, and I don't want to spend the entire time just doing optimization problems, but I think you will definitely see a benefit to Lagrange multipliers. Yes, Ash.
Can we go over a channel in terms of S and T?
Yep, absolutely. Any questions on this before I get? Is that okay, Christian? Did I kind of show you enough of
Okay, yeah.
what you're looking for? That's kind of the setup of it. From this point on, it's really just an algebra, but it's a messy algebra problem. So don't worry. If you get the concepts, that's all that really matters for the test. So.
Okay, yeah, I think I got it.
Okay, so let's. I mean, I'll just make one up. It's probably easy. Oops. So let's say that z here is x squared divided by y plus, say, e to the power 2x minus sine y, where x is s squared plus t squared, and y is 3s cubed minus y over t. Now, your two choices here are to either substitute that x and y in to try and write z directly as a function of s and t, and then use your derivative rules, which hopefully you can see will be quite messy, or to use the chain rule, which, let me remind you, so partial dz ds is partial dz dx times partial dx ds plus partial dz dy times partial dy ds. And to deal with it in terms of 4 different simpler expressions, all then combined into a single formula. See if you can do it that way. And then also partial dz dt as well.
partial z, partial z, partial x has to have x and y in it, right?
Well, the final answer should only involve s and t. So you want to, at the end, then plug in the values of x and y, but only once all the differentiations happened. So like in this case, well, it's probably a good time to do this. So partial dz dx would be 2x divided by y plus 2e to the power 2x. Partial dx ds will be 2s. Partial dz dy will be minus x squared over y squared minus cosine y. Partial dy ds will be 9s squared. But at this point, having done the derivatives, now I really want this thing in terms of s and t. So now I can go through and say, okay, x is now s squared plus t squared. Y is 3s cubed minus 1 over t plus 2e to the power 2x, which is s squared plus t squared, all multiplied by 2s, plus minus x squared, so minus s squared plus t squared all squared, divided by y squared, which is 3s cubed minus 1 over t all cubed, minus the cosine of y, 3s cubed minus 1 over t, times 9s squared. There's then no expectation of simplifying that. Again, that will be algebra for not telling me anything really. You know, the point is just looking at that should give you a feel of what it would have looked like to try and differentiate, to plug in x and y first and then use product rule, quotient rule, chain rule. Right? It's a real mess either way. It's not quick either way, but this way keeps things far more manageable. You're not trying to do 5 things at once. You're trying to do 2 things in 4 different places and then combine them together. So you're much less likely to make a mistake, even though you end up with a real. Of course, that does simplify if you tried, but that's not what I'm interested in. So if you're happy with that, then you understand the chain rule to the level that I need you to understand the chain rule. Okay?
Wait, why is the bottom one cubed?
I don't know, because I'm not paying attention. Should be squared.
First I asked,
No, that's just me not paying attention. Make sense? Happy with that? All right, what else? We got 20 minutes, just under. You will see an example of.
Well, is there any like, is there any like domain and range on the test, right? Also?
I mean, in the context of level curves, yes. I mean, level curves kind of incorporate domain and range and a bit more into one question. So that's kind of how I'll ask that, if you like. But to some extent, when you label the level curves, you're almost to some, I mean, you're not giving the range there, but you're giving a sufficient sample that I think you could infer the range from it. And similarly, when you draw the level curves, the space they take up is in effect the domain. And so, you know, for example, let's imagine your function was this. Okay, so your level curves are when your function is constant. So y minus x squared is c squared. In other words, y is x squared plus c squared. So you're talking parabolas for your level curves. But c squared is definitely a positive number. So it's y equals x squared. Circle would that be x squared plus y squared equals something.
Oh, yes, he's a
And so, you know, if I put c equals 0, then y is x squared. And so I get my standard quadratic graph, parabola. Which I label with c equals 0. But if c is equal to 1, then I get y equals x squared plus 1. So a parabola shifted 1 unit up. If c is equal to 2, then y is x squared plus 4. So a parabola shifted 4 units up. C is 3, a parabola shifted 9 units up. But by implication, you can kind of see by picking these, I can see that my domain, the fact that all this bit down here is empty, is giving me some implication about domain. Of course, if I specifically asked you about domain, it is possible, you know, there are questions just about domain. So if I asked you for the domain, well, you'd say, well, y minus x squared has to be greater than or equal to 0. You can't square root a negative number. So y is greater than or equal to x squared. But remember, domain now is a region of the plane, not an interval. So basically, the domain in that sense is this. Everything on or above y equals x squared. But the level curves kind of incorporated that to some extent. C can't be negative here. You can't have c equal negative 1 because the square root of something can't be negative 1. And so by drawing the level curves, I was kind of drawing some samples which gave the implication of the domain with them. Similarly, the range here, our range is still an interval, but that's going to be 0 to infinity. Can't get a negative number out of that function, but I can get any positive number out as far as I want to go. So that will be domain and range for this function, but level curves kind of show that and a bit more. Because the point of the level curves, of course, is it gives you a sense of what the surface looks like. You've got a parabola sitting on the plane because c is 0, so the output of the function. You've got another parabola, 1 unit up and 1 unit out. You've got another parabola, 3 more units up and 2 units out. So I've got a kind of a series of parabolas that are themselves forming a parabola as well, which kind of makes sense because if you think about this function, right? If z is the square root of y minus x squared, and again, don't miss the notation here. Level curves aren't the same as graphs of surfaces. They're very closely connected to each other. You can make one into the other, but if I want a surface, I'd write z equals. Level curves exist entirely within the xy plane. They're just a different way of expressing both the domain and range and more details. But if I did want to do that, well, okay, z squared is y minus x squared. And so x squared minus y plus z squared is 0. And if you look back to the first chapter, that will give you an elliptic paraboloid. And so you get that shape kind of going. Is it? I can't remember. I never remember the names. Maybe, not sure it is elliptic paraboloid, is it? What was it called? Not that I'm going to be asking you to name anything here for sure. Don't worry about that. Just trying to remember. No, yeah, elliptic paraboloid. Yeah, that was right. I mean, back then we would have written it as y equals x squared plus z squared. That actually would have been the way around we did it, and so you end up with circular cross sections. But here it's a different way of presenting the same things. Okay, does that kind of answer your question about domain and range? What else? Are you happy with gradient? Is gradient and directional derivative making sense, and tangent planes?
Confused about gradient function stuff is like, so the output of it, if it's given like a surface, it's like a 2D vector, right? Pointing the direction of the most increase, right? But then you can do the thing where you passing z along with it, and then it gives you the normal, right? It gives you the normal
So it'd be the normal vector to the tangent plane.
Yeah.
Yeah.
So I was just confused how it gives you both. Like how it gives you both.
So yeah, the problem is the gradient vector is equally applicable to 2-dimensional and 3-dimensional vectors. So what you're describing, the reason why it can give you both is sometimes you're thinking about it in terms of a 2-variable function, which becomes a 2-dimensional vector when you do the gradient, as opposed to maybe sometimes it being a 3-variable function. So you know this would be section 6 and then section 7. So to try and give you contrasting problems here. So let's look at question 29, for example, in section 13.6. So that gives me a 2-dimensional, oh sorry, a 2-variable function rather, y squared minus x root y at the point 0, 3. And the question wants to know, find the gradient of the function and the maximum value of the directional derivative at the given point. All right, so first thing I need is the gradient function, which in this case is going to be 2-dimensional. So it's partial df dx, which is minus square root yi, plus partial df dy, which is 2y minus x over 2 root y j. Right. And then I specifically want that at the point 0, 3, which will be minus square root 3i plus 2 square root 3j. All right, so that's my directional derivative at that point. That then is the direction of maximum increase.
I think x is 0, so I think that should be like that whole thing x over 2.
Right, that bit's 0, but the 2y is still going to be 2 square. Oh, sorry, 2 root, it should be 6. I'm sorry, I'm writing a square root where there isn't a square root. Thank you. So yeah, that should be a 6j. Sorry about that. And so that's my direction of maximum increase. The question says, though, what is the maximum value of the directional derivative? Well, don't forget that the directional derivative at a point is equal to the gradient vector at that point dotted with the direction that you're going. And in this case, the direction that I'm going is the gradient vector, because basically this is the dot product is the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between. Well, to maximize that, since the magnitude of u is always going to equal 1, the best I can hope for there is for cosine theta to equal 1 as well, which will happen when theta equals 0. And although that was kind of my proof, that the gradient vector points in the direction of maximum increase. And so it basically turns out that the size of that thing is simply the magnitude of the gradient. And so the answer to the other thing is simply the magnitude of this thing, which will be the square root of 3 plus 36. So square root 39 is the answer to that question. All right, so that's one aspect of it. You deal with the idea of gradient being also the direction in which you experience maximum increase. That makes sense? Contrast that with section 7, where we're trying to find an equation of a tangent plane to a surface. This time, what you'll be given will be a function of 3 variables because it's a surface. All right. So the key difference is going to be here I'm dealing with a function of two variables. Section 7 I'm going to be dealing with a function of three variables. There'll be some section 6 questions that have three variables too, but so get rid of this. Everyone happy with this? So let's shift our attention to section 7. Let's do question 20. Yes. Is that a good one? Good to do. Actually, let's do 25. No, I'll do the odd ones. I'll do number 20. So 16 minus x minus y squared. At point 28. So that's a surface. Particular point on the surface. That's going to have tangent plane. Right? The version tangent line we had before. But what I can see here, and so I guess this is your question, but anytime z x and y, you can rewrite that to say that f of x and y minus z is equal to 0. And this thing here is implicitly a function of three variables. And so that probably is what ultimately answers your question, is that concept of writing it that way. So in this case, it's like I'm saying x squared plus y squared plus z equals 16. And so my gradient function, or I guess actually to fully do it in that way, the way the book does it, I should say x squared plus y squared plus z minus 16 equals 0. And so this thing here is what the book would. No, because I'm adding x squared and y squared to both sides. And so my gradient function here will be 2xi plus 2yj plus 1k. And notice the 16 was irrelevant, that disappeared. And so my gradient function at the point 228 will be 4i plus 4j plus k. And that will be my normal vector, because the gradient functions point in the direction of maximum increase, which is also the normal vector to the tangent plane. And so the tangent plane will be 4x plus 4y plus z equals some constant. And to find out the constant, I just need to plug in the fact that 228 is on the graph, on the plane. And so 8 plus 8 plus 8 gives me 24. So the tangent plane here would be that. But they're both using the gradient, but one is reinterpreting the given surface into a three variable function and creating a three-dimensional gradient, whereas one sticks with a two-dimensional gradient.
So could you take this down a dimension too and find like the normal of the curve?
Yeah, you could do. I mean, this would work for finding the tangent line. It'd just be a ridiculously elaborate way of finding the tangent line to a curve when all you've got to do is differentiate. But it would.
Wouldn't that be easier? Because in the last chapter we were trying to find the normal vector, but it was a huge pain, right? For curves, for 2D curves.
That was not quite the same thing.
Okay.
It wasn't. This wouldn't work for that because the problem is last time you were given a vector valued function, that was to a curve. This is set up in terms of a surface that you could scale down, but I mean, to some extent that was the original definition of the normal vector. But the normal vector to a curve was easy, if you remember. It was the normal vector to a three-dimensional curve that was difficult, and that wouldn't work here. So yes, but only for the problem that was never complicated in the first place, not for the bit that was. Right, so test tomorrow. I'll see you then.
See you tomorrow.